Hello and welcome, my friends. My name is Stephen Greider, and I'm really excited to tell you everything I know about machine learning. Before we get started, one quick thing I want to mention here, how to get help in this course if you get stuck or you need a little bit of help troubleshooting. So the first place you can look to is the Udemy QA boards. You can find the discussion boards on this page. You can go look at the very bottom right-hand side, and you should see a little question mark when you hover over the video player. So you can always ask a question on the QA boards. You can reach out to me on Twitter or my email as well. In general, I usually answer all questions about once a day, usually between Monday and Friday. So if you don't see an answer from me on the weekends, usually good practice to try to poke at me again during a weekday if you want to get a quick response. In general, I answer quickest most reliably in general on email, but every now and then I get a little bit busy and I might get a little bit behind on answering your questions. Okay, so that's it. Without further ado, let's continue in the next section, and we're going to start talking about machine learning. In this section, we're going to dive right into our first technical topic. We're going to walk through a very small machine learning example. In this example, I want to walk through the entire flow from start to finish of how we might be presented with some problem that could be solved with machine learning, and then walk through some type of imaginary solution. We're not going to write any code just yet. We will very shortly, but for right now, I just want to do a high-level overview on how we would generally approach this problem. So here's the problem. I want you to imagine for a second that you are an analyst at a small city, and your city has a flooding problem. Every year, it rains a whole bunch, and every single year, your city floods. The flood causes some amount of damage, and then it's up to your little city government to pay some amount of money to fix that flooding damage. Now, this ends up being a big problem every single year. So let's imagine for a second that maybe the city manager walks up to you and asks, hey, we're kind of forecasting around 240 millimeters of rain this year. So that means that in total, over the entire year, there's going to be about 240 millimeters of rainfall. So they want to understand how much flood damage there might be as a result of all that rain. Now, this is kind of an interesting problem. How could you possibly guess how much flood damage there would be based upon how much rain falls? Well, let's lay out a possible way of solving this problem. Okay, so here's a series of steps that we're going to walk through to attempt to solve this problem. And we're going to use the same series of steps throughout many other problems that we work on throughout this course. The very first thing that we need to do to solve this problem is attempt to identify data that might be relevant to solve the problem at hand. The problem at hand, we need to somehow understand, given some amount of rainfall, how much damage there might be. So how would we do this? Well, I think that we might be able to come to some conclusion pretty intuitively. I think this makes sense. If the amount of rainfall during a year changes, we're probably going to see a change in the amount of flood damage, or more specifically, the amount of money that we have to pay to fix this flood damage. So if the annual rainfall goes up, we're probably going to have to pay more in flood damage costs. If the rainfall goes down, or if there's no rainfall at all, we're probably not going to have to pay any money for flood damage repairs. So in this case, we would refer to this annual rainfall metric as an independent variable, or alternatively as a feature. And we would refer to the flood damage cost that we have to pay for any given year as the dependent variable of this relationship, or alternatively as a label. So that means that whenever our rainfall changes, we expect to see a change in the flood damage costs. Thus, it is a dependent variable, or we also refer to this as a label. So I think that that kind of pretty closely identifies and relates the data that is relevant to our problem. We probably want to understand how much rain falls in any given year and how much damage that has caused in any previous year. So the next thing we need to do is somehow assemble a set of data using those two relevant metrics related to the problem that we're trying to solve. Now, I want to make one thing really clear throughout this entire course. In a lot of other exercises around machine learning and a lot of online tutorials and what have you, you almost always get presented with this really nice data set. A data set that has already been formatted and is in a nice CSV file or a spreadsheet, and it's really easy to load it up and then somehow run some number of calculations on it. But in the real world, we almost never get these nice data sets prepackaged for us. So one thing that I'm going to really harp on throughout this entire course is making sure that you have the ability to understand how we can collect data, assemble it all together, format it, and then use that to make some type of prediction using machine learning. So with that in mind, I want to approach this problem and think about assembling a set of data right here from scratch. Like if we didn't have this nice spreadsheet at hand that says how much flood damage there was, and here's how much it rained each year, how would we actually put this data together? Well, we might do a little bit of on-the-ground research. For example, we might go and find a newspaper snippet from 2009 that says that there was 250 millimeters of rainfall last year. So that would be in 2008. Maybe we then find a YouTube video from 2011 that says in the previous 2 years, there was 197 and 274. And on weather.com, maybe since 2011, there was 291, 136, and 306. Now that's just the amount of rainfall that we found for each year, from maybe 2008 all the way up to 2013 or so. But what about the amount of flood damage? Well, for that, maybe we go and reference like a budget or something like that. Something that says, hey, for these previous years, here's how much money we spent on flood costs or flood repair for each of these years. So you would take both these two sources of data right here and kind of paste them together and eventually end up with a nice looking table like this. Something that relates for every year, the amount of total rainfall that occurred in millimeters and the amount of flood damage money that was spent. So it took, say, $6.2 million to repair all the flood damage in 2013, but maybe in 2012 there was very little rain and we didn't have any flooding, and so there was $0 spent on flood damage repair. So we can consider this right here to be our data set. This is a table of sorts that relates our independent variable of the total rainfall, or our feature of total rainfall, to our dependent variable or label of the amount of flood damage that we spent. Or I should say the amount of money that we spent on repairing flood damage. Okay, so let's take a quick pause right here. When we come back to the next section, we're going to start to talk about how we can decide what type of output we are predicting and what that even means. So let's take a quick pause and I'll see you in just a minute. In the last section, we started talking about a tiny little problem that you might be presented with if you were some analyst at a city working on a flooding problem. So we've now identified the data that is relevant to our problem, and we've assembled that into a data set. We now need to decide on the type of output that we are predicting. Now this step, as we walk through it, is going to seem a little bit confusing or a little bit esoteric. I'll tell you right now that based on this type of output that we are trying to predict, we are going to choose a different algorithm to somehow relate our data together. So the purpose of this deciding on the type of output that we are predicting, its purpose is to somehow narrow down the algorithm that we'll use to process all of our data. Let's take a look at two common types of output that we might try to predict. All right, here we go. These are two common types of output that we might try to predict. The first is classification, second is regression. There are other types of outputs or other types of algorithms out there as well, but for the most part in this course in particular, we're going to be focusing on classification and regression. The purpose of a classification process or algorithm is to somehow take all of our input data, like the amount of rainfall for each year, and then predict some value of a label that belongs to a discrete set. Now that doesn't make a lot of sense when I say it out in plain English, so we'll take a look at an example of this in just a second. But before we do, the other type that we're going to be considering is regression. With regression, we are trying to predict values for our labels or our outputs that belong to a continuous set. Now again, that doesn't make sense either, so let's take a look at a couple of examples of both these. Okay, so first off, regression. On this diagram, I've labeled or kind of laid out three different problems or questions we might try to answer that belong to a type of regression family. So if I were to ask you, based on the year, make, and model of a car, what is its value? Well, you'd probably answer that question with a dollar value, like it's worth $0 or $10,000, $20,000, $30,000. Those are all numbers, denominations that belong to a continuous set of values. So anywhere from 0 to 50,000, or maybe it's a really expensive car and it's worth 100,000. That is a continuous set of values. My car could belong to any value from 0 to $50,000. Let's take a look at another one. So maybe based on an individual's daily calorie intake and the minutes that they spend exercising, what is their weight? Well, again, the output from this question right here, or what their weight is going to belong to a continuous set of values. So maybe their weight is either between 80 or at a minimum 80 pounds, all the way up to, say, 400 pounds. A person could weigh any amount of weight between those two values. Now, just one last example. let's say that based on the height of a pine tree, which is just a type of tree, what is its age? So how long has this tree been growing? Again, maybe that would belong to a continuous set of values, so anywhere from 0 to 500 years, and any value in between. So these are all examples of outputs or predictions that are continuous in nature. We can get a prediction or an output that belongs to any value in between these two bounds. Now let's also take a look at some examples using the other type, classification. So with a classification type algorithm or a classification technique, we are trying to predict values that belong to a very small set or a very small pool. So examples of classification techniques would be, say, based on the number of hours that a student studied for an exam, did they pass or fail? In this context, a student can either pass or fail. That's it, no other options, just those two selections. And so that's what I mean by discrete here. We get two options, you either pass or you failed. There is no like score or percentage of questions that this student got right. It is solely pass or fail. Another example would be, say, based on the content of an email, is the email a spam email or not spam? So two options there. It's either spam or not spam. That's it. And then finally, based on where a football player shoots from, are they likely to score a goal or not score a goal? In football, soccer, if you're from the US like myself, you either score a goal or you don't. So either I score the goal or I kicked it out of bounds, or maybe the keeper grabbed the ball and blocked the shot. So these are all examples of classification type predictions. We are trying to take some input and then predict an output that belongs to a discrete set of values. Now, with these two techniques in mind, classification and regression, if we think back to our original problem, where we need to decide the type of output we are predicting, you and I definitely know that we are predicting dollar values right here. So there is not like a output of we had to pay money or we didn't pay money. It's not we had to pay over $1 million or under $1 million. It is solely how much money did we spend. So this is definitely a regression type problem because we are trying to predict continuous values right here. All right, so that's a lot of talking for that one step. Let's move on to the next one. So now, based on that type of output, which we said is regression in our case, we need to pick an algorithm that will determine a correlation or some relationship between all of our features, which you'll recall is the amount of data that has fallen in this year, and our label, which is the amount of flood damage that we found. So we might go ahead and pick some arbitrary random algorithm to try to solve this problem. Now, we're not going to dive too much into the algorithm side of things on this flow for right now, because as you might guess, that's the kind of the entire point of this course, is to walk through a bunch of different algorithms. But we can essentially understand that once we pick an algorithm, we're going to feed our data that we have collected into it, and hopefully our algorithm will decide or discover some type of relationship between our different features and our single label. So after that, we would then use our model, or whatever the output from this algorithm is, to make a prediction, which in our case is to predict how much flood damage there will be if we have 240 millimeters of rainfall. So let's kind of imagine that we walk through this step together. So we're going to say that maybe we take this data set and we pass it into some algorithm called a linear regression algorithm, which is an actual algorithm that we're going to learn a lot about later on inside this course. Once we feed in our data set and run this algorithm, the algorithm says, okay, I have found a relationship between the amount of annual rainfall and the amount of dollars that we have to spend to repair all the flood damage. And that relationship is the annual rainfall in millimeters times 0.033 minus 5.1792. That's our relationship between annual rainfall and flood damage. So now recalling that the original problem statement was that we need to figure out how much flood damage there will be if there is 240 millimeters of rainfall, we would take that 240 millimeters, plug it into this relationship right here, and if we do the math, we get 0.033 times 240 minus 5.1792, and I would estimate that we would have about $2.74 million of damage. So $2.74 million in damage for that amount of rain. So I would go back over to my city manager and say, okay, I did the analysis based upon these previous years of data that we have, where we have some amount of rain and some amount of money spent to fix that damage. I think that if we have 240 millimeters of rain, we're going to have to spend about $2.74 million to fix it. Okay, so that's it. That is a walkthrough on a very simple, very straightforward machine learning problem. Now I want to very quickly give a couple of takeaways here, or just some important things I want you to understand at this point. Okay, so a couple things from each step right here. The very first thing we did was identify our independent variables. So the things that kind of relate together to make some information available about our problem. We had called features, or we used the word features to refer to categories of data points that affect the value of our output. And we called that output a label. And the next thing we did was we assembled a data set. Again, a big thing that I'm going to harp on throughout this course is that a lot of times the data we want to make use of is not always going to be nicely packaged for us. So sometimes we might have to do a lot of formatting, or essentially put this data together by hand to be able to have some data set to work with. The next thing we did was decide on the type of output that we were trying to predict, or the type of algorithm that we would probably want to use. We had said that regression is used anytime that we are trying to predict continuous values, and we use classification anytime that we are trying to predict discrete values, or values that belong to a small pool of possible values. Next, we picked an algorithm that would determine a correlation between our features and our labels. Again, that is something we're going to learn a lot about, all these different algorithms throughout this course, so we're going to go a little bit light on detail on that step for now. And then finally, once we used our model or used that algorithm, we produced a model that could then be used to make a prediction about some future value. And our models that we generate using these algorithms are going to try to relate the value of a feature or a set of features to the value of our output or our label. All right, so that's pretty much it. Let's take a quick pause right here. When we come back to the next section, we're going to start working on our first little application. In this section, we're going to start working on our first example and start taking a look at our first algorithm that we're going to use. This is going to be a fun little project. I think you'll like it a lot. We just have to spend this section to do a tiny little bit of setup. So let's get to it. We're going to go to this website listed right here, and we're going to download a tiny little starter pack. So there's just a little bit of code that I put together to make our lives a little bit easier and give us a nice little example to work with. So I'm going to open up a new browser tab and navigate to this URL. Once here, you'll see a couple of instructions inside the README for the file that give different methods of downloading it onto your local machine. So you can either download this as a zip file, or you can use Git to clone it as well. I'm going to go ahead and clone this entire repository. So I'll find the green button over here, I'll copy the link, and then I'm going to flip on over to my terminal. I'm going to find some workspace directory, some place where I'm happy to put a bunch of code that we're going to work with from this course, and I'm then going to run git clone. So that's going to clone the project onto my local machine. After I've cloned this machine, or excuse me, cloned this repository, I'm then going to change into that new folder that was created called mlkits. And then inside there, there's one folder I want to change into called Plinko. So I'm going to change into Plinko. And then inside there, I'll see that there is an index.html file. I want to open up that file right now. I don't have any other infrastructure here like Webpack or anything like that. We just need to open up the index.html file. If you're on Mac OS X, you can go ahead and run open index.html. Otherwise, if you're on Windows, you can just go ahead and manually open the HTML file by navigating it to it in your folder File Explorer. Now, once you open up the file, you're going to see a little screen like this appear. Let's take a quick pause right here. When we come back to the next section, I'll give you a quick overview of what's going on in this little application, and we'll start talking about the problem that we're going to try to solve. In the last section, we downloaded and ran a tiny little application that is now running inside of our browser. You'll notice that on this page, we have a big panel up here on the top left-hand side, and as you move your mouse around, it looks like there's a little ball that seems to follow your cursor. If you then click somewhere, you'll see a little ball fall. It'll bounce off of all the little pegs that you see in here, and then eventually fall into a little bucket at the bottom. If I click a whole bunch of different balls fall, and they all end up inside of one of these different buckets. You'll also notice that every bucket has its own little number or counter on it that designates how many times a ball has fallen into it. One other thing I want to point out right now is that on the bottom right-hand side is a reset button, and if I click that, all the different counters on here get reset as well. All right, so let's talk about what's going on with this example. This is a tiny application that I put together that's in the theme of a very popular game show game called The Price is Right. The game itself that we put together is called Plinko. The Price is Right is a popular game show that runs in the US, United States. And in this game show, you compete for various prizes and sums of money for, whatever it is you're trying to win. Now, there's a bunch of different games. One possible game is the game of Plinko. In the game of Plinko, a contestant walks up to the top of this board, and then they have some number of little pucks or discs that they then drop into the playing board. The disc then falls down, bounces off a bunch of different pegs, and eventually falls into one of those little buckets. And the bucket that it falls into determines how much money a contestant wins. So in this case, this contestant won $1,000 because that is where the little disc fell to. Now, as you might guess, our application is very similar in nature to that Plinko game. So if we click, the disc falls, it bounces off the stuff, and eventually ends up in one of these buckets. Now, we're going to try to model this little game right here using a different algorithm, one or two different algorithms. There's only one little twist here. Rather than saying that if a ball falls into a very particular bucket, we win some amount of money, we're going to alter the rule set just a little bit. So here's what we're going to try to do. We're going to say that given some data about where a ball is dropped from, can we somehow predict which of those buckets that ball is going to end up in? This is our goal. This is the analysis that we're going to try to conduct on our little application. We're going to try to write some amount of code that will say, all right, if we drop the ball from over here, it will fall into maybe bucket 2. But if we drop it from over here, it will fall inside of maybe bucket 8 or 6 or whatever it might be. So that's our goal. That's what we're going to try to do. Let's take a quick pause right here. When we come back to the next section, we'll start to lay out a series of steps that we're going to go through to somehow model this problem and solve it to some degree. So quick break and I'll see you in just a minute. In the last section, we took a look at the game Plinko. Remember, our goal here is to somehow drop a ball at some point on the board and predict which bucket is going to fall into. So in this section, we're going to start walking through the same series of steps that we just walked through a couple of minutes ago. The first thing we need to do is somehow identify the data that is relevant to the problem that we are trying to solve. Now, I think that there's two pieces of data that are probably pretty evident or obvious from the get-go, but there might be one or two others that are a little bit less obvious. So the first thing that is probably very relevant to the problem we're trying to solve is to somehow record where we are dropping this ball at. You'll notice that on the top right-hand side of this little board, I have a drop position counter. That drop position is measuring the number of pixels from the top left-hand side, or the very left-hand side, all the way over to the drop position. So all the way over here at the very far left is 0 pixels. And then as we start to go right, we increment that drop position by 1 for every pixel over that we move. So if I click right here, I am dropping this ball at drop position 555, or essentially 555 pixels over from the left-hand side. And that's probably a very obvious piece of data that we're going to want to record anytime that we drop a ball. The other piece of probably obvious data that we would want to record is which bucket the ball falls into. So did it fall into bucket 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10? Now again, those are probably two obvious pieces of data that we would want to record. But I have a quick question for you. Do you think that there might be any other pieces of data inside this application that we might want to record as well? Other pieces of data that affect where a ball falls or which bucket the ball falls into? Well, if you look really closely underneath this chart, you'll see these two little forms down here. One that says range of ball bounciness, and the other that says range of ball size. So these are two little inputs that will control exactly how bouncy the ball is and how large the ball is as well. The other thing to notice here is that these are ranges of values. So I have a start range of 0.5 and an end of 0.55. That means that my bounciness factor, essentially, for lack of a better term, will be somewhere randomly between 0.5 and 0.55. I can change the start value to something like, say, 1, and then the end value to something like 0.1. Now I have a much less bouncy ball. So if I now click on this chart up here, you'll notice that the ball is really not bouncing at all. And as you might guess, that's probably going to affect exactly it's going to impact exactly which bucket the ball ends up falling into. So in addition to the drop position, I think that the bounciness of the ball is going to be something very relevant to trying to predict which bucket the ball goes into. One other thing I want to show you very quickly is that I could bump up the start to 0.9 and the end to 1. And now we're going to have a very bouncy ball. And so if I drop these now, you'll see that they're bouncing all over the place, and they might end up going very far from where they started. Okay, so now the other one is the range of the ball size. Right now it's fixed at 16 pixels, or essentially 16 pixels wide. I could very easily change this as well, so let's say we have 30 to 30. Now if I drop a ball, it's much larger than it was before. And again, as you might guess, I would probably argue that the ball size is going to affect which bucket it eventually falls into. So in total, I think that we're going to have 3 different features and 1 label. I think that we need to somehow record a drop position, the bounciness of the ball, and the ball size. And I think that any time that we change one of these features, we're going to be somehow affecting or changing which bucket the ball is going to land into. So we're going to have 3 features, and I think we're going to have the single label of which bucket a ball lands in. All right, so let's take a quick pause right here. When we come back to the next section, we're going to start to think about assembling a set of data related to this problem. So quick pause, and I'll see you in just a minute. In the last section, we were able to identify data that was relevant to the problem we were trying to solve. Remember, we had said that we want to somehow record our drop position, our ball bounciness, ball size, and the bucket that a ball lands in. So now it's up to us to somehow assemble a set of data related to the problem that we're trying to solve. So essentially, we want to click around a whole bunch on this diagram and record a bunch of distinct data points. We want to record where we dropped the ball from, how bouncy the ball was at that point in time, the ball size at that point in time, and which bucket it eventually fell into. Now, before we start to worry too much about exactly how we're going to record this information, I want to talk to you a little bit about how we generally store data sets in the world of JavaScript, because again, that's what we're going to be using as our language of choice throughout this entire course. Now, in the world of JavaScript, for maintaining data sets, there's really 2 distinct approaches that we can take. The first is to record all these different ball drops, or all these different observations, as we might call them, inside of a single array. And inside that single array, we might have a single object. And this single object would record information about that single ball drop attempt. So in this case, I have a full array of 4 different records. That means that I dropped a ball 4 different times. The first time, I dropped the ball at position 300. So again, we can use the drop position up here at the top right-hand side. So 300 would be like just about there. And then my ball bounciness was 0.4. My ball size was 16, and it landed in bucket number 4. Now, this is one approach that we can use to record and store data in the world of JavaScript. But we're going to use a slightly different approach, one that ends up being a lot easier to make use of, if a little bit more confusing when you first get used to it. All right, so here's the approach that we're going to use for storing data inside of all of our applications that we're going to be working on throughout this course. We're going to store all of our data inside an array of arrays. So inside of a large outer array, we're going to have a bunch of different inner arrays. And each of these different inner arrays is going to represent one single ball drop. Inside this array, we record the drop position, the bounciness, the ball size, and the bucket. So in other words, the index of every value that is stored inside these inner arrays is very meaningful, even though they're not necessarily labeled as such. In this approach, we kind of have to keep it in our minds, or kind of in our heads, that the first index in each of these inner arrays is the drop position, and then the next one is bounciness, the next one is ball size, and the final one is bucket, or which bucket the ball fell into. So we need to make sure that we stay very, very, very much aware of what the individual indices inside of these inner arrays mean to us. Now, like I said, when you first get started with this approach of storing data, initially it's a little bit challenging, but later on inside this course, when we start making use of some other libraries, you're going to see that there is a very, very good reason that we take this type of approach right here. And it really ultimately makes life a lot more straightforward than it otherwise might be. Okay, so with that in mind, the next thing we have to do is figure out how we can somehow record information from each of these ball dropped attempts. Well, for that, we get to write some code, finally. So it's been a couple of videos into this course. We haven't written any code just yet, so I'm really happy we now get to write a little bit of code. We're going to write a little bit of code into this application that is going to somehow track every single ball drop and record the drop position, the bounciness, the size, and which bucket it falls into. So to get started with this process, we're going to first open up our code editor based upon the project directory that we had just downloaded onto our local machine. And so back inside of my terminal, I'm at that same Plinko directory. This is a folder that we created a couple sections ago. And inside of here is the index.html file, a lib folder, and a score.js file. I'm going to open up my code editor inside this directory. Now notice that I'm running code dot right here. I am able to run this command because I've set up Visual Studio Code to respond to this command inside of my terminal. If you have not done the same, you will not be able to run this command. At any rate, all you need to do at this point is open up your code editor of choice based upon this Plinko directory. Okay, here we go. So again, I'm inside the Plinko folder. I see the lib directory, index.html, and score.js. Let's open up that score.js file. Now inside of here, you're going to see that there are two functions that have already been defined. The first function is called onScoreUpdate. This is a function that I created. I wired up this application for us to use. Anytime that a ball falls into a bucket, onScoreUpdate will be called with the drop position of the ball, its bounciness, its size, and the label of the bucket that it fell into. So is it bucket 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all these different buckets down here. So again, every single time a ball falls into a bucket, this function gets called. You'll also notice there's a second function inside of here called runAnalysis. We're going to add a lot of code to this runAnalysis function eventually. All you need to know right now is that if you click the Analyze button down here, that runAnalysis function will be automatically called. So again, I did just a little bit of pre-setup for us just to get us started. Let's take a quick pause right here. When we come back to the next section, we're going to write some code into onScoreUpdate and make sure that every single time a ball falls into a bucket, we record some information about that ball. So quick pause, and I'll see you in just a minute. In the last section, we opened up our code editor inside the Plinko directory, and we started working on our score.js file. Again, our goal right now is to write a little bit of code inside of onScoreUpdate. We're going to make sure that every single time this function gets called, we store some information about the ball that was dropped and the bucket that it eventually fell into. So let's write a little bit of code to do exactly that. One quick thing I want to remind you about, in order to store all of our data for this application, we're going to make an array, and inside of it are going to be a bunch of other arrays. Each of the inner arrays is going to store information about one single ball drop. So to get started, inside my code editor, I'm going to declare a new data structure outside of that function. At the very top of the file, I'm going to make a function called outputs, like so. See, I said function, I meant to say an array. So I've now got an array called outputs. This array is where we're going to store each of the different observations that we make inside of our application. I'll then delete the comment right here, and then we're going to use a JavaScript built-in function to push in a new array to this outputs array, and inside this second array, we're going to store the drop position, bounciness, size, and bucket label. So I'm going to write out outputs.push. I'm going to stick a new array in there, so this is going to be the array that's going to reflect data about a single drop attempt, and I'll put in drop position as the first index, then the ball's bounciness, then its size, and then its bucket label, like so. Okay, so that's it. That's all we have to do to record in some information about every ball that gets dropped. Now to test this out, I'm going to also add in a little console log underneath that, and I'm going to console log outputs, like so. So now every time that we see a ball touch a bucket, we should see this console log statement, and it should be console logging whatever's inside of the outputs array. Now I'm going to save this file, and then I'll test it by going back over to my browser. I'm going to open up my Chrome Developers Console, like so. You'll notice that I'm on the console tab over here. I'm going to make sure that I refresh this page because we just made a change to its related JavaScript file, and there's no live reload or anything like that set up for this project. And then I'm going to go ahead and just click anywhere on here and let a ball drop. And then when it goes down into a bucket, you'll see that I get this console log over here. So if I expand this, I'll see that I have an array with an array that has 4 entries inside of it. So I can expand that smaller one. And remember the order in which we reflected all of our data here. The first index is its drop position, which in this case was 361. The second index is how bouncy the ball is. Now, remember, we're setting a range down here. Just in case it's not clear, this is the range of possible bounciness values. So that's saying that every ball that we drop will have a distinct bounciness between 0.5 and 0.55. In this case, that randomly determined bounciness was 0.5479, and so on. Next up is the ball size, which was 16, and then we have the bucket that the ball fell into, which is number 4. And of course, we can see over here that, in fact, the ball did fall into bucket number 4. If I now click around a whole bunch more, we'll see some additional console logs, which with each of those additional ball drops. And now we can really see the structure of this data set start to form. So I've got the outer array. Inside there are all of the different ball drops that we've now conducted. So we now very clearly have a pretty solid data set to work with here. Let's take a quick pause here again. And when we come back to the next section, we're going to move on to our next step, which is to decide the type of output that we are predicting. Is this a classification problem or a regression problem? So quick pause, and I'll see you in just a minute. In the last section, we started recording data from every single ball drop that was done inside of our application. Now, a couple of videos ago, I had said, oh yeah, this data collection stuff is sometimes really hard. So it might seem like the code that we just wrote, like, this one-liner right here, is kind of anticlimactic, like that was really easy. Well, to be honest with you, a little bit down the way on this problem that we're working on right now, this project, we're actually going to see that our data set kind of has some rough edges to it, and we're going to have to do some additional work on it before we can actually make use of it. So, truth be told, yeah, the data side of things sometimes gets a little bit hairy, and we are going to see it with this project, even though it looks really straightforward right now. All right, so now on to our next step. We need to decide on the type of output that we are predicting. What type of analysis are we doing here? Is it a regression or a classification? I'm going to argue that this is going to be a problem of type classification. Given a ball drop, we are trying to guess which bucket that ball is going to fall in. And there is a finite or a discrete set of buckets that could fall into. It could fall into bucket 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only in those buckets. There is no in-between bucket, like there is no bucket 2.5 or bucket 6.3 or something like that. A ball can only fall into one of these 10 buckets. Now this might be a little bit surprising because I had previously said that with our classification stuff, we looked at this diagram just a second ago, I had said, oh yeah, classification, it's where we make a binary choice like pass or fail or spam or not spam or score or not score. Well, in reality, a classification doesn't have to be an either or a binary choice. With classification, we can have many different categories. We could have just 2, like say pass or fail. We could have 3, we could have 5, 10, 15, 20, 100. In reality, there's not quite any distinct limit to the number of different categories that we can have when we're doing classification. Even with these different examples that we're looking at right here, we could kind of break these down. At the end of the day, if we really wanted to, we could kind of break these down into subcategories. We could say that a student either passed, or kind of passed, or barely passed, or barely failed, or totally failed. So even though we've got these binary categories here, we could technically expand them a little bit and dive into like subcategories. So again, we're not limited to just 2 decisions. We can have as many as we want within reason. Okay, so again, we're going to be using classification techniques to analyze this data set. Now, the next thing we need to do is to pick an algorithm that's going to work for this type of classification work that we're trying to do. Now, in this case, I've picked out an algorithm for us. So we're just going to say, yep, we're going to use this particular algorithm. We're not going to do any analysis or comparison between different algorithms we could use. We're just going to say, yep, we're going to use this one this time. The reason we're just going to beeline this distinct algorithm is that it's a really great one to just get started with when you're first getting into machine learning, because it's one of the very few algorithms in machine learning that kind of intuitively just makes sense. So let's talk about the algorithm we're going to use. All right, so the name of the algorithm we're going to use to somehow guess which bucket a ball is going to fall into is the k-nearest neighbor algorithm. That's the name of it. You'll frequently see this abbreviated as KNN as well. Now, if I had to apply like a 1-sentence summary or a 1-sentence description to this algorithm, I would say birds of a feather flock together. Now, if you're not a native English speaker, you may have never heard this phrase before. This is a kind of a saying or a phrase in North America, I don't know, maybe Europe as well. The idea behind this phrase right here is to say that if you have a bunch of birds that are sitting together, and you know what those birds are. Like, let's say here's a bunch of birds sitting together, and we know that they are all called nightingales. Like, that is a type of bird, and we know that these are nightingales right here. Then if another bird flies up to it and sits with all the other birds, and it looks real similar, well, chances are this other bird over here is a nightingale as well. So the phrase birds of a feather flock together means to say that if we have a bunch of different things sitting together, they're probably all the same thing. So if I had to apply a kind of a single sentence description to k nearest neighbor, that's what I would say. Now let's take a quick pause right here. We're going to come back to the next section, and we're going to start to walk through the k nearest neighbor algorithm, and then eventually implement it inside of our project over here as well. So quick pause, and I'll see you in just a minute. In the last section, we started talking about the k nearest neighbor algorithm. In this section, we're going to start to do a deep dive on the algorithm and really focus on how this thing internally works. I want to first begin by giving you a little thought experiment, something that's going to help you understand why this algorithm works at all, and why it's actually a pretty good thing to use in the case that we're trying to use it for right now, which is to guess which bucket a ball is going to drop into. So here's our thought experiment to help you understand why this algorithm is going to work really well. I want you to imagine for a second that we put a ball 300 pixels away from the left-hand side, so this is a drop position of 300, and we drop it 10 times right around that spot. Maybe not exactly at 300, but maybe right around 300. So we go right here, we click 10 times, and we record each of the buckets that it falls into. And so we end up with maybe a data set that looks like this. Again, we did not drop the ball exactly at 300, but we dropped it right around it. And then in each of those cases, we recorded which bucket the ball fell into. So maybe at 298, it went into number 4, 299, 4, and kind of goes down the list. I don't have to read these all off to you. In just about every one of these cases, the ball fell into bucket number 4. So now, with these observations in hand, I want to ask you a question. If we dropped a ball at 300 pixels, which bucket do you think it would fall in? Well, this is kind of an easy question. If we dropped the ball at 300 pixels, and that would be kind of like right here on the table, right around 300 pixels, everything else was going into, without a doubt, bucket number 4. So if we dropped it at 300 pixels, I would say very confidently, yes, it's going to go into bucket number 4. That is pretty much exactly what k nearest neighbor is doing for us. It's looking at all these other observations that are very close in nature or have some very close initial inputs or features. It looks at the results for each of those, and it says, okay, if we now have a new observation with a very similar number of right around 300, it's probably going to have the same output as all the others as well. So with that in mind, let's take a look at the inner workings of k nearest neighbor. Now in this diagram right here, we're going to walk through the exact code, more or less, that we're going to write to implement this algorithm. If these steps seem confusing, that's totally fine, because like I said, we are going to implement this algorithm from scratch. So right now, this is just kind of a little taste of what to expect with all the code that we're going to write. Now, one thing I want to mention about this diagram is that our initial implementation of k nearest neighbor is going to have only one independent variable, or one feature. So for this initial walkthrough, we're going to be only working with drop position, and we're going to completely ignore the bounciness and the ball size for our prediction. So for initial implementation, just going to worry about the drop position. So with that in mind, let's get to it. So we're going to first start off by asking a question. We want to make a prediction. If we drop a ball at 300 pixels, which bucket is it going to go into? Here's how we're going to solve that. We're going to first drop a ball a bunch of times around the board, and we're going to record which bucket it goes into. So in other words, we're going to go back over here, and we're going to click all over the place. We're going to drop a bunch of these different balls, and we're going to record which bucket each of those go into. Remember, we already wrote the code to record that data. After that, we're going to take each of those different observations, and we're going to subtract the drop point of each of those observations by 300 pixels. And then we're going to take the absolute value of the result. And as a reminder, the absolute value essentially just turns a negative value into a positive one. It essentially takes the magnitude of a number. Now this step right here might be a little bit confusing, so let's take a look at these first two steps in diagram format. Okay, so step number 1, again, that was to drop a ball around the board a bunch of times. So let's imagine that we dropped the ball a bunch of times at all these different positions, and we recorded the bucket for each of those. Step number 2 is to take those drop positions, subtract 300 from them, and then take the absolute value of the result. So I've now added in a new column right here to represent that second step. So we took our drop position, subtracted 300, and then took the absolute value. As you might guess, this is going to determine how close or how similar each of these other drops were to the data point that we actually care about of 300. You'll notice that a drop position of 0 minus 300 gave us a value of 300. That means to say that if we drop a ball right here at drop position 0, remember that's reflected up here at the top right-hand side. So if we dropped a ball right here, whatever results from that drop is probably going to be a very different result than if we drop it from 300 over here. So the purpose of that second step is to figure out how similar or dissimilar all these other observations are. You'll notice that the 275 and 325 records right here, which are very close to 300, relatively very close, both resulted in values of 25. So these have very low values, which means to us that chances are these buckets right here of 3 and 4 are going to be very close to the result that we care about for the drop position of 300. Now, after doing that a bit of math, we're then going to sort those results from least to greatest. So we're going to sort this table right here based on that new column that we just added in. So once we sort that, we end up with this right here. You'll notice that the 325 and the 275 are at the very top. So the observations that are most similar to the data point that we care about end up at the very top of the table, and the observations that are least similar end up at the very bottom. Now, the second to last step is to look at the top k records. In this case, k is a variable. It's going to be a whole number, a positive integer, that tells us to look at the number of records to look at the top of that list. The k right here is a reference to the actual name of the algorithm, k nearest neighbor. So the k means to say, look at the top 1, or the top 2, top 3, top 4, top 5, however many records, and take the most common result from those top 4, 5, 6, 7, whatever it is, records. So in our case, if we had, say, a k equal to 3, we would look at these top 3 records right here. We would look at the most common result out of those 3. In our case, the most common result is the fourth bucket, because we see number 4 and number 4 right here. So we see number 4 twice, and we see the bucket number 3 only the single time. So we would say that chances are, if we drop the ball at 300 pixels, it would end up in bucket number 4. Now the value k right here is obviously a very important factor. If we had changed k equal to, say, 4 instead, and considered the top 4 records, we would then have bucket number 4 twice, and bucket number 3 twice as well. And so that would put us in a little bit of a bind, and it would be kind of tough for us to figure out, well, we got like a 50% chance for bucket number 4 and 50% for bucket number 3. So that makes life a little bit more challenging. You might think, okay, well, how do we actually pick out a value for k? Well, in reality, there's no magic number of k. There are different metrics we can use to kind of analyze the result after the fact, but there's not necessarily a very strict rule that says, oh yeah, k must always be 4 or 5 or 6 or whatever it might be. We'll take a look at a couple of different strategies over time to kind of optimize the value of k that we pick here by looking at the actual accuracy of our predictions. Okay, so that's pretty much it. That is the k nearest neighbor algorithm in a nutshell. Again, we're going to first take a bunch of data readings. We're going to figure out how far away each of those drops were from the 300 pixels we care about, or whatever the drop position is that we care about. We're then going to do our sorting, look at the top k records, and then find the most common bucket. So let's take a quick pause right here. When we come back to the next section, we're going to start writing out this algorithm from scratch inside of our code editors. In the last section, we walked through the k nearest neighbor algorithm. We're now going to start implementing this thing from scratch, but before we do, I want to do a quick review of a library that you may or may not use before in the JavaScript world. We're going to do a quick review of this library, or maybe just introduce it for the first time, because it's a library that we're going to be using throughout this entire course to do a lot of different operations. We're going to first take a look at the documentation around this library. The library is called Lodash, by the way, and then we'll work through a very quick example just to make sure that you're up to speed with some general ideas behind the library. The Lodash documentation for this library that we're going to be used, can be accessed at lodash.com/docs. So I'll navigate there right now. Now this is a utility JavaScript library. whether you are using JavaScript on Node.js or you're writing React code or Angular, whatever it might be, Lodash is almost always a very useful library to have around. It has a lot of different methods built into it for working very efficiently with arrays of data or objects or just about anything you can possibly imagine in the world of JavaScript. Like I said, we're going to be using this library quite a bit throughout this course, so I just want to go through one or two very quick examples with you. Now, to actually walk through these examples, we're going to use a little tool that I put together. This tool is a coding tool of sorts that allows you to enter in a little bit of code and then very quickly see the output from that code. So you could do this inside of your code editor, but it's going to make life a little bit more challenging to run it. So let's check out this tool very quickly. One thing I want you to know about this link right here is that these JSP letters right there are case sensitive. So when you try to visit this link, make sure you put in capital J, S, and P. All right, so I'll open that page. On the left-hand side is a little code editor, and we can write in some amount of code here, and then reference that variable, and it'll be automatically printed up on the right-hand side. I could then write in some number of expressions, like say divide that number, or multiply it by itself. And the result of each of these different statements will be reflected automatically on the right-hand side. I can then change the original number, and you can see that the output over here on the right-hand side changes as well. So again, this is just a nice little tool to very quickly write a little bit of code and see the output over here. And so in reality, it makes it a very nice tool to use with Lodash because you can test out all these different methods and get an idea of how they work. Now, like I said, I want to very quickly go through one or two quick examples with Lodash. If you've already used Lodash before and you feel pretty confident in how it works, you could of course skip the rest of this section and move on to the next one if you want to. Otherwise, let's go through a quick example. All right, so in this tool, I'm going to put together a little array of arrays with a structure very similar to the data structure that we're going to be working with for all of our data inside all of our data sets in this course. So it's going to be an array of arrays where the inner arrays contain maybe some different numbers that represent some data. And I'll just enter in a couple of dummy values in here, and we'll work around with it just a little bit. Okay, so we can imagine that maybe this is an array of arrays where each inner array or each row represents some observation about some natural event or something that we want to analyze in some way. Now I want to very quickly show you just two very important methods to understand about Lodash as we start going into our k-nearest neighbor algorithm. The first method from the Lodash library that I want you to understand is the sort by method. So if you want to, you could go back over to lodash.com and look up sort by and look at the documentation for it if you want to. But of course, I'll show you an example here very quickly. So with sort by, we can reference Lodash as the underscore. The underscore is a valid JavaScript variable name, so there's nothing special about it being called underscore. It's just what Lodash colloquially is known as. We'll then reference the sort by method and then pass in our array of numbers. Now, as you might guess, this sort by method is used to sort an array. Sort by is very special because we can pass in a second argument as a function, and that function will be called with every element in this array. So in this case, it'll be called first with this array, then this one, and this one. The purpose of this second argument, or this function, is to allow or to give the sort by method some criteria to use to sort all the elements in this outer array right here. So in our case, maybe we want to sort this array by the second index in here. So if we sort it by the second index, I would expect to see from least to greatest. So the first entry should be -5, then 1, then 2, then 5. So let's try writing in a function that will provide the second element in each of these arrays to use as a sorting variable. So I'll put in a little function here that will be called with each individual row. And then I will return row at 1, like so. So that's telling sort by that we want to sort the numbers array using the second element in each of these little arrays as our sorting criteria. And you can see over here that we got our correctly sorted array from least to greatest. We have -5, 1, 2, and then 5. Now, one thing that you might be interested in is a little refactor to this sort by function right here. You'll notice I'm using the classic ES5 anonymous function syntax. I could very easily shorten this syntax to use an arrow function instead. So to do so, I would remove the function keyword, I would put an arrow on the other side, remove the parentheses around row, remove that curly brace and the curly brace down below, and then remove the return keyword and a semicolon at the very end. And so I end up with just that like so. And that is completely identical to the code that you saw just a moment ago. Okay, so that's simple enough. Now I want to take that sorted array, and I'm going to save it to a variable that I'm going to call sorted. Now I want to show you one other very quick Lodash function, and then you'll see why I'm really walking through this example here, because there's one very critical example that I want you to see at the very end. So I now want to try to map over all these records, or this sorted list of records right here. And I want to extract just the second index, or the second element, from all these inner arrays. So to do so, I'm going to map over the output of sorted right there. And then I'm going to again provide a function that will be called with every individual row inside the numbers list. And this time around, I'm going to return the second element like so. So now I've written a map function that's going to extract just the second element from each one of these inner arrays. And I end up with -5, 1, 2, and 5 like so. Now maybe I would assign that to a new variable that I'll call mapped like so. Now I want to pivot just a little bit now, and I want to tell you about a very important feature of Lodash that we're going to use quite a bit as we start going into this k-nearest neighbor algorithm. One thing that you'll start to notice with this pattern right here is that we've kind of got like a variable name, and then dot some function, and then we pass in the result of whatever we called the previous variable. So notice how we had numbers, passed in numbers and called that sorted, and then sorted went into map, got assigned to mapped, and then maybe if we wanted to add in more functions down below, we would take mapped and add it into the next function. So this is a lot of very repetitive code. Lodash has a built-in function to help us very easily clean all this stuff up. So I want to very quickly show it to you. This is the really important part of this section. If you go back over to the Lodash documentation, you can look up another method called chain. Chain allows us to very quickly chain on, so to speak, multiple different Lodash functions. And so we can use it to write some very clean and concise looking code. Let's take a look at a very quick example. To use chain, we'll call _.chain, and then we'll pass in our original numbers array. And now onto this call, we can chain on as many different Lodash functions as we want to. So for example, I could now call sort by, like so. When we start to use chain, the key thing is that we don't have to manually pass in these arrays to every additional function that we want to add in. When we use chain, our numbers array is kind of implicitly passed as the first argument to sort by for us. So all we have to do is pass in whatever we had used as the second argument previously as the first argument this time around. So I'll put in row is row at 1. And then to then map over that array and extract that second column in there, I could then chain on a .map and say again row at 1 like so. And then when I'm all done with my chain of all these different methods, I can then finally put on a .value like so. The .value is going to stop the chain and eventually return the value or the end result of all this computation. And so you can see over here, we still have our -5, 1, 2, and 5, just as we did before. Okay, so I know that this whole Lodash thing was a little bit of a diversion, but again, it's something that we're going to be using quite a bit throughout this course, mostly for manipulating all of our different data sets. So let's take a quick pause right here. When we come back to the next section, we're going to use this chain functionality to put together our k-nearest neighbor algorithm in a surprisingly concise little bit of code. So quick pause and I'll see you in just a minute. In the last section, we got a quick review of the Lodash library. The most important part of that section was understanding how this chain function works. It essentially allows us to call a variety of different Lodash methods on a single value, and essentially perform a calculation pipeline of sorts. We're going to use this chain method as the key to very concisely solving this k-nearest neighbor algorithm. And like I said, we're going to be using Lodash throughout this course to help us do a large variety of different calculations. So with all that in mind, let's now delete all this code. And we're going to write out our k-nearest neighbor algorithm directly inside this editor so we can see some very quick output over here. As soon as we finish up this initial implementation, we're then going to move it over to our code editor for the actual Plinko project. All right, so let's get to it. The first thing I'm going to do is put together a little bit of fake dummy data up here that we can work around with. So I'm going to make an array up here at the top called outputs. I'm calling it outputs because remember, that's what we had called our outputs array over here inside of our real project. And then inside of here, I'll put a couple of fake data records. Remember that the ball dropping, or the kind of the ball data recording that we're doing, has the drop position, and then the ball bounciness, then the ball size, and then the bucket that it fell into. So I'm going to do 3 other entries here. We'll say a 200 pixel drop position, 0.5, 16, we'll say bucket 4, maybe 350, 0.5, 16, and 4. And then we'll do one more 600 pixels, 0.5, 16, and 5, like so. All right, so if this structure right here looks kind of strange, remember all we're doing there is using that same style of array of arrays for storing our data that we had mentioned previously. So each of those different inner arrays represents a different ball drop. First element is position, last one is our bucket. Okay, so let's now start to write out all the different steps for solving our k-nearest neighbor algorithm. Now I took every stage along this diagram right here that we just went over, and I kind of put it together in diagram format so that we can really understand the different Lodash functions that we're going to make use of. So the first step of k-nearest neighbor is to say that for each observation, we want to subtract our drop point value from 300 pixels and then take the absolute value of that. So in other words, we're going to take our data array, which you'll see I replicated right here, and we're going to pass it into Lodash's map function. And then the end result of that is going to be an array of arrays with just our distance as the first element in there, and then the bucket that it fell into as the second element. You'll notice that I completely dropped off the ball bounciness and the ball size because, as we had said previously, right now we're just concerned about doing this analysis with one variable, and we're not going to consider the bounciness or the ball size just yet. Okay, so back inside of my editor over here, I'm going to start off my .chain, and I'll pass in outputs. I'll then map over that, and for every row inside of here, I want to return another array that has first the distance to 300 pixels as the first element, and then the bucket as the second element. Now, if I just put all the code for getting that distance directly into this map function right here, it might look just a little bit dirty. So I've got a good idea. Let's make a separate little helper function called distance. And this will return the distance from some point to whatever our prediction point is, which for us is like 300 pixels. So I'll say math.abs is going to be our point minus the prediction point. And then I'm also going to make a new temporary variable up here called prediction point, and I'll set it equal to 300 pixels like so. All right, so now the first stage of our map function right here, I'm going to return an array. The first element is going to be our distance function that takes our row at 0, and the second element will be our row at 3, like so. Now it looks like I made a little typo somewhere in here. Where did I do that? Distance row, oh, excuse me, right there. There we go. All right, so I know that this step, or that we just went through, looks a little bit confusing, but if you walk through it step by step, I think that you'll get a really good idea of what's going on. So all we did here was we set up our chain, we called map on our outputs, and we tried to get out the distance for that first element in there to 300 pixels, and the second element is our bucket number. So the output of this step right here is what you see up here on the top right-hand side. And if I look back at my diagram, it definitely looks like what I expected. First element is the distance to 300 pixels, and the second is the bucket that the ball landed in. Okay, so now that we got that done, let's move on to our next step. So the next step is to sort our results from least to greatest, using the first element inside of each of those inner arrays. And so you'll recall that in the last section, we just spoke about that sort by method. So we can use sort by, that's a part of Lodash, to very quickly sort this entire array of arrays from least to greatest. So back over in my code editor, underneath the map, I'll chain on a sort by, and I'll say that the sorting criteria that I want to use is the 0 entry in my row array. So now I can see that everything is correctly sorted. I have 50, 100, 290, and 300. Now the next step is to look at the top k records. Remember, k is a positive integer. So it's going to be the number of top records that we want to consider for saying, okay, well, this new prediction that we're trying to make is going to be very similar to these top k records. To pull out these top k records, we're going to use the _slice method. Slice just takes some number of elements out of an array and returns just those elements. So let's add on the slice right now as well. So I'll add on a .slice, and I want to take everything from the first record up to, how about like the first 3 records, like so. Now you'll notice I hard-coded 3 right here, but k is supposed to be a variable. So just to make sure that this is easy to change in the future, I'm going to create a new variable up here and call it k, and then reference that down there. So now if I ever want to change the number of records that I'm considering for my prediction, I could very easily just change k right here, as opposed to finding it inside of my chain. Now you'll notice that we only have 3 entries at this point in time. So these are the 3 most similar records to the point that we're trying to predict of the 300 pixel point. Now this section is getting a little bit long, so let's take a quick pause right here and continue in the next section. In the last section, we started working on our k nearest neighbor algorithm, and we just have a couple more steps, so let's keep at it. We've now done our slice to consider only the top k records. The next thing we have to do is look at those top k records and figure out what the most common output, or the most common label, actually was. Now in this case, you and I can look at this output right here and say, clearly 4 is the most common. But actually writing some code to tell the computer how to actually read that can be just a little bit challenging. So believe it or not, we still have to go through a couple other steps to count up the number of 4s, or the number of buckets that we see inside of here, and return the largest value. The first in this process of figuring out which bucket has the most common occurrence, or the most greatest frequency, we're going to use the countBy helper method from Lodash. CountBy is used to count up the number of records that match some given criteria. So in our case, we want to count by and somehow group together all the second elements inside of these inner arrays right here. So we're going to pass this thing to countBy, and then we're going to get back an object that has a couple of different key value pairs. The keys of this object are going to be the values, or the unique values, that are seen inside of this array. And so in this case, our unique values in the second index, or the second position here, are 4 and 1. Then the values, so the other side, is the number of times that each of those values, or each of those unique elements over here, occurred. So in this case, the element 4, or the number 4, showed up 2 times, because here it is right here, and here it is right here. And then the element 1 showed up 1 time. So the result of countBy is going to be an object with 4, 2, and 1, 1. Let's add in this step right now, and we'll figure out how to go from there. Okay, so over here, we're going to add on our .countBy, and we need to give this thing some criteria of how it's going to somehow count up all the different records here. And so the criteria is going to be the second element in each of these inner arrays. So I'll put in row at 1, like so. And now you can see there's that object. So the key is the value that was seen in the original array, and then the value is the number of times that it occurred. And so we also saw 4 2 times. Now once again, you and I can look at this object, and it's very easy for you and I to say, oh yeah, 4 is the most common occurrence. So clearly this ball, if we drop it from position 300, is going to drop into bucket 4. Once again, actually writing out some code to tell the computer to find that 4 and return it is just a little bit challenging. So just a couple more steps. So the next thing we're going to do is call another method called toPairs. toPairs is going to take that object, and it's going to take each of those key value pairs and return them as an array of arrays, just as we had previously. So we're now going to have an array that says 4, bucket 4 occurred 2 times, and bucket 1 occurred 1 time. So let's do that right now. I'll add on toPairs. Okay, there we go. Bucket 1 occurred 1 time, and bucket 4 occurred 2 times. Now the next thing we're going to do is another sort by. So we're going to sort from least to greatest using the second element as our sorting criteria again. So So that means that the bucket that was used most commonly or showed up most frequently is going to end up at the very end of this array. So I'll do another sort by. I'll get my row, and I'll return that second element inside there again. So now I see that bucket 4, which occurred 2 times, is at the very end of this sorted array. So all I need to do now is get the last element inside of this overall array. To get that last element, I'll use a very appropriately named method called last. So last is going to return the last element in this big outer array, which in this case is going to be 4 and 2. So then I'll do my dot last. So now I get just 4 and 2. And then I'll do kind of the opposite of the dot last. I can call dot first, and I get the first element out of that inner array. So now I know that the most common bucket that's closest to other observations for 300 pixels is bucket number 4. There's just one last little thing to take care of here. You'll notice that when we print this out, it has the quotes around it. So this is just a little technicality, but when we use that count by step to put all of our records into that object, technically those keys were turned into strings. Now in our case, bucket 4 really needs to be like the number 4 and not string 4. So to get a number out of this right here, I'm going to add on just one last step, a parse int, like so. And that returns truly the number 4. So then the very last thing is add on a value, which terminates our entire chain. All right, so that's it. That is k-nearest neighbor algorithm, put together more or less from scratch using the Lodash library. I know that going through this process probably seemed really confusing. I know I added in a lot of kind of confusing steps here, but this is probably one of the most concise implementations of k-nearest neighbor that you're going to see just about anywhere around. So it's a very concise implementation that is generally pretty easy to follow if you understand how Lodash works. All right, so let's take a quick pause right here. When we come back to the next section, we're going to take this implementation and move it over to our code editor and run it inside of our Plinko project. So quick break, and I'll see you in just a minute. In the last section, we finished up our k-nearest neighbor algorithm inside this little code editor over here. So we're now going to take all this code and move it over to our code editor for the Plinko project and run it for the real data set. So we're going to do this in a couple different steps. The first thing I'm going to do is pull over that distance function. We're going to eventually modify this distance function to make sure that our k-nearest neighbor algorithm works for multiple variables as well. So I'm going to cut this thing, and I'll go back over here, and I'm going to paste it underneath run analysis. Next up, I'm going to take the entire chain right here. I'm going to cut all of that and move it back into my run analysis function over here. And then I'll do a little bit of indentation just to clean it up like so. And then finally, the last thing we have to do is define our prediction point and our k value as well. So I'm going to cut both of those, and I'm going to paste them in at the very top of this file as well. Okay, so that's pretty much it. Now, last thing we need to do is to make sure that we take whatever the nearest bucket is for the point we're trying to predict and actually print it out once we run this analysis. So I'm going to assign the results of this entire chain to a variable that I'll call simply bucket. I think that's reasonable. And then at the very end down here, I'll console log bucket. And how about we put in a little bit of reporting information here as well? We'll say something like, your point will probably fall into bucket, like so. Okay, so that looks pretty good. Now, the last thing we have to do is flip back over to our browser and test this. And you know what? One last quick thing we're going to fix here. Remember on score update, we put in that console log. I don't think we really need that thing anymore, so I'm just going to delete that very quickly like so. Okay, so now we'll flip back over to our browser. I'm going to go back over to our Plinko project, and I'm going to refresh the browser page. So now we need to first make sure that we drop a bunch of different balls in different places all around the board and record all that data. We already wired that stuff up with our onScoreUpdate function right here. So all we have to do is get our Plinko board to drop a ton of balls and then record those data points, and then we can run our analysis by clicking on that Analyze button down here. And you might notice that there's a couple of tools on here on the right-hand side that can be used to very quickly get a bunch of data put together. So you can use this drop a bunch at various spots right here, this little section right here, to very quickly drop a ton of different balls all over the place. You'll notice that the default inputs are 10 and 200, so that's going to drop 10 balls every 200 pixels along the top edge. Let's try clicking on drop right now and seeing what happens. Okay, there we go. So that is 10 balls every 200 pixels. Now, of course, we want to get a whole bunch of data. So let's try updating these values a little bit. Let's say that we want to drop 10 balls, how about every 10 pixels? So that's going to be dramatically more all falling at once. So now click drop, and you notice that your browser might lag just a little bit, and they all fall down there. Maybe I'll do like 1 or 2 more quick, just to get a really robust sample size. Okay, so that looks good. So now last thing we have to do is click on Analyze down here. That's going to run our k-nearest neighbor algorithm and print out the bucket that we are most likely to have a ball fall into if we drop it at exactly 300 pixels. So I'll click on Analyze, and it tells me that dropping our ball at 0.300 is probably going to fall into bucket number 5 right there. So now the last thing to do is actually test out this assumption. So I'm going to click on Reset down here to reset all the bucket counts. And then I'm going to drop a bunch of balls at a single spot. So I'm going to drop 100 at exactly 0.300. And hopefully, we're going to cross our fingers, hopefully we're going to see that most of them are going to fall into bucket number 5. All right, so I'll click on drop. And they all come out. And lo and behold, it looks like, well, 11 got in there, but there was certainly far more that got into bucket number 4, and even more that got into bucket number 3 and bucket number 2. Let's try repeating this 1 or 2 more times and seeing what happens. So it looks like it kind of caught up there, but still, bucket 4 clearly has a greater representation than what we got for reality on 0.300. So let's take a quick pause right here and discuss some of these findings. In the last section, we finally tried to test out our k-nearest neighbor algorithm. However, we saw that the results were not that great. So our analysis predicted that we would see a ball dropped at 0.300, like right around right there, to fall into bucket number 5. But when we use this little tool right here to drop 100 different balls at exactly position 300, we very clearly saw that bucket number 5 wasn't really the winner whatsoever. So in this section, we're going to discuss a couple of different strategies to kind of vet these results and then try to improve our algorithm to some degree. Now, the first thing I want you to understand is that whenever you implement these algorithms the first time around, very, very commonly, you're not going to see the results that you expect. And so almost always, you'll do some initial implementation and then have to go back to the drawing board and figure out exactly why things did not quite work out the way you expected. So first thing that we're going to do is think about adjusting the parameters of our analysis. You might recall that back inside of our score.js file, we had set k equal to 3 right there. So that meant that we only wanted to consider the closest 3 points when attempting to guess which bucket a ball was going to fall into at 0.300. Now, as I said earlier, the use of 3 right here was kind of a little bit arbitrary. So we could very easily start to massage this number and see if we could come out with some greater accuracy than what we got already. The next thing that we could possibly do is add in more features to explain our analysis. Remember, at this point in time, we have only implemented k-nearest neighbor in order to explain one independent variable. So in other words, only the point or the distance away from the left-hand side of the board, like over here, is attempting to be used to explain which bucket a ball will fall into. It might be the case that the actual bounciness of a ball, which remember is a random number right now between 0.5 and 0.55, or the size of the ball has some effect on where the bucket falls. So we could also attempt to expand our algorithm to account for multiple different features inside of our simulation. The other thing that we might try doing is to change our prediction point from 300 pixels. Maybe there's something just a little bit off about that 300 pixel point, and maybe if we tried a different point, like let's say 450, like over here, or if we tried 600 over here, maybe we would have a result that has a little bit more accuracy to it, and that would give us at least a little bit of confidence in our algorithm. The last thing that we might do is at some point in time, kind of accept that maybe there's just not a good correlation between the drop position of our ball and which bucket it falls into. Now, in this case, I'd say that chances are that the drop position does have an effect on where a ball is going to land. Clearly if I drop a ball over here, it's probably going to land in one of these buckets, and if I drop it over here, it's going to land somewhere over here. So I think that without a doubt, the drop position does have an effect on our output. But for other analyses that we might do, maybe that's not always the case. Maybe we need to go back to the drawing board and really investigate how we are collecting data and try to do a little bit of work to get some better correlation between our recorded data and our predictions. All right, so the first thing you and I are going to do in order to analyze this stuff is attempt to adjust the parameters of our analysis. So we're going to do that by changing the value of k right here. Now, as you might guess, manually changing k a whole bunch and saying like, k equals 2 and 3 and 4 and 5, and manually rerunning our application for each of those attempts would get really old very quickly. So instead, we're going to write a lot of additional code into this file that's going to automatically try out different values of k and then print out some accuracy percentage or some analysis to tell us exactly how correct or how not correct any particular value of k might be. And so by doing this additional analysis, maybe we could come to some determination of what the best value of k might be. So let's take a quick pause right now. When we come back to the next section, we'll start working on doing some additional analysis on what the ideal value of k might be. In the last section, we spoke about some ways in which we might be able to increase the accuracy of our k-nearest neighbor algorithm. Now, before we try to implement any of these changes right here, there's one quick thing I want to mention. At present, in order to gauge the accuracy of our algorithm, we have to flip back over to this little tool. We have to drop a whole bunch of these balls to get some data points, and then we can finally click Analyze and get some console log over here that tells us some result. So that is definitely kind of a laborious process to go through to evaluate whether or not making any of these changes is actually worth it. And so before we try to tackle any of these changes right here, we have to first have some way of comparing accuracy, some like rock solid, concrete, apples to apples way of comparing the accuracy of our algorithm given changes to any of these different inputs. So before we make any of these changes right here, we need to first invest a little bit of time to get some better method of recording exactly how accurate our algorithm is. Not only for some single data point, like some single ball drop at 300, we need to have some way to compare many different positions and say that if we change the value of k from, let's say, 3 to maybe 5, that is going to increase the accuracy of our algorithm for any possible drop in here, and not just dropping the ball at exactly 300 pixels. So let's talk about how we would do that. How can we somehow record the accuracy of our model, or get some accuracy of our model, over many different positions? Well, here's one way to do it. So we're going to record a bunch of different data points. So we're going to essentially use that little feature to drop a lot of balls at the same time all over the place like so. Once we get a whole bunch of data, we're then going to split all of our data into two separate pools. We're going to call one set our training set of data. So that might be this set of data over here. And then the other piece might be our test set. And this is going to be this other piece over here. Then, for every single record inside of test, we're going to run our k-nearest neighbor algorithm using our training data. So in other words, we're going to take off this first record right here. This first record has a drop position of 10, and the ball fell into bucket number 1. So we're going to run our KNN algorithm using this training data, and we're going to try to predict the bucket for a drop of position 10. If we then get a result of bucket 1, we would say that, okay, that's good. That is a positive result. Our algorithm was accurate. If we do not predict bucket number 1, then we'll say, nope, totally wrong. We might be able to improve this a little bit. We'll then throw away that record, and we'll go on to the next piece of test data right here. So we'll then run KNN again for a drop position of 137, and we'll see if it predicts bucket number 2. We then throw that record away. We move on to the next one, run it again for 323, and try to predict bucket 2, and then repeat the entire process over and over again until we eventually exhaust all of our test data. So the idea here is that we've got this pool of data where we know exactly what bucket the ball went into given some drop position. And so we can very quickly have some set of data that we can test over and say pretty confidently that if we make a change in k, or if we introduce some new feature to our data set, or we change anything else there might be as inputs into our algorithm, we'll very quickly know that this is an improvement for all the different variables inside of our algorithm and not just like some single data point at just that 300 pixel part. So that's the idea. That's what we're going to do. We're going to split into training and test. We'll then run our algorithm many times and try to summarize and report those results and print out some total accuracy. So let's take a quick pause right here, and we'll start writing the code for that in the next section. In the last section, we spoke about how we can create two separate data sets, a training set and a test set, to more efficiently gauge exactly how accurate our algorithm is. So let's now flip back over to our code editor, and we're going to put together a little function that's going to split up our data set into these two separate groups. I'm going to go down to the very bottom of this file, where I'm going to create a new function called split data set. And I'm going to call this thing with some existing data set. Let's just call it data. And then I'm also going to pass in a number that's going to be the number of records that we want to have inside of our test set. So I'll call that test count, like so. So test count is going to indicate how many records we want to take out of our data set and put into the test set over here. And then presumably all the remaining records, however many other we have, will remain inside of our training set. Now, one thing that's really important to think about when we start splitting up our data in this fashion is to make sure that we might want to shuffle our data before we split it in any way. Let me lay out a possible scenario here. Let's imagine for a second that instead of using this feature over here to collect some initial data of automatically dropping a bunch of balls, let's imagine that you and I manually click around this canvas. So maybe we start off here on the left-hand side and we click a whole bunch. And we keep clicking, and we go over to the right-hand side and eventually get to the end. And that's it. That is our set of observations. Now think about it for a second. If we take this data set and just evenly split it into two, then we're going to have some amount of data that includes observations only from this half of the chart. And the other data set, or the other half, is only going to have data from this side of the chart. And as you might guess, if we tried to predict one side of where a ball is going to fall into using observations from the other side, we're probably going to get some ridiculous and very inaccurate results. So usually, before we split our data set into a test set and training set, we will shuffle our data. So I'm going to do that as the very first thing inside my function over here. I'm going to say const shuffled is _.shuffle data, like so. So that's going to take our data set, shuffle it up entirely, and now we can freely split it as much as we please, and we'll be somewhat confident that we're getting a very randomized set of data that will hopefully include data from both sides of this chart, even if we went from left to right and got all of our observations. Okay, so now the next thing we're going to do is split our data set into two and return it. So to get my test set, I'm going to use the slice, there we go, function again. I'll pass in shuffled, and I'm going to get records all the way from 0 up to test count. And then I'll also get my training set, and that will be slice shuffled, everything from test count on. So notice how in the second line right here, we didn't put in a 0. So essentially this first line right here is going to take everything from 0 up to index of test count, and then the second line will take everything from test count to the very end of the array. And then finally at the very bottom, I'm going to return an array that contains the test set and the training set, like so. Cool, so now we can use this function to get some training set of data and some test set. Let's take another quick pause right here. When we come back in the next section, we're going to modify our run analysis function to make sure that it's going to use all the records from our test set to make predictions. So quick pause and I'll see you in just a minute. Now that we have a function to split our data set into two, we're going to start to modify our run analysis function. We're going to run our KNN algorithm many different times for every record inside of our test set. We'll then see exactly how accurate the algorithm was and eventually print out some report that says, hey, it looks like, yeah, we are at some amount of accuracy, like, I don't know, 25 or 65 or 80%, whatever it is. Now, the first thing I'm going to do is take this entire chain statement right here, and I'm going to move it into a helper function. Remember, the run analysis function gets called anytime that we press that analyze button on our app back over here. And so it's kind of like the central brains for our entire application. So I don't really want to use run analysis for running our KNN algorithm directly. Instead, I'm going to put it into a helper function so we can more easily call it and pass in some customized arguments. So I'm going to make another function underneath the run analysis one, and I'll call this simply KNN, like so. I'll then take this entire chain right here. I'm not going to take the const bucket. I'll cut it, and then I'll move it into the KNN function. And then I'll make sure that I return this thing. Now, two quick things to keep in mind here. First off, the KNN algorithm as it stands right now is always going to run over the outputs array, which is our entire data set. We're now saying that we want to compare some given record against only our, back over here, training set of data. That's going to be our data source for the algorithm. And then we're going to try to predict records inside the test set one at a time. So to make sure that we're using our training data and not the entire data set, I'm going to say that we're going to get an argument to the KNN function that we'll call simply, how about data set? Or now let's go with data. And then we'll use that as the input to our chain right here. So now anytime that we pass in KNN, we have to pass in some data that it's going to use as part of its algorithm. Now the second thing I want you to remember is that we want to make sure that we run that algorithm with a different test point every single time. But right now, our distance function is hard-coded to use that prediction point of 300 at the very top. So we probably don't want to fix that number at 300 anymore. So I'm going to delete that variable. And we're going to say that when we call our distance function, remember we put that together as a function, we're going to pass in the data point that we want to make our prediction for. And that's going to be the first number out of our test example that we're currently running the algorithm for. So in this case, like, 10. And then 137, 323, and so on. So to make sure that we are able to customize that point on the fly, we'll say that the KNN function will also get some point argument. And we're going to take that point argument and pass it through to our distance function like so. So now we need to make sure that our distance function is going to take the second argument as opposed to the hard-coded variable that we had at the top previously. So down inside of distance, looks like I had already called that initial argument point. So let's change this to be like point A and point B. And then we'll get the distance between point A and point B, like so. Okay, so that's a lot better. Now we've got a fully generalized KNN function that takes some data set and the point that we're trying to make a prediction for. Let's take another pause right here. When we come back to the next section, we're going to start to test out this KNN function and make sure that we can actually gather some accuracy data together. It's a quick pause, and I'll see you in just a minute. In the last section, we fully generalized our KNN function. So we have to pass in our data set and the point that we're trying to make our prediction for every single time we call it. Now, the very last thing we need to do is clean up our run analysis function. I'm going to remove the console log in there. Inside this function, we now need to make sure that we split our data set into the test set and training set, and then we'll iterate through all the records in our test set and try to make a prediction for them using the KNN algorithm using the data from the training set. I know that these two variable names right here seem really similar, and I know training and test can get a little bit confusing, but I think that as soon as we write some code for this, it'll make a little bit more sense. So up inside of my run analysis function, the first thing I need to do is call that split data set function. I'm going to pass in my outputs array, and I need to specify the number of records that I want to have inside of my test set of data. Remember, we had that test count variable right here. So to start, let's say that we'll try to make predictions for 10 random separate points. Now when I call split data set, it's going to return an array that has the test set as the first record and the training set as the second record. We need to get these two variables out of this array when we call the function. So to do so, I'm going to use a little bit of ES 2015 destructuring syntax. So I'll say test set and training set like so. Now, if this syntax right here seems a little bit surprising, all it's doing is saying, okay, split data set is going to return an array with two elements inside of it. So we're going to take the first element and assign it to test set. We'll take the second element and assign it to training set. So now that we've got these two sets of data, we're going to iterate over everything inside of test set and use the training set and our knn function to make a prediction. For this first iteration, we'll do a simple for loop just to keep things very, very clear, but once we get this working, we'll very quickly come back and refactor it just a little bit to make sure that we use something a little bit more modern, like a for each statement. So let's do a for loop for right now. So I'll do let I equals 0, I less than test set dot length, I plus plus. I'll then call knn and pass in my training set. And then I need to make sure that I pass in the drop point, which is going to be that record, or each individual record in turn, from the test set that we're currently working on. So I'll look at test set at I. Now test set at I is going to give us the entire record. So test set at I essentially reaches into the test set and pulls out this single observation array. So I now need to get out the actual drop position. That would be at index of 0. So I'll do test set at I at 0 like so. So once I call this, I'm going to get back a bucket. That is the prediction for whatever that particular drop position was. For right now, let's just do a console log of that bucket just so we can make sure that we don't have any typos here and make sure that everything is working okay. Once we run this once successfully, we'll then come back and add in a little bit better reporting to get a better idea of our current accuracy. Okay, so let's go test this. I'm going to make sure that I save this file, and then I'll flip back over to my board. I'll refresh the page. The first thing I need to do is drop a bunch of different balls to get some initial test data. So I'll drop 10 every 10 pixels. I'll wait for those to go all the way down, and then I'll run my analysis. So it looks like for those 10 randomly picked entries, we picked bucket 5, 9, 4, 7, 3, 9, 4, 8, 9, 4. Now we need to make sure that we take those different predictions and we compare it against whatever bucket it actually fell into. Remember, test set at I is a full-on prediction. It contains all these values, and the very last value in there is the bucket that it actually fell into. Let's make a very quick change to that console log right here. In addition to logging out the bucket, we can also log out the test set at I, and then we'll print out the third element in there, which is the actual bucket that the ball fell into. Now let's save this and run it again, and now we'll be able to do a little bit of a visual comparison and see if we're at all accurate at all. Okay, so I'll flip back over. I'm going to refresh the page again. I'm going to again drop 10 every 10 pixels to get an initial data set. And then I'll run my analysis. Okay, so it looks like we predicted 3, but it was actually 5. We predicted 10, and it was 10. We predicted 5, and it was 5, 7, 7. So it looks like in some cases we're doing okay, but some of the other values down here are not doing quite so well. So now the very last thing that we need to do is somehow consolidate all these metrics right here into a single accuracy reading, like maybe a percentage or something like that, to say that we are accurate 25 or 35 or 55, whatever it is, % of the time. So let's take a quick pause. When we come back to the next section, we're going to consolidate this thing into a little metric that we can very easily read. We now have the ability to run many different predictions at a time by splitting off a separate test set of data. The last thing we have to do is tabulate all these results right here into a single number and say that we are right like maybe 40% of the time or whatever it might be. So back inside my code editor, I'm going to remove that console log we just put together, and above my for loop, I'll put together a little counter variable of sorts. I'm going to start this thing off as, how about a variable that we'll call number correct, and we'll start it off as 0. So now every single time that we get a prediction correct, we're going to increment this thing by 1. And then after we run the entire for loop, we'll print out some message that says, hey, we're correct this number of times. So after our const bucket right here, we'll add in an if statement to see if we were correct. So I'll do bucket equal to test set at I at 3. And if those two are the same, I will increment number correct like so. Then finally, outside the for loop, right after it, we'll add in a big console log that says something like accuracy, and our accuracy can be computed as the number that we got correct out of the number of records that we put into our training set originally. So we can do something like number correct divided by, in this case, we hard-coded the number of records that went into there as 10. That's probably not the best. So let's pull that out to a separate variable. We'll say something like test set size. And then I'll pass that in here. And then I can also reference that down here as well. Cool. Okay, let's save this and we'll run a test inside of our browser one last time. So I'll refresh the page. I'll again drop 10 every 10. And then we'll run our analysis. So it looks like right now we are correct about 40% of the time. Now that's definitely not super awe-inspiring. 40%, maybe not the best thing. But if you reset everything, I want you to notice how if I change the number that I dropped on a single click to like 100 and then drop it, notice how my results get spread over like 5 or 6 different buckets. In general, our accuracy of a random guess, like if you just guessed a completely random bucket for any given ball drop, you would have a 10% chance of guessing correctly because there are 10 buckets here. So technically, an accuracy of 40% is definitely better than the baseline of 10%. It's not great, but it's definitely better than bad. And maybe it's something that we can improve over time. We'll have to see. Okay, so this looks pretty good. We've now got some code put together where we can gauge the overall accuracy of our algorithm. So now the very last thing we need to do to put this new accuracy gauge to the test is to start changing some of the different variables and parameters inside of our analysis. So I think the first thing we need to do is start to adjust that k value. I think that we could create some type of for loop or something like that to alter our k value over time. And then for every different value of k, we can rerun our analysis and print out the accuracy of that particular value of k. So let's take another quick pause and start putting that code together in the next section. In the last section, we started putting together some accuracy statistic here. We're now ready to start altering the value of k over time. Before we do, I want to do a little bit of code cleanup on this block of code right here. You'll notice that we've got this for loop, which is a little bit archaic. I think that we could probably rewrite this entire block right here using the chain function from Lodash and considerably consolidate everything that you see here. So I'm going to add a little bit of new lines underneath that console log. I'm going to leave the old code in here for now so we can use it as a reference as we rewrite this using Lodash. I'm going to first begin by adding a chain, and we're going to chain over our test set of data. So I'm going to chain on test set. Then for every single record inside of test set, you'll notice how we're essentially running some calculation and then really just doing a if statement right here and checking equality. So we can very easily rewrite this type of logic right here using a filter function instead. A filter function is going to remove, let's pull it up really quick. I'm at my Lodash documentation. With the filter function, we pass in an array and then a function. And if that function right there returns true, then it's going to be included in some output array. Otherwise, if it returns false, it will be rejected and not included. So we could very easily put this little comparison right here into a filter function. So to do so, I'll chain on a .filter. This is going to be called with a single test point. Essentially, that's a single test observation. You might even want to call this like test observation instead. But I think test point is just a little bit more concise. So then inside of this function right here, let's do a long form function first, and then we'll kind of reduce it down in size. We want to run knn with our training set of data, just as we did before. Now, rather than having to reference test set at I, we've already got the individual test point that we care about. So as the second argument, I'll pass in test point at 0. Remember, that's the actual data point or the drop point that we care about. I'll then compare that against the actual result, which is test point at 3, just as we had before. 3 is where we are storing the actual bucket that the ball fell into. So that's test point at 3, like so. And I'll make sure that I return that result. So what you see right here is very, very much accurate to what we are doing right here. Now the only change I'm going to make to this is to remove the return keyword and the curly braces to just consolidate this into a single line. So I'll remove the curly brace, I'll remove the return, I'll remove the other curly brace as well, and I'm going to get that semicolon off the very end of the line too. All right, so now we're going to end up with an array that has only the records where the bucket count, or the bucket that was determined, was equal to what it actually was when we dropped it inside of our little simulator. So now the next thing we need to do is somehow count the number of records, because that's what we were doing before. We were counting how many we had correct. To do that, we can use another function from Lodash called size. Right here, the size function is going to count the number of records. It's essentially identical to calling length on an array. So I'll do a .size. And then remember before, we were dividing by the test set size. We can actually do this step right here inside of our chain as well. We can do so with a very aptly named function called divide. So with divide, we can divide two numbers, but of course, because we're in this little chain statement, we don't have to pass in that first argument. All we have to do is pass in the number that we want to divide it by. So I'll do a .divide, and I'm going to divide by my test set size of 10. And then finally, at the very bottom, I'll pull out my value. And I'm going to assign this to a variable that I'll call accuracy. Okay, so what you see right here is the same thing as everything that we were doing with that entire statement right there, but it's dramatically more concise. I know it's a little bit more complicated, especially the first time you write this stuff out, but it's definitely more concise. So I'm going to delete all that, and I'll replace it with a single console log of accuracy. And if we want to be totally identical to how we were before, we'd say like accuracy is. Okay, I'm going to save this. I'll do a quick test again. So I'll do my refresh. I'll drop 10 balls every 10 pixels. And then I'm going to analyze the result. And it looks like this time around our accuracy was down to 0.3, or essentially 30%. We were only correct 30% of the time, which is still better than totally random. So not the worst thing in the world. Okay, let's take a quick pause right here, and in the next section, we'll actually get around to varying that value of k. I know I said that we were going to do that this section, but just one more quick little pause. Now that we've done our little refactor, we're going to start to run this statement of code right here for different values of k. We'll observe the accuracy for each different run, and then we'll eventually pick some value of k that we'll move forward with throughout all the rest of the work we're going to do on this project. So to vary the value of k, we're going to essentially wrap this entire block right here with a for loop. We'll change the value of k, and then we will rerun our KNN algorithm considering a different number of top records. Now we could definitely do a for loop as we did previously, but again, a lot of things that we could write with for loops can be very easily recreated with Lodash instead. So here's what we're going to do. I'm going to pull open my Lodash documentation again, and I'm going to look up a function called range. So with range, we can pass in a start number and an end number, and that will produce an array for us. So a good example is right here. 1 to 5 is going to produce an array 1, 2, 3, 4. So the end index right there is not inclusive. It stops 1 short. Once we use range to produce this array, we can then use this array as all the different values of k that we want to test our algorithm with. So let's give this a shot. I'm going to flip back over. And right above our accuracy statement, I'll do a range. And I'm going to test out values of k from, how about 10 to like 15. And then for each of those different values of k, so I'm going to put in a for each statement here. I'm going to put in my k as the argument, because that's what we're treating it as here. And then I'm going to wrap this entire block of code inside of that for each, like so. So now we're going to iterate from 1 to 14 in this case, because remember the 15 is not inclusive. So we're going to run from 1 to 14, and we're going to do an accuracy test for each of those different values. Now the last thing we need to make sure that we do is we need to make sure that we actually use this value of k when we run our KNN algorithm. Right now, our value of k is hard-coded up here at the top. So I don't want to hard-code this thing anymore, so I'm going to delete the const k equals 3 at the very top, so that's totally deleted. And instead, when I run my for each, I'm going to pass in the value of k to my KNN function call. So as the third argument, I'll pass in k like so. So right there, now every time we call the KNN function, we are passing in the data that we want to be used as the kind of similarity data set, the point that we're trying to make the prediction for, and the actual value of k. So now I need to make sure that down inside of my KNN function right here, I receive that k argument like so. And remember, k was used on that step right there. Okay, so this looks good. Now I'm going to save this, and then I'll flip back over to my application. I'm going to refresh the page. I'm going to get my initial data set by dropping 10 at 10, as we did previously. And maybe I'll get a little bit more data, so I'll do another 10. Okay, cool. And then finally, I'll click on my Analyze button. All right, so for all of our different values of k, we printed out an accuracy report. One thing we kind of forgot to do is actually print out the value of k that's being used on every given step here. So let's try putting that into the little console log here as well. We'll say something like, how about for k of k, accuracy is blah. So now we'll get a nice little statement that says, for a given value of k, our accuracy is whatever it is. Now let's try doing this again. So I'll do another 10 at spacing 10. And let's get just a little bit more data. I'm going to run that one more time. By the way, you might notice that we're getting more balls over here on the left-hand side than it looks like we are on the right-hand side. The only reason for that is that I arbitrarily capped the number of balls that can be dropping at any given time, just to prevent you from accidentally locking up your browser by spawning too many balls. So you see, if I click drop really quickly, like I'm dropping as fast as I can right now, it will only allow about 700 unique balls to be created at a time. So that's why you're sometimes seeing fewer balls ending up in these buckets over here. It's because if there's a cap at any given point in time, it's going to first spawn the balls on the left-hand side, and then it might run out of space, or kind of space to spawn more balls by the time it gets to the right-hand side. When it comes to our KNN algorithm, it doesn't make a big difference, because all we need to make sure is that we have data readings from all over this entire board. Okay, just a quick aside, I thought you might be curious. Okay, so now that we've got our data set, we will analyze it and see our report here. So for all these different values of k, it looks like we are ranging in accuracy from 0.2 all the way up to about 0.5 or so. So that's definitely, not the worst. Again, our benchmark is 10%. If we guess randomly, we would be correct 10% of the time. So even an accuracy of 0.5, and technically even an accuracy of 0.2 is better than random. Now, one thing that might be affecting these accuracy ratings right here is the fact that we are only using a test set size of 10 records. 10 is kind of a little bit small, and we could definitely try to make predictions for far more records than this and try to get an even more accurate rating to say that a given value of k is better than the others. And one thing I want to tell you about here is you don't want to run your test set too high. If you start putting in values of like 200, that means that you're going to run the KNN analysis 200 times 14 times. And that would possibly lag up your machine just a little bit. So I think that maybe I'll settle for something like 50. And I'll try this again. So I'm going to save the file. I'll do my refresh. I will get my initial data set. And I'll drop one more. So that was another good time where you saw the number of balls was definitely capped. It only spawned balls on like the first 3 quarters or so. Okay, that's definitely enough data. So I'll do analyze. And you'll notice how it took that time a little bit of, you saw that kind of like little delay as it calculated each step. We're definitely getting to the point where my laptop even is taking a little bit of time to run this analysis. I have a rather modern laptop myself. It is a very, very new high-end model. So if you're on an older laptop, it might take you a little bit of time to get through each of these steps. Okay, so this time around, our accuracy ratings are dramatically different than what we had before. Before we were ranging from like 0.2 all the way up to 50 or so. But now that, or excuse me, 0.5, like 50%. But now that we are including more guesses or more tests inside of this test set, we can see that the rating is a little bit more consolidated, all the way from 0.28 to 0.18, and then 0.26, right around 0.2 to 0.3, or about 20 to 30% correct. And it looks like we've got a good little bump in accuracy around 10 and 11, where we get up to 0.3, and then even down at a k of 14, we get to 0.34. So without a doubt, we could definitely play around with the value of, or the range of k's that we test, and we could also play around with our test set size quite a bit. It's definitely up to you where you want to draw the line and eventually say, okay, I'm happy with the k value here. As a quick test, I'm going to run one last analysis. This time I'm going to bump up to 100 records, and I'll expand my range of k to how about like 20 or so. Now, if you have a slow laptop, if you have an older model laptop or desktop or whatever you're using, I encourage you to be kind of careful with these numbers because they might entirely lock up your browser if you put them too high because you're doing too much processing. So do be careful with these numbers as you start to change them. Okay, so I'm going to do one more analysis here and see if I can get a little bit more definitive value for k. Now, as usual, I'm going to get some initial data set. So I'll do my drop. I'll do a drop again, and I'll do one more time just for really good measure. And then finally, I'll do my analysis. All right, there we go. So now with an even larger test set size, we can see some even more fine-grained statistics on how accurate we are. You'll notice that, again, it starts off with an accuracy of about 0.3. I think last time we were maybe at 0.24 or something like that. And it looks like our accuracy drops off around a k of 2. That's actually kind of interesting, but it kind of makes just a little bit of sense. Because when we have an accuracy of 2, if we see, say, bucket 6 and bucket 7, then it's kind of random which one will be picked. And if it turns out that bucket 6 was correct, well, we weren't quite able to build consensus, where we're able to build consensus more easily when we start getting to these larger numbers. Now, it looks like I'm going from 0.31 and then down a little bit, and then I start to go back up when I get to around like 8, 9, and 10, which is what we actually saw previously on the last iteration as well. So it kind of looks like a sweet spot is on the higher side of like 7 or 8. So maybe a k of 10 in general would be a really good spot to land for the analysis of our data set with just this one single feature of the exact drop position. So I think that moving ahead, at least as long as we're only using the drop position as the only feature that we're considering, I might use a k of 10 here, because it looks like that's kind of a happy medium as I start to vary my test set size. Right around 10, it looks like I'm starting to get a peak in my overall accuracy. Now, one quick thing I want to mention here, I know this section is running just a little bit long, just one last thing. One thing that you might try changing is the spacing at which you drop these numbers as well. You know what, let's just do it really quickly. Doing these little testing is really, really fun for me personally. So let's do this one more time. I'm going to drop one ball every 1 pixel. So 1 and 1. If you do 10 and 1, you're going to definitely run into that ball cap very quickly. So try 1 and 1 as your spacing here. And I'll again do some initial data. And I'll do it one more time. And then I'll run my analysis. Okay, there we go. Now, you'll notice that when we start to drop down that accuracy to 1 and 1, for some very interesting reason, it looks like we're falling quite a bit, about 10% across the board, even as we get up to those k of 10, 11, and 12, where we saw around 0.3 before, we now see like 0.22, 0.25, 0.26. So without a doubt, there definitely seems like there's a lot of different variables here that we could play around with and hopefully come to some consensus over the value of k. Like I said previously, it looks like 10 in general is a pretty happy number to sit with. And that's just for this application that we're working with. It might be that on different problems with different data sets, different values of k come up with dramatically different results. So in general, a good way of approaching this is to just run the KNN analysis multiple times and eventually pick out a value of k that kind of seems like you're getting to a nice sweet spot. Okay, so again, sorry for the long section. Let's take a quick pause right here, and we'll continue in the next section. Through a little bit of hard work, we now have the ability to say exactly what value of k works better than some other given values. Of course, it still looks like these different values of k that we're making use of have some variability depending upon exactly how we create that test set. So I think that we still need to look at some other ways of improving our KNN algorithm. The next thing we're going to start to work on is adding more features to explain the analysis. So remember, right now, we've got a couple of different variables or features that are floating around. We've got the drop position, we had the bounciness of the ball, and we also had the ball size. But at present, we are completely omitting the ball bounciness and the ball size from our algorithm, and we're only taking the ball drop position into account. Now that was definitely fine before, because we had a version of our KNN algorithm that worked with a single independent variable. So we're now going to start to modify our algorithm and have it take into account multiple variables, in addition to just the drop position. let's talk a little bit about how we're going to modify that algorithm to include multiple different features. All right, so here's the modified algorithm for using multiple variables. Now, I could definitely walk through this thing step by step, but I'm going to tell you right now, the only real step that changes in the entire flow is that distance calculation. Before, we were trying to figure out how similar or dissimilar a drop position was to all of our different observations. We're still going to do the exact same thing, but now we're going to be finding the distance, so to speak, between multiple different features. To give you a really good idea of how this is going to work, let's first walk through exactly what was happening before when we were only taking the drop position into account. So this is what we're doing right now. So we've got our training set over here where we've got all these different data points. We've got the drop point, the bounciness, the ball size, and the bucket it went into. So essentially with our training set, we took each of these different values, so first 40, and we kind of graphed it, so to speak. You can imagine that we kind of graphed it on this chart. We then put another data point on for the 150, so maybe that would go right around there. We then had our 350, so maybe right there, and then the 425 right here. After we put those together, we then said, okay, our prediction point. How close or far away is this thing from any of these existing points? If the prediction point had a 323 drop point, then we would take this thing and put it maybe right around there or so. So if we then said that we had a K of 1, we would look at that data point right there as being the closest, most similar drop position. And so whatever bucket that thing went into is probably where this one is going to go into as well. If we had a K of 2, we would maybe consider this point and this point. And if we had a K of 3, it'd be the closest 3, and a K of 4 would be all 4 of those data points put together. Now, again, the key thing to keep in mind here is that the very simple distance calculation that we're using right now, so inside my code editor, here's that distance function. We were just finding the straight line, one-dimensional distance from point A to point B, and then taking the magnitude or absolute value of that distance. And that fit this chart right here very well. So how is this going to change with a second feature, or even 3 or 4 or 5 features being added in? Well, essentially all that changes is the chart that we're using to find our distances. So let's do that same exercise, now taking our drop position and our bounciness into account. So again, we'll say for 40 and a bounciness of 0.5, maybe that line would be, or that data point would be like right there or so. Then 150 and 0.25, or 0.52, excuse me, that'd be maybe right about there or so. 350 and 0.55, that'd be maybe up here. And then 425 and 0.53. So let's see, maybe right around there, a little bit higher, right there or so. So then our prediction point was 323 and 0.25. So that's maybe, or 0.52. Sorry, I keep on mixing that up. I think this was my other 0.52 right there. So I think 323 might be like right about there or so. I think that's reasonable. Okay, so now we would want to find the distances between all these points and our prediction point and see which one was closest. Now remember, in our 1D case back over here, we had said that the 350 data point was very, very similar to our prediction point. But now this time around, if you look, our same 350 point from the training set is all the way up here, and it no longer appears to be the closest to our prediction point. Instead, it looks like this point and this point are the closest. Maybe this one's a little bit closer. And of course, I'm not being really exact where I put these data points. So clearly by introducing these additional features into our comparison, we are dramatically changing which point we consider to be closest or more similar to these other data points as well. Now, the last thing we have to really consider is, all right, we understand that we're going to include multiple variables in this comparison or multiple features, but how are we going to actually change this distance formula right here? How are we going to find truly how far or close away one point is from another? Well, to do so, we're going to use the very classic Pythagorean theorem. So the Pythagorean theorem, we take a triangle of sorts where this c, or the hypotenuse, is going to be the true distance from one point to another. So back in this diagram over here, if we wanted to find the distance from our prediction point to maybe this one up here, that c, or the hypotenuse, would be the true distance between these 2 points. And to calculate that, we would take the difference in one direction, or the x-axis, the difference in the y-axis, we would square them, add them together, and then take the square root of all that. and that would give us the distance between those two different points. So, in other words, to change out our entire algorithm and make it work for multiple dimensions, all we really have to do is update our distance formula right here, and also make sure that when we pass in these data points to that distance formula, we consider all the different features that are relevant. So the drop position, the bounciness, and the ball size as well. So let's take a quick pause right here. When we come back to the next section, we're going to start to update our KNN algorithm to take into account multiple different features. So quick pause, and I'll see you in just a minute. In the last section, we started talking about how we can include multiple features in our KNN analysis. We had said that we can kind of imagine that our distance formula plots all of these different points and then tries to find the closest point to our observation point. And so we would want to find the distance from this point to this point, this one to this one, this one to this one, this one to this one, and then use that as our sorting criteria. We had said that we could use the Pythagorean theorem to determine that distance. So I want to very quickly go through a quick example and then show you one or two side topics you might be interested in. All right, so same example we were just looking at. We would want to find the distance from the blue point to the green point up here using the Pythagorean theorem. Now we're just going to go through this one iteration of this, but in theory we would want to go through from this point to this point and all the other combinations as well. So up here is the Pythagorean theorem written out in common notation. So we want to get this distance A on the x-axis between the 2 points. So that would be the difference in their drop position. So we would take the 350 minus the 323 of our prediction point. So there's 350 minus 323, and we would square that. We would then take the difference in the bounciness between the two as well. So that would be 0.55 minus 0.52, so 0.55 and 0.52, and we would square that as well. We then add those two sums together and then take the square root of the entire thing. And just so you know, these stars right here is the JavaScript operator for raising a number to a power. So *2 squares a number, *0.5 is taking the square root of something. Now I could very easily take this number right here and place it into some JavaScript console, like I'll just open up one right here, run it, and you would see that the distance between those 2 points is just about an even 27 units. Okay, so that's an example of how we would do a 2-feature distance calculation. Now, one thing that you might be very much aware of is that in our application, we actually have 3 separate features. We have our distance, or our drop position, we've got the ball bounciness, and we've got that ball size. And we probably care about all 3 features. So how does this equation change when we have 3 features? Well, once you get into this Pythagorean theorem, adding on additional features is incredibly easy and straightforward. So if we want to add on a ball size metric as well, then we could imagine plotting all of our data points on a 3-dimensional space like so, where we've got our drop position, our bounciness, and our ball size. In this case, our ball size was the same for all these different records, and at 16, and I just did that to make this chart a little bit easier to put together. But essentially, you can imagine if we had different ball sizes on here, we would want to find our prediction point right here, and the 3-dimensional distance to all the other points, taking that ball size into account as well. So to get our 3D Pythagorean theorem, all we have to do is add in this new C term right here, where C would be the change or the distance along the ball size metric alone. So in this case, that's 16 for both of them, so it would be 16 minus 16 equals 0. But you can very easily imagine that maybe if one of these was different, like say this was a ball size of 18, then the C term right here from this prediction point to any of our training examples would be something like 16 minus 18, like so. So as we start to add on more features, we just put in additional squared terms into this equation. The square root doesn't change. We don't put on any multiple in front of this. We just put in these additional squared terms. That's it. Okay, so with this in mind, let's take one more quick break. We'll come back to the next section, and we're going to start to refactor our KNN algorithm to take multiple features into account. So quick pause, and I'll see you in just a minute. Now that we understand how our algorithm is going to change once we introduce multiple features, let's start to update our code so that we can take into account not only our drop position, but also the bounciness and the size as well. Now, as we do this refactor, things are going to start to get just a little bit challenging. And the reason for that is exactly how we put our KNN algorithm together. you'll notice that inside of here, specifically on this second line right here with the map statement, we're making a very big assumption. We're calling distance, and we're always assuming that the only metric that we care about is in the first index of each individual observation. And that's no longer the case. In reality, we now want to consider many different indices, or inside of each individual row. Specifically, we want to consider everything up. It's a good diagram for this back here. We want to consider all the different indices inside this individual observation except for the very last number. The very last number is our label, and so we do not want to include that in any distance calculation. Now, we could very easily modify all the code in here and just say like, oh yeah, find the distance from row 0 and row 1 and like, row 2 like so. But I think it would be really nice if we had a version of this algorithm that would work nicely for any arbitrary number of features that we want to throw at it. So in other words, if this structure right here ever starts to change, and we start to add in some additional metrics, whatever number that might mean, and that one, I would still want this algorithm to work a-okay and not just start to mysteriously break as we start to change the number of features. So that's why doing this little refactor is going to be just a little bit challenging. We really need to just make sure that this will work with any arbitrary number of features. Okay, so with that in mind, let's first make a change to our distance function and refactor it to use the Pythagorean theorem instead. And I think that'll start to give us a pretty good base to understand how we're going to write code to work with any arbitrary number of features. So we're going to assume that the distance function is going to be called with point A and point B, but rather than imagining that point A and point B are numbers, like the maybe 300 and 350 that they were before, we now want to assume that point A might be an array with a couple of different numbers in it. And point B will be the same, where it might be 350.55 and 16. And so we need to make sure that we write some code that can still work no matter how many different values we put into these point A, and point B arrays. Now doing this with Lodash is going to be very easy and straightforward, but the code for it is going to look just a little bit confusing. So let's very quickly do an example over inside this little code editor over here, just so you can see it visually play out. Now remember the URL for this. Let me put it on the screen one more time, just because we haven't looked at it in a little bit. And remember that the JSP is all capitalized. Okay, so let's assume that we've got like a point A at 1, 1, and maybe we've got a point B at 4, 5 as well. We'll just start out with these 2 dimensions, and we'll come back and add a third one on in just a second to verify that this works with however many features we want to throw at it. Okay, so we're going to do a little bit interesting code here. I'm just going to throw the code up, and then we'll take a look at what it's doing. So I'm going to do my chain. I'm going to chain on point A, and then I'll add on this method here called zip with point B. Okay, to be honest, that's kind of the hard part to understand right there, this zip function. The zip function is going to take 2 arrays, so in this case point A and point B. It's going to look at each index, so like 1 and 4, and then 1 and 5, and it's going to put them each together in their own separate little array. So notice how the output over here, we now see the first element from each of these arrays in 1 and 4 right here, and then we see 1 and 5 put together in their own array right here. The reason that we're doing this is that it much more closely fits with how we have to execute the Pythagorean theorem. Remember, the entire goal of that Pythagorean theorem is to take the distance between this point and this point right here. So we really need this point's drop position and this drop position, and we want to subtract them together. So that's why we're doing the zip, to make sure that it's very clear that these 2 initial numbers right here are very closely related, and that these are 2 very close related numbers as well. So now after that, we can do a map statement. And the map statement will be called with our pair of numbers that are very closely related. So we could now do something like pair at 0 minus pair at 1, and then square the result. Now, just one little issue, however, putting on the pair at 0 and the pair at 1, just a little bit ugly here. So maybe a better way of doing that would be to use a little bit more ES 2015 destructuring. So rather than referencing pair at 0 and pair at 1, I'm going to destructure those 2 numbers out of this argument right here. So I'm going to put on a pair of parentheses, and then a square brace like so, and I'll reference A and B. So that's saying that we understand that the argument here is going to be an array with 2 elements. And we want to take whatever that first element is and assign it to a variable called A. We want to take the second element and assign it to B. So now in our math over here, we can do simply A minus B. And you see that we get the same numbers that we had before. You'll also notice that 1 minus 4, or the difference between those, is -3, and the difference between 1 and 5 is -4. So we're using some kind of interesting code here. I know it looks kind of strange, but we're definitely saving ourselves a ton of effort of having to write out a for loop or anything like that. Now the last thing we have to do here is square the result of this difference. So after the first little parenthesis right there, I'm going to square it by putting in **2. Now just one little thing, this whole code editor is not set up to work with that ** syntax. That's a relatively new piece of syntax. So you'll notice that I'm now getting an error message down here. So for just a moment until we finish this snippet of code, I'm going to leave off that square value. We'll finish off the rest of the expression, and then once we're sure that everything is more or less working correctly, we'll come back and put on the squared term. Okay, so now that we are mapping this thing, we're taking the difference and then squaring, in theory, remember we're going to come back and do that in just a second, between all of these different terms. Now the next thing we need to do is sum them all up. And again, Lodash has our back for that. We can just call sum. It'll sum everything together. And then finally, we should never forget that with a chain statement, the very last function call has to be value to actually get a number out of this thing. Okay, so that's pretty much it. Now, like I said, the last thing I want to do here is add on the squared terms. So back up here, I'll put on the **2, and then I need to make sure I also take the square root, which I can do by at the very end doing a **0.5, like so. Now, I know you see the error down here. Again, that's totally fine. It's just because this editor is not started up for the exponent syntax. So now the last thing I want to do to actually test this out, even though this editor doesn't recognize the ** syntax, chances are that your browser does. So to test this out, I'm going to copy this entire statement. I'll open up my terminal, and I'll paste this in, and I'll get a result out. And you'll see that the result here is 5. The reason that this worked out so nicely is that this is actually forming what's called a 3, 4, 5 triangle. Essentially, one really good triangle set of dimensions to memorize is a 3, 4, 5. If this side right here is equal to 3 and this is equal to 4, the hypotenuse is always going to be equal to 5. So that's why we call it a 3, 4, 5 triangle. So you might notice that the point A and point B coordinates I picked right here, this has a x position, or essentially, the initial coordinate is a difference of 3, and then the second coordinate has a difference of 4. So essentially, we have a 3-leg, a 4-leg, and so the hypotenuse must be 5. Like I said, it's a nice little metric to memorize just to make sure if you ever have to write this code again, you'll know that you're getting the right answer without having to actually pull out a calculator or something like that. Okay, so it looks like this is working out just fine. And of course, if we start to add on additional dimensions here, like, I don't know, a 6 or something like that, it's going to continue working just fine as well. Now, if you try to copy paste this over again, you're going to get an error message that point A has already been declared. That's because we declared these two things with the const syntax. But if I wanted to, I could very quickly copy this code, refresh my page, and then paste it in, and I'll see my result up here right there. No errors, it looks like everything still works. Okay, so this is perfect. So I'm going to go back over to my code editor and replace my distance body function, or the body of that function, with the code that we just wrote. I'll clean up the point A and point B, because those were just examples. I'll indent that, and then I'm going to return the result like so. Okay, so we now have a distance function that works with any arbitrary number of features. I'm going to clean up that comment as well. So this is looking pretty good. Let's take another quick break. When we come back to the next section, we're going to make sure that no matter what, we always pass in the correct values into the distance function right here. So quick pause, and I'll see you in just a minute. In the last section, we replaced our distance function to work with any arbitrary number of dimensions. So we can have a ton of data in point A, a ton of data in point B, and we're going to always find the distance correctly. Now, the next thing we need to do is update our KNN algorithm right here. At present, we've got these hard-coded references to row at 0 and row at 3. We hard-coded those in because those were the indices of our drop position and the bucket that the ball went into, or our label. So we need to now refactor this a little bit to make sure that it's always going to work no matter what, even if we start to change the structure of our data. So again, this is the current structure. We've got the drop position, bounciness, ball size, bucket, and at some point in time, we might decide to come back and add in additional features here. So maybe something like that and that. And now our indices are going to change. So to accommodate for this, we're no going to longer use these hard-coded indices right here. Instead, we're going to start to divvy up this row value and the row right here and make sure that we're only considering the values that we really care about, so the features in this case and just the label in this case. So to do so, I want you to recognize that it appears with our current structure of data, the first elements all the way up to the last one right there make up our feature set. So we want to pass those off to the distance function. And the last element is always our label. And we always want to put that in as the kind of secondary element in this little array that we're making right here. So we really just want to kind of split off the very last element there. To do so, we're going to, you guess it, use two Lodash functions. So to get this initial set of records right here, or just the features by themselves, we can call initial and pass in that array. And you'll notice that it kind of removes that last record on there. And we're left with just this right here. And then to get the last element, of course, we could do our last point, and that gets us our label by itself. That pretty much solves our problem. Now, one thing you might be a little bit curious about, you might be thinking, why are we using these last and initial functions? Why don't we do something like, I don't know, maybe something like point.pop, which removes the last element, or kind of gets the last element on the array. Well, this is something that we haven't quite gone into just yet, but there's a very good reason that we're not using classic functions like pop or shift or unshift. The reason that we're not doing that is that the pop function modifies this original array. So if I pop something out of point and then print it out, I'm left with just the 3 original records right here. Now, for our current problem, that's not a big deal, because that's kind of what we're trying to do, right? We're trying to get that element by itself, and then also get the first 3 records. So it might seem like using pop is a really good idea. But on this KNN algorithm and other algorithms that we're going to work on in the future, we very frequently have to reference the same data point over and over. And so at all costs, we want to avoid mutating this array in any way, shape, or form, because we might need to reference this data inside of here at some point in time in the future. And if we are just going to willy-nilly wreck that array and destroy it over time, we're going to very quickly get in a lot of trouble. One of the great things about many of these Lodash functions is that they do not modify the original array, and they instead return a new array where applicable. And so after doing the initial right here and the last right here, I can print out point again, and it's still the original array. I haven't modified it in any way. Okay, so I think we got a better idea of how to approach this. So let's flip back over to our code editor and give it a shot. All right, I'm going to find that map function right here, and the first thing I'm going to do is expand it with some curly braces like so. I'm definitely going to write this thing in multiple lines, so just to make it a little bit more clear, I might be able to condense it down to a single line, but I think they would probably get a little bit confusing kind of quickly. All right, so I'm going to make sure I get my return keyword in there as well. And then maybe just to make things even more clear for right now, I'll put the array on multiple lines. Like so. All right, let's take care of our label first. So instead of row at 3, I'm going to instead do our last of the row. So last row. And then in addition, for the distance right here, rather than passing in just the first point, I'm going to instead do row at 0, or excuse me, not row at 0, I'm going to do initial on the point, or excuse me, the row. I keep on reading point over here at the end. Now, one thing to keep in mind is that the point itself, actually this is very relevant, the point is being made up of our test data right now. And those test data featured, or those test data records, have a label on them as well. And so when I pass that data into the distance function right here, I definitely want to do initial on this point as well. Now this is going to kind of put us into a bind, however. Let's put initial on here really quickly, and I'll tell you why. Okay, so that looks good. So let me tell you why putting the initial on this point that we're passing in as kind of the thing that we're trying to predict is going to be a little bit of a pain. So if you recall, we had said that we were going to divide everything up into our training step, our training set, and our test set. Here we go right here. So the only reason that we're doing that initial on that point value is that we want to get off the label on that thing as well, because those are data points that were sourced inside of our application, just like our training set. So we still care about that label on the end. We just don't want to pass that label in to our distance function. So that's why we're putting the initial on here. Now, the reason that this is kind of a pain is that at some point in time in the future, you and I might want to make use of our algorithm manually. So we might want to enter in some value to make a guess with. We might want to enter in a value of something like, hey, where would a ball drop if we dropped it at, or where would a ball fall if we dropped it at 400 with a bounciness of 0.5 and a ball size of 20? Now, when you and I enter this data in, we are almost definitely not going to put a label onto the end of this thing because we don't know what the label is. We have no idea what the label is. We're trying to figure out what the label is. It's only our test data that has the label on the end there because it was sourced or is created by our application, and we already know what the bucket is for each of those individual examples. So in one case, we've got this data structure where we've got the bucket on the end, but if we ever start to use our algorithm in the future to predict points of our own, we're probably not going to put the bucket on the end there. So with that in mind, I think that we should probably not put the initial on this statement right here, and instead, when we pass a data point into the KNN function, we should make sure that the point, or this value right here, has already had the label kind of taken off. Because that's going to mean that our KNN function is going to work just fine when we try to use it for testing purposes, and when we try to use it for predictions on our own as well. Okay, so with that in mind, I'm going to come back here and I'm going to remove that point, because we're going to assume that point from now on, point has 3 values. It doesn't have that 4th label anymore, that's the assumption. But to make sure that that's actually the case in our current code, we're going to go back up to our run analysis function, and I'll find where we're calling KNN right now. So here's where we're passing in the test point, and we now need to make sure that we're not going to put in the label on this thing anymore. So to make sure that's the case, all we have to do is take off that index right there, and I'll put the initial on this thing instead, like so. So now whenever we call our KNN function from our testing code right here, we're passing in that array with only the 3 entries in it. No label is present. And so that means that we're now going to be able to very easily reuse our KNN function in the future as well when we start trying to make our own predictions. Okay, so this looks pretty good. I am going to take the comment off of here. And I think that we have now successfully converted our KNN algorithm to use multiple different features. So let's take a quick pause right here, and we'll do a quick test of this thing in the next section. In the last section, we had a pretty long refactor of our KNN function. So now it works for any number of features that we try to throw at it. Now, before we test this out in the browser, I made a little typo at some point in time in the last section. You'll notice down here on 2 pairs, I accidentally at some point put the underscore dot right there. Don't know where that really came from, so I'm just going to clean that up really quickly. Okay, so that looks better. Now I'll go back over to my browser. I'm going to refresh the page. It looks like everything is still working. Okay, so just as before, our application is still set up to do some analysis for our k values. That's totally fine. We're going to now do the analysis for ideal k values using these multiple different dimensions. So maybe with multiple dimensions, maybe we'll find out that our k value that is optimal is going to change. Who knows? Let's try running this and see what happens. So I'm going to again do 10 different balls at 10 pixels. So I'll do my drop. I'll do another drop. And one more for good measure. And then I'll run my analysis. Okay, so let's see how we're doing. Okay, so everything is printing out just as it was before. You'll notice that it's significantly slower this time around. The reason that it's so much slower is that we've added in quite a bit of complexity by including multiple dimensions. Some performance issues like this is something that we're going to be really concerned with later on inside the course, but for right now we're just going to kind of suffer with it running a little bit more slowly. Alright, so I got my output right here, and it looks like in some cases our accuracy is way better than it was before. Now, I'm kind of surprised that it's so much better. You might recall that before for a k of 1 we had something like, 0.2, and a k of 2 is something definitely like 0.2 as well. So maybe I'll try this one more try. I'm going to refresh. And I'll do 10 on 10 again. and one more, and I'll run the analysis right away. Okay, there we go. So again, I'm going to print it out, and again, it still seems to be quite high. It seems like it's doing awfully well. That's definitely not the worst thing in the world, but I want to point out something to you that could be throwing these results off and maybe not adding in that bounciness factor quite as attractive as these results right here would make you think that it is. So let's take a look at a diagram or two. Okay, so as you recall, let's see, we're just looking at this one right here. We had said that we were going to plot our drop position against our bounciness. And then on our axes, I had ranges from 0 to 200, 400, 600. And then on the bounciness, we had 0.5 and 0.55. Now the way in which I made this diagram right here was very, very misleading. I want you to look very closely at these axes. The x-axis, or the horizontal one, is running from values of 0 up to 600. But on the horizontal, or semi-vertical, we're running from values of 0.5 to 0.55. But I still made it seem like the gap between these two values right here was identical to the gap between values of 0 and 600. Let's take a look at another version of this chart that is going to be graphed a little bit more realistically. Okay, so this one is a little bit more realistic. It kind of accounts for the true distance or the true range between the different values of bounciness and the range of values in our drop position. You see, as the drop position starts to change, we're getting very large differences in our numbers, anywhere from 40 to 150 to 425. But as our bounciness changes, it's only going from 0.5 to 0.55. So in reality, all these data points are essentially on a straight line going right across. What does that really mean? Well, it means that when we start to do our analysis, the bounciness factor is probably not affecting anything quite as much as you might expect. If we try to find the distance of points, or try to find what points are close to our prediction point right here, this diagram makes it seem like maybe point B is the closest, or this green point right here is the closest one. But in reality, if we really consider it from the correct axis perspective, that green point is not the closest one. It was this one over here. Oops, that one right there. Because the bounciness factor is very, very small. So small that it might as well be 0. If you even look at this equation right here, you'll notice that the bounciness term ends up being 0.03 squared, which is a very, very small number. Let's actually run the math on it very quickly. So the bounciness factor is only 0.03 squared, which is 0.0009. Very, very small. But the distance calculation was 350 minus 323 squared. Let's make sure we get our parentheses in there. And the result of that was 729. So what that means is that the contribution of distance from our drop position is a huge, huge, tremendous factor compared to the contribution of our bounciness factor. It essentially means that the bounciness is just not in any way contributing any meaningful information to our k-nearest neighbor analysis. So clearly, even though we've wired this thing up to use multiple features, it's maybe quite not working the way we expect. So let's take a quick pause right here. When we come back to the next section, we're going to talk about how we can kind of address this problem and solve the fact that the bounciness seems to be such a tiny little factor. Okay, quick pause and I'll see you in just a minute. In the last section, we spoke about how the range of values for our bounciness is absolutely minuscule compared to the range of values for our drop position. And so chances are that when we run our analysis right now, the bounciness factor is basically having no effect on our actual output. So in this section, we're going to learn about 2 strategies that we can use to address this. All right, so here's our 2 strategies. We can normalize our data and we can standardize our data. Both these strategies are almost identical. The only big difference between them is the formula that we use. So with normalization, we take our original data, which might arrange in values for, say, just our drop position from 300 to 600. We only consider one feature at a time. So we would only apply normalization to drop position by itself, then we would apply it to bounciness, then to ball size, and so on. With normalization, we're going to try to proportionally scale all of our numbers between 0 and 1. So for example, the data point right here at 300 would be assigned a new value of 0, and the point at 600 over here at the very top end would be assigned a data point of 1. Standardization is very similar, but instead of bounding numbers between 0 and 1, we try to base all of our numbers around a value of 0, And then we get what is called a normal distribution around that of -1 and 1 standard deviations. So with standardization, we're not necessarily capping values at 0 or 1. With standardization, we can very easily have values that go beyond that single 1 standard deviation, as would probably be the case over here with the 600. Now we're going to talk about standardization a lot later on inside the course because it's a fantastic method with some of the algorithms we're going to use later on. But for right now, we're just going to concern ourselves with normalization. Now applying this strategy of normalization, of getting numbers between 0 and 1, uses what is called a min-max method. So with the min-max, we're going to look at one feature set at a time. So like just our ball drop position, and then just the bounciness, and just the ball size. We're going to look at each of those features, and we're going to find the minimum value and the maximum value. We're then going to apply this equation right here for every value in that data set. Now this equation right here is kind of a little bit unclear, especially with these really long words that I'm using, so we'll walk through an actual example of this in just a second. Okay, so here's some examples of it in action. Now that's not what I'm talking about when I say we'll go through this in a second. We're going to actually write the code out for this in just a second. That's what I'm talking about. But just very quickly as examples, if we have drop positions with these values right here, the minimum value would be 150, and the maximum value would be 650 right there. And so we would use these min and max values to scale each of these values, which would then make them scale or range between 0 and 1. We could then do the same thing for bounciness as well. Note how we apply this to bounciness. We are selecting our min and max values from the bounciness data set only this feature, one feature at a time. And so at the end of the day, after we apply the scaling to every separate feature, they're all going to range in values from 0 and 1. And so in theory, they're all going to apply to our outcome, in this case, which bucket the ball falls into, equally. Okay, let's very quickly look at an example of this in that nice little code editor. So quick reminder, here's the link to it. We'll just do a very quick example. Okay, I'm going to open up a new browser tab and navigate over there. Now let's consider some arbitrary points. Let's do like say 200, 150, 650, and 430. And those are actually the same data points I just showed you in this diagram over here. Same one. So we should get the same result right there. So the first thing we have to do is find the min and max values in this array of numbers. Now, of course, Lodash has our back for this. We don't have to write any for loops or anything like that. So we can do const min is _.min points. And const max is .max points. We'll then map over our points array. And for every point, we're going to run that min-max formula. So I will return point minus min divided by max minus min, like so. And then I see the output up here. So we get 0.1, 0, 1, and 0.56. So that's our scaled output. Or another way of saying it is normalized. You will see the terms scaling and normalization used somewhat interchangeably. For whatever reason, very similar. You see them interchangeably used in a lot of different blog posts and what have you. But standardization definitely is a very different beast. Now, the last thing you might be curious about, you might be thinking to yourself, Stephen, how does this not just dramatically change the results of our k-nearest neighbor algorithm? How does this not just absolutely nuke everything we're doing? We're just arbitrarily dividing numbers here. How does it not going to somehow change what we're getting as an output? Well, I want you to remember exactly how k-nearest neighbor, the algorithm itself, works. Let's walk through a quick example using only drop position of k-nearest neighbor, and then we'll take a look at it with some scaled numbers as well. And you're going to see that the output does not change and really cannot change. So in the version right here that you see that has no scaling whatsoever applied, we've got our drop positions that range from 40 all the way up to about 425. So the first thing, and then we want to make a prediction about an observation point at 200. So we would take all these observations right here, and we would subtract 200. So 40 minus 200, and then absolute value of that would be 160. We get 50, 150, 225. We would then sort all these based on their distances, and we end up with red, green, blue, purple. Now let's go through the same process, but we're going to scale these numbers during this distances step as well. Okay, so same stuff that you see right here. All we've done is scaled the numbers in this intermediate step. So now our values range from 0 to 1. Notice how we are also going to scale the value of our prediction point as well. So we don't just take our prediction point of like 200 pixels and throw it in here. We do our min-max formula based on this data set over here, and then we apply it to our our point that we're trying to predict right here as well. So if we run min-max with these data points and then apply it to the 200, we would end up with 0.415. So with that in mind, we can now go through the same process where we scale each of these training values and then subtract 0.415 from each of them. So we would end up with 0.41, 0.129, and so on. And then when we try to sort those, we end up with red, green, blue, purple, which is identical. Here, I'll tab back and forth, identical to what we had before. So it's irrelevant that we scaled these numbers. Doesn't make a difference. No change whatsoever. The outcome is always going to be exactly the same because these are all distances that are relative to the point that we're trying to predict. Okay, so hopefully this makes a little bit more sense. Let's take a quick pause right here, and then when we come back to the next section, we're going to start to implement min-max on our project. So quick pause, and I'll see you in just a minute. In the last section, we spoke about using the min-max method to normalize our data set. In this section, we're going to start to implement the min-max method as a function inside of our score.js file. So to get started, I'm going to first scroll down to the very bottom of the file, and I'll make a new function called min-max. This thing is going to be called with some amount of data, and then we're going to also include a second argument here called feature count. And let me tell you a little bit about why we are including this feature count variable. The purpose of that variable right there is to relay exactly how many different columns worth of data that we have that we want to attempt to normalize. Now, in our case, we have 3 different columns of data that we want to normalize. The first column, so to speak, is the drop position right here. And you can see it kind of makes a column of sorts. The second column is the bounciness variable, and the third is going to be our ball size. So in our case, we have 3 different columns of data that we want to normalize. The reason that we are including this feature count as a variable, the reason that we are trying to say how many columns of data we want to normalize at all, is remember, over time, we might start to include more or fewer features inside of our data set. So if we start to add in some additional features here, like 5, 3, whatever it is, we need to make sure that we tell this min-max function that we now want to normalize the first 1, 2, 3, 4, 5, 6 columns worth of data. The other reason that we are including this variable and not just saying, oh yeah, let's normalize everything, is that in our data set, the very last column is our label. And that label, the bucket number right there, does not need and should not be normalized. So that's why we're including that feature count variable. It's to make sure that we only normalize the first couple of columns and we don't accidentally update or change the bucket label as well. All right, so inside of here, we're going to start putting this thing together. Now, the first thing I'm going to do here is make a clone of that data variable. When we eventually use this min-max function, we're going to apply it to the original outputs variable that we pass off to this split data set thing right here. So we're going to modify outputs in some way. Remember that anytime that we start to work with arrays of data, we go pretty far out of our way to make sure that we don't mutate any of our existing sets of data. We don't want to mutate any variables. We don't want to mutate any arrays or objects. We want to create new modified data sets. So the easiest way to do that here is to do a deep clone of this data set and just make a clone of it before we start modifying any values inside of it. So to clone that thing, we're going to use a Lodash function called, let's pull it up here, clone deep. So the purpose of clone deep is to take an array or object and just duplicate all the values inside of it. And again, we're doing this so we do not modify that original outputs array. All right, so up here at the very first line, I'll say cloned data is _.clone deep data, like so. Okay, so now that we've kind of backed up our data set here, so to speak, we can start to actually modify the values and do our normalization on clone data. Now to do the actual normalization step, we're going to use a double nested for loop. I would love to use a for each loop here or a map, but it really just ends up being a lot easier to use a double nested for loop, and you'll see why in just a second. So I'm going to put down one for loop where I starts off as 0, and I needs to be less than feature count, and I++ like so. So the purpose of this outer for loop right here is to iterate over each column or each feature that we want to normalize. So this outer for loop for us is going to be going from 0 to 1 to 2. 3 iterations, because feature count is going to be 3 for us because we have 3 features. Then inside the for loop, I'm going to extract just the column of data that we care about, just the initial feature set of these drop position values right here. So we're going to extract that column by itself. When we extract it, it's going to be a lot easier to get the min and max values from it. So to extract that thing, I'll say const column is cloned data.map. I'm going to take every row that we have, and I'll return row at I. So again, this is kind of doing a column extraction. Column is now going to be an array of numbers. No nested arrays here, just an array of numbers. Next up, we're going to find the min and max values inside of column. So I'll do const min is underscore.min column, and const max is underscore.max column. Now that we found the min and max values, we're going to iterate over every different value that we have for our drop position inside of clone data, and we're going to modify them in place by applying the min-max function. So I'm going to say for let j equals 0, j less than cloned data dot length j plus plus. All right, so I know the 2 for loops here might be a little bit confusing. So one more time, the outer for loop right here is iterating over each column. So starting at column 0, then 1, then 2. The second for loop right here, the j equals 0, is iterating over each row. So we're starting off with row 0, row 1, row 2, row 3, and so on. So now that we've got the 2 for loops in place, we're going to update our value of clone data for each drop position in place. So I'm going to say cloned data at row j and column I. Now notice the order here. It's j, then I. So the first index is picking out a very specific row, and then the second index I is picking out our specific column that we want to update. And that's going to be data at, clone data at j at I minus min divided by max minus min. Now one quick thing here, please make sure that you have this set of parens around the clone data minus min. If you don't have the set of parens right there, then the order of operations will be off and the normalization is not going to work as you expect. Now the other thing I want to mention here is that we are doing an update of our data in place. So we're not really mutating the clone data array here, or we're not producing a new value. We are completely mutating all the values inside of clone data, which is why we did that initial clone step right here, so that we didn't modify or mutate our original data set. Now after we do all these min-max steps, we can finally return clone data like so. Okay, so that's pretty much it. Now let's take a quick pause right here. When we come back to the next section, we're going to see a very quick example of this function in action, and then we'll wire it up to our actual KNN algorithm. So quick pause, and I'll see you in just a minute. In the last section, we put together our min-max function. I want to very quickly show you a quick demo of this thing in action, just so you get a good idea of what it's really doing for us. So I'm going to make sure that I save my score.js file, and then I'm going to flip back over to my application inside the browser, and I'm going to refresh the page. I've now got my console open over here, and if I want to, I can very easily make reference to that min-max function that we just put together. So there's the code for it right there. Let's very quickly put together a fake little data set, and then just run min-max on it so that we can verify that the thing is working as we would expect. So I'm going to say const data is an array of arrays. So remember, this has to be a data set of the structure that we would normally expect. Now to write out this data set a little bit easier, I can press Shift-Enter to get a new line here without actually running this. So then I'll put in some fake data here. We're just going to put in 2 columns. One column is going to be a feature, and then the other column is going to be a label. So I'll put in like 51, Shift-Enter, 25, 3, Shift-Enter, how about, I don't know, 10, 4. And then Shift-Enter, and I will close that array off like so. Okay, so now I'm going to call min-max on that, and I'm going to tell it that we want to normalize only the first column of data. So after we call min-max, I'm going to expect to see a result where this last entry right here should probably have a leading value of 0. The first one should probably have a leading entry of 1, and I would bet that this middle entry right here would be right around 0.5. I'm only saying those numbers because the lowest value that we ever have when we're doing a min-max is going to turn into a 0, and the greatest value is always going to turn into a 1. All right, so let's try this out. I'll do a min-max, I'll pass in data, and then I'm going to say that we only have one feature that we want to attempt to normalize. Okay, so I get my result. And if I expand this, I don't really have to expand it. You can very easily see the result right here. So that 50 got turned into a 1. 25, I was a little bit off. It came out as 0.375, and then 10 came out as a 0. And then notice how all of our labels at the very end of each row did not get modified at all. All right, so this definitely looks like it's working the way we expect. So now the last thing we have to do is modify our run analysis function and make sure that we actually do our normalization before we run any KNN stuff on it. So I'm going to go up to the top of this file. Here's where we are running our analysis. And I'm going to wrap our outputs right here when we pass it off to split dataset. I'm going to wrap that thing with our min-max function so that right before we try to split this dataset into 2, we're going to first run the normalization and then do the splitting operation. So I'm going to wrap that with a min-max. And I'm going to make sure as a second argument to the min-max function, I pass in the number of columns or the number of features that we want to normalize, which in our case is 3, like so. Okay, so I'm going to save that, and we'll flip back over to our browser, and we'll do a little bit of a test. Okay, so back over here, I'm going to refresh the page. Make sure that you do save the file in your code editor over here, of course. Now that I've done my refresh, we're going to again go through a typical analysis. So I'm going to first update my drop a bunch at various spots form right here to be 10 balls at every 10 pixels, and then I'll get a little bit of sample data to work with. So I'll drop once, we'll drop twice, and I'll do it just one more time. And then I'll go ahead and run my analysis by clicking on Analyze over here. All right, so there we go. Looks like it's kicking off. Now, it does look like this is running awfully slowly. So it could be that we made a little bit of a mistake, or it could be that I just have some very high values for my test set size and my range over here, which is probably the latter. I think that I just left those values too large. Okay, so it looks like this is going, and it's definitely taking a little bit of time. So let's take a quick pause right here. When I come back to the next section, we'll start to interpret the results and see if our analysis is doing any better now that we've implemented some min-max normalization. In the last section, we implemented our min-max scaling and then reran our k-value analysis over our entire dataset. As you can see, we were getting accuracy values right around 8% because I'm seeing values of about 0.08 here. Now that's actually a pretty awful result. That means that with our k-nearest neighbor algorithm, we're only able to predict the correct bucket about 8% of the time. As a quick reminder, if you guess randomly which bucket a ball is going to go into, you're only going to be accurate 10% of the time. So a random guess is essentially better than doing our k-nearest neighbor algorithm right now. So what that tells me is that equating, or weighting, I should say, our ball bounciness and our drop position equally is probably a very bad idea. In this section, I want to investigate a couple of reasons why that might be, and then I also want to investigate how we could kind of get a better sense in the future whether or not weighting our ball drop position and the ball bounciness is something that we should even think about doing. So let's get to it. All right. So the first thing I want to talk about here we go. So changes to our ball drop position very clearly make changes to our output. In other words, if I drop a ball over here, I'm probably going to see the ball fall into buckets 1, 2, or 3. But if I drop a ball at a very different position, that's definitely going to have a marked impact on our output. Instead, I'll probably get an output of bucket 8, 9, or 10. So not only do we know that a change in the ball drop position makes a change to the output, it also makes predictable changes. So when I go from very low values of the drop position, I know that I'm probably going to end up with a bucket of 0 or 1, 2, or 3. And as I start to get very large values of drop position, I know that I'm probably going to end up with buckets of 8, 9, or 10. Now with the ball bounciness, we have a somewhat similar effect. As we start to change the ball bounciness, we definitely get changes to our output. And you can actually use our tool right here to see that in action. Let's very quickly look at a demo just to prove to ourselves that by changing the ball bounciness, there is an impact on which bucket a ball goes into. I'm going to click the reset button down here at the bottom right-hand side, and then I'm going to go to my range of ball bounciness over here, and I'm going to use start value of 0 and an end value of 0.1 or so. So this is at the very low range of ball bounciness. So with this very not bouncy ball, like essentially a flat or heavy ball, let's now try to drop a bunch of different balls at a single spot. So I'm going to drop 100 at pixel 300. Let's hit drop. Now, when I get the output here, you'll see that the results are mostly concentrated around buckets 4, 5, and 6. Okay, now that we remember that, buckets 4, 5, and 6, let's now change our range of ball bounciness. I'm going to go to 0.9 up to 1.0. I'm then going to do a reset over here, and then I'm going to drop a couple balls again, like so. All right, so before, it looked like most of our balls were centered around bucket 4, 5, or 6. But now we've got a huge concentration around 6, 7, 8, and we have a range from like bucket 2 all the way up to 10. So without a doubt, making a change to the ball bounciness, intuitively, we know that that is going to affect our output. But the changes that are made are not in any way, shape, or form predictable. So even though it is useful information to know the ball bounciness, like we know that it's going to affect the range of values that we might have as an output, it doesn't really aid us in any way to predict what that possible output might be. And in fact, as we just saw by the output over here of 8%, we saw that it's probably quite detrimental to try to think too much about that ball bounciness. So clearly when we start to do our analysis here to try to predict which ball a bucket is going to go into, we might want to not consider the ball bounciness. It looks like we have greater accuracy if we just forget it. Now this entire idea of kind of selectively including some features like our drop position and neglecting or forgetting other features like our ball bounciness is what we refer to as feature selection. So with feature selection, we essentially look at our entire data set and we look at all the different features or types of data that we've recorded. We look at all those different values, and then we might say that for some different features, such as ball bounciness, we'll say, you know what, we probably don't want to consider this feature in our analysis at all. In other cases, such as the drop position, we might want to definitely include it in our analysis, because we know that if we include it, it's probably going to enhance our ability to successfully predict some type of output. With feature selection, we can either do kind of a gut check or a gut feeling, a very subjective way of doing it, which would be for you and I to do more or less what we just did, where we drop a couple balls with different inputs, and then we say, okay, it looks like the ball bounciness isn't very useful. And so we can kind of intuitively or subjectively say, I really don't think ball bounciness is appropriate, let's just forget it. We can also do a more objective analysis. So an objective analysis means that we're going to run some type of analysis or some type of algorithm to try to determine which features are relevant for our analysis. Now, in some different algorithms out there that we can do machine learning with, there are some really great ways to run some analysis and say, okay, here's like the top 5 most important features for predicting some output that I'm trying to figure out. But in the world of k-nearest neighbor, or at least as far as we're going to go, we've got a little bit more straightforward, but kind of, a method that makes sense for doing feature selection in a more analytical or objective fashion. So here's one way that we could do feature selection with our k-nearest neighbor algorithm. We could take our data set and run the k-nearest neighbor algorithm with it, including only our drop position as a feature. So just the drop position by itself, and then run k-nearest neighbor. And then we can record the accuracy of that analysis. And as we had seen previously, we got all the way up to an accuracy of about 30% or so, which was, definitely not great, but definitely better than random. We can then repeat the same analysis, but with a different data set, a data set where we only include our ball bounciness. So notice how now in our data set up here, we've got a ball bounciness of 0.5, 0.52, 0.53, and so on. And then we've got the label right next to it. So bucket 4, bucket 5, bucket 4, bucket 7. So then we can run the k-nearest neighbor analysis again with this, and we might end up with an accuracy of like 10% or even less potentially. And so that means that if we use ball bounciness inside of our k-nearest neighbor algorithm, we're essentially just randomly guessing if we end up with an accuracy of 10%. So essentially, by paring down our feature set and running our k-nearest neighbor algorithm again and again, we can get a better idea of which features we want to include in our analysis and which we might want to entirely forget. Now, we've already kind of seen these results in action. We've seen that only looking at the bucket or at the drop position gives us an accuracy of 30%. We've now very clearly seen that using a drop position, or our bounciness, gives us a very bad accuracy as well. So we've kind of seen this in action, but I want to very quickly kind of code up this solution, where we look at these different factors in isolation. It's just so we can verify for ourselves that yes, using the drop position and omitting the ball bounciness is the right way to go. So let's take a quick pause right here. When we come back to the next section, we're going to modify our code just a little bit to iteratively run our analysis considering different features by themselves. And then we'll eventually end up saying, okay, yeah, we definitely only want to consider our drop position, and we definitely want to omit our bounciness. So quick pause, and we'll tackle that in the next section. In the last section, we spoke about how we can do feature selection with k-nearest neighbor by rerunning our analysis over and over using just one feature at a time. So our job is going to be to modify our code to first run k-nearest neighbor algorithm with only the drop position, and then only the bounciness, and then not pictured in this diagram, but we'll do it as well, only consider the ball position, or excuse me, ball size. All right, so let's get to it. I'm going to flip back over to my code editor, and I'm going to find my run analysis function. So all the changes that we're going to make in this section are all going to be inside of run analysis. We've already done a lot of work around finding an optimal k, and I think that you'll agree with me that I personally found a value of k of 10 to be pretty good. So we're now going to fix the value of k that we're making use of, and we're going to change which feature we are iterating over, or which feature we're selecting at a given time instead. So at the top of this function, I'm going to give myself a little bit of space and then say const k equals 10, like so. So now we're going to reuse a lot of the same code right here, but instead of changing k over time and ranging from 1 to 20, we're going to be changing which feature we are looking at instead. Okay, so the first change I'm going to make here is I'm going to change the range. I'm going to say that we want to range from values of 0 to 3. Remember that the range function is not inclusive. So range is going to produce values of 0, 1, and 2 here. 3 is not going to be included. Then when we do the for each, rather than calling that k, I'm going to call it feature instead. So feature inside this function will be equal to 0, then it's going to be equal to 1, and then 2, like so. And that's going to match up perfectly with our data structure over here, where we want to consider feature at 0, which is drop position, and then bounciness, and then ball size. Okay, I'm going to clean up that comment. I just put it there to make things a little bit more clear. And the next thing I want to do is take where we split up our data set right here and move it into the range. We're going to first select which feature we're picking out at a given time, and then we'll split our data set into 2, and also do our min-max operation. So I'm going to cut that line of code, and then move it into the for each statement, like so. Then on the line above it, I'm going to use a map function on our original outputs array. Remember, outputs has our original data, and I'm going to select just the feature that I care about at any given time out of outputs. So I'm going to make a new variable here called simply data, for lack of a better term. We're going to map over outputs, and for each row, we're going to put together a new row that will be assigned to data. So data is going to have the same structure that you see in this diagram right here. Data is going to have just the drop positions and the label, just the ball bounciness and the label, and just the ball size and the label as well. So for each row, we're going to return a new row. The first entry in that row will be row at feature. Okay, so just a little trick there. Remember, we're iterating over each row at a time. Feature is going to be the number 0, 1, or 2. So we're returning either the ball position, the ball bounciness, or the ball size to make an array of this structure. And then as the second element in this new array that we're returning, I'm going to return the .last entry of the row, which for us is our label. The only reason I'm using the last syntax here, as opposed to doing like row at 3 or something like that, is to avoid having to hard code that index there. Because remember, as much as possible, we try to avoid hard coding references to individual columns or anything like that. Okay, so I'm going to use underscore last row. So I know that this line right here looks a little bit confusing, but all it's doing is looking at outputs and giving us back something that looks exactly like that right there. And then for the next iteration through our ranged loop, it'll give us something that looks like exactly that right there, and same thing for the ball size as well. So now on the next line down, when we split our data set, we don't want to split and run min-max on the outputs array. We want to run that operation on data instead. So rather than outputs right there, we're going to do data. And then I'm also going to change the 3 right there because no longer are we dealing with 3 features. We only have 1 feature. So I'm going to change the 3 to a 1 like so. Now just one more small change we have to make. If you look at our filter function right here, and I'm going to zoom out for a second just to make sure it's visible. So on our filter function, to check our accuracy, we have a hard-coded reference to test point at 3, because previously our label was always at index 3. So I'm going to also use the last syntax there as well, so that we don't have that hard-coded 3. Because in this case, our test point no longer has 4 entries inside of it. It's only got the 2 that you see right here. So I'm going to change this to _.last row, or test point. Okay, so that looks good. Now, very last change, we need to update the log statement down here, because we're not varying over values of k anymore. So I'm going to say for feature of feature, like so. Okay, so that's it. That's the updates to run analysis. I know that these updates to this kind of heavy-duty code here can be kind of hard to follow, but at the end of the day, some of the stuff is not the worst if you have some reasonable programming experience in the past, and we say, oh yeah, we want to run our analysis on a data structure like this where we omit some columns. I'm kind of sure that eventually you would be able to come up with a solution on your own. All right, so that's all we have to do. I'm going to save this file. We're going to take a quick pause. When we come back to the next section, we're going to run this new analysis inside of our browser and see which features give us the greatest accuracy. So quick pause, and I'll see you in just a minute. In the last section, we made a little change to our run analysis function. So now, rather than changing values of k, we are iterating over all the different features we have. Let's now flip back over to our browser. I'm going to refresh this thing, make sure my console is open, and then we'll drop some data points and then run our analysis. So I'm going to again drop 10 balls every 10 pixels, and I'll drop 3 sets of them just so we have a ton of data to work with. So there's 1, there's 2, and there's 3. And then I'll click on Analyze. All right, so there we go. I see that only, there we are. Okay, so there's the third one. Just took a little bit for it to pop up. So for feature 0, that is our ball drop position. So if we consider only our ball drop position by itself, we have an accuracy of 32% with a k value of 10. Now that's not that bad. Remember, our kind of baseline accuracy is 10% because that's the random guess. Now for feature 1, which is our ball bounciness, we have an accuracy of 0.13. And then for our ball size, we have an accuracy of 0.12. Now, something that's very important to keep in mind about the ball size right here is that if you left the defaults in this form, all the ball sizes are identical. So we have a start position of, a starting ball size of 16 and a ending ball size of 16, which means every single ball is equal to 16 pixels. So the fact that we have an accuracy of 12% or 2% above the baseline of 10 is just by chance, totally by luck. And if we reran this analysis a couple more times, we might end up with an accuracy of like 8% instead when we start looking at ball size. Now, given that the ball bounciness of 0.13 right there for our accuracy is so close to the ball size of 0.12, and the ball size is not changing, which means it pretty much cannot be a predictor of what bucket the ball is going to fall into. This is telling me unequivocally that our ball bounciness alone cannot give us any information whatsoever, about which bucket a ball is going to go into. So in this case, I think that by conducting this analysis, we've determined that really the only good predictor on which ball a bucket is going to go into is given by the drop position. And the ball bounciness and the ball size, while they might change the result, they do not allow us to accurately predict the result. There's a difference between the two. Something can affect an output, like, but if it's a dice roll, if it's just a game of chance, well, it's not something that really is going to give us any more information or help us increase any accuracy of our analysis. All right, so this was definitely pretty good. Let's take a quick pause right here, and we'll continue in the next section. At this point, we've really torn apart this Plinko example quite a bit and really investigated the k-nearest neighbor algorithm. In this section, we're going to start to do a little bit of a pivot away from this project and talk about some other things that we're going to start working on as well. So let's get to it. All right, so everything that we've done up to this point in the course has all been about getting an introduction to some very common operations and fundamental concepts that you need to understand in the world of machine learning. So even though we've only covered exactly one machine learning algorithm, k-nearest neighbor, you still have a very solid fundamental base that you can now use to apply many other algorithms as well. So we've learned about the differences between features and labels, splitting up our test and training sets of data. We've spoken about feature normalization and selection, and we've also definitely drilled home quite a number of examples talking about our common data structure of arrays that we use for storing all of our data. Now, at this point, I really consider this to be like the fundamentals, some things that you need to understand for every different example or every different application that you're going to work on around the world of machine learning. So even though it seems like all this stuff might have been very closely related to just that k-nearest neighbor algorithm, in reality, just about every one of these steps is going to be repeated over and over and over again for every other algorithm that you're going to work on. So with that in mind, we're going to now start to pivot a little bit and take these skills we've now developed and look at a couple of other topics. So first thing I want to tell you about is our use of Lodash in this course so far. At this point, we've used Lodash for just about every line of code that we've written. We've used it because it has methods for just about everything that we need to do. Just about every operation you can imagine around working with a collection of data as we have is encapsulated in the Lodash library, which makes it fantastic. It also has a very fantastic API design. All these different methods have very similar interfaces. So for example, you've seen a billion times calling a Lodash function, passing in an array of data, and then passing in a function as the second argument. In addition, learning about Lodash is great because all the skills that you gain with it are transferable easily to other JavaScript projects. Even if you're working on a React.js or Node.js or Angular or whatever it might be project, you can probably make use of Lodash on it. So using Lodash to pick up some of these basic machine learning topics is definitely great. However, it has its downsides. The Lodash library has been very heavily optimized. Don't get me wrong. The authors of the library have spent a tremendous amount of time making sure that every function inside of it runs as fast as possible. However, for our purposes, we need something even faster. When we started to do our end analysis here around these different features, and even when we were doing the analysis earlier on the optimal k value, we definitely saw that some of those operations took a lot of time to run. And without a doubt, a lot of that slowdown was caused by using the Lodash library. In addition, Lodash is not necessarily numbers focused. It's all about working with arrays of arbitrary types of data, not necessarily numbers. So even though it has some functions like multiply, subtract, divide that can be used for doing arithmetic operations, it's definitely not the focus of the library. In addition, some things around Lodash are a little bit awkward. For example, you've seen me point at this diagram many times at this point, and I've said, oh yeah, we need like this column, so to speak, of numbers. And extracting that column right there required us to use a somewhat awkward mapping function, which wasn't super ideal. So even though Lodash has served us very well at this point in time, it's not something that we're going to start to carry into these future algorithms that we're going to work on as well. Moving forward, we're going to start using a different library called TensorFlow.js. Now, the reason that I showed you Lodash to start in this course, rather than just diving straight towards TensorFlow.js, is that they have similar APIs, relatively similar APIs. If you've understood everything that we've done with Lodash so far, you're going to be very well prepared for tackling TensorFlow.js. A lot of the methods very similar in nature. Even the way in which we use TensorFlow.js is very similar to Lodash. Remember with Lodash, we chained on all these method calls like these right here inside of our actual algorithm. We're going to see that we do something extremely similar with TensorFlow as well. So trust me, I showed you some initial implementations using Lodash here for a very good reason. It's going to make the transition over to TensorFlow very straightforward. Now, the next reason that we're going to use TensorFlow is that it's absolutely optimized for fast numeric calculations. You're going to see that once we start to implement algorithms like k-nearest neighbor, they're going to run with TensorFlow significantly faster than if we continue to use Lodash. TensorFlow also has two kind of separate sets of APIs. It has a low-level API for working with numbers, very easy and very straightforward. It also has a higher-level API that makes putting together some more complex machine learning algorithms significantly easier and more straightforward. Finally, and this is one of the big reasons that we're going to be using TensorFlow, is that everything that you learn around TensorFlow.js is going to be very directly transferable to a very popular Python library called NumPy. In the machine learning world, Python is of course used very frequently, and with Python, the NumPy library is absolutely a gold standard. You're going to see in the Python world, the NumPy library gets used on just about every machine learning project out there. Almost every single one, bar none. TensorFlow is built to have a very similar API to NumPy, so as you start to learn TensorFlow, if you ever decide to kind of transfer over to Python for your machine learning needs, you're going to see that a lot of your knowledge carries over quite directly. Now, the downside to using TensorFlow is that it's still in active development. So even though I'm putting out this course after the library has been released for many months now, quite a bit of period of time, you're going to see that over the next couple months, years, the library is going to change just a little bit. Now, having said that, it's my contention that everything that you're going to see change in TensorFlow is not necessarily going to be a breaking change. A vast majority of their API, in my opinion, is going to remain constant from here on out. You're going to see feature additions. You're going to see new methods. You're going to see some new things come into the library. But again, it's kind of my contention that you're not going to see a lot of the core fundamental operations in the library start to change. So even though it's in active development, I think that it's still a pretty safe bet to kind of invest your time in learning right now. Okay, so the wrap up in this section is that we've spent a lot of time talking about some stuff that has seemed very boring, but we've done it for a very good reason. All these basic operations are going to be repeated over and over for every single project that we work on from here on forward. So all these same things we're just going to do over and over and over again. Next up, we're going to start to dump the Lodash library, especially around working with numerical values, and we're going to start to pick up TensorFlow instead. So let's take a quick pause right here. We're going to come back the next the next section, and we're going to start to talk about how we're going to learn TensorFlow. So quick pause, and I'll see you in just a minute. In the last section, we laid out a couple of reasons that we're going to be making use of the TensorFlow library inside the rest of this course. So I now want to give you a quick preview on how we're going to pick up this library. So in the next couple of videos, we're going to get a quick couple lectures to talk about some fundamental concepts around TensorFlow, just to give you an idea of how the library is structured and how it works. Because it will work, even though I said it's similar to Lodash, it is going to work a little bit differently than many other JavaScript libraries that you might have used before. After that, we're going to go through a couple quick exercises with TensorFlow. So this is not necessarily going to be any machine learning algorithms or stuff like that. It's just going to be a couple very small exercises to make sure that you understand how to use the library. After that, we're going to take our k-nearest neighbor algorithm and re-implement it using TensorFlow. So I put the note on here that says, sorry, we have to, because you might be kind of tired of k-nearest neighbor at this point. And you might be thinking like, all right, let's get to business here. Let's learn about some other algorithms. Well, to learn TensorFlow, without a doubt, the easiest way to do it is to re-implement an algorithm that you already know very well. That's going to give you some really good idea of how to effectively use this library. So even though this step right here might end up being very boring, without a doubt, I am convinced this is the right thing to do to learn more about the TensorFlow library. After that, we're going to start to focus on building a lot of different algorithms using TensorFlow.js and really start to see some of its power in action. Now, having taken a look at this diagram and having told you that we're going to rebuild the same algorithm that we've already spent quite a bit of time on, you might have like one or two questions in your head. You might be thinking like, hey, where are all the cool algorithms and cool examples in this course? We've been looking at k-nearest neighbor for quite a while now. Let's get some different examples going on here. You might be also wondering, like, is this really the fastest way to learn all this machine learning stuff? Well, let me give you a clear answer to both these questions. I've taught machine learning in person to many different people at this point, and having taught it to many people and spoken to many people in industry, I've kind of come to a couple of conclusions. The people who learn machine learning the fastest and the people who have success in industry and real life projects applying this stuff are not really the people who understand the absolute inner workings of every last one of these algorithms. Instead, the people who really pick up the stuff quickly are the people who can experiment with these algorithms very quickly because they have an exceptionally strong basis in these fundamental operations. They understand how to split data sets out. They understand how to use a test set to verify the validity of a model. They understand how to do feature normalization. They understand how to do correct feature selection. And they can do all these operations very quickly. When you get good at these basic operations, applying any different algorithm becomes totally trivial. Because it turns out that all these algorithms, at the end of the day, you use them, or the API for making use of them, ends up being pretty darn much the same. So that's my goal in this course. Even though we will spend a lot of time, like a tremendous amount of time, to help you understand some of the inner workings of some of these core fundamental algorithms, don't get me wrong, we are going to do that. My real goal to help you understand machine learning and to help you pick this stuff up and use it effectively is to teach you some of these more boring concepts and make sure that you're really, really, really good at them. Because once you get good at this boring stuff, everything else in the machine learning world starts to be just the same concepts over and over again on repeat. Now, of course, I could have made a course that had just like application after application over and over, just like bam, 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 here's how to like wire up a webcam for image recognition and kind of like, these fun little projects. I could have done that, don't get me wrong. I could have structured the course in that fashion, but I'm 100% convinced that the fastest way to pick up machine learning and understand how to apply it on your own is to learn these more fundamental concepts. So again, I just want to give you, a little bit of a quick talk or some reasoning on why we're spending some time learning some of these more fundamental operations as opposed to just like diving into, hey, here's how to build a recommendation system. Once you learn the fundamental stuff, everything else is totally easy. All right, so now that I've given you a little pep talk, let's take a quick pause right here. In the next section, we're going to start picking up the TensorFlow library. In this section, we're going to start talking about some fundamentals around TensorFlow.js as a library. Let's get to it. All right, so the first thing to understand is the location of all the documentation for TensorFlow that we're going to use. So in a new browser tab, feel free to navigate to js.tensorflow.org. Once here, let me pull it up myself. Oh, there we go. So once here, you're going to see the familiar orange heading at the top. One thing I want to mention right away is that the page that you might be looking at might look completely different from my own. So as I mentioned previously, this project is under active development, and this landing page right here changes pretty darn frequently. At the very top, I'll find API reference, and we'll take a look at some of the API references in here over time. This is a page that we're going to come back to innumerable number of times, and again, it might look different when you take a look at it. But as I said previously, I have great faith that over time, this library is not going to have tremendous breaking changes. You're probably going to mostly see additions or new features added into its API. All right, so a couple more diagrams. Let's get to it. Now, TensorFlow's number one job as it relates to us is to make working with numbers in an array of arrays really, really easy. So what I mean by this is that TensorFlow.js has many different purposes. If you go back over to that documentation page and scroll down the left-hand column, you'll see that there is a tremendous number of objects, functions, and properties that belong to this library. We're going to use a pretty good number of all these, but in general, there's those two sets of the API that I spoke about a little bit earlier. On the one-hand side, there's the low-level linear algebra API, and there's also the kind of higher level that makes it pretty darn easy to make some more advanced machine learning algorithms pretty quickly. So we're going to be mostly sticking to the lower level API, which is mostly concerned with working with straight numbers in arrays of arrays. So as far as you and I are concerned, its number one job is making numbers in arrays of arrays really, really easy to work with. Now I want to continue a little bit and talk a little bit about some very important pieces of terminology. So in this section, we're going to tackle some core pieces of terminology that we're going to be repeating throughout the course over and over and over again. The core unit of work in the TensorFlow library is something called a tensor. A tensor is essentially a JavaScript object that wraps a collection of numbers, and those numbers will be in some type of structure of arrays. What you see here on the screen are all examples of possible tensors. Again, these are going to be arrays that are wrapped inside of a JavaScript object. So they're not just straight arrays, they have a ton of methods and additional pieces of functionality tied to them. Inside of each tensor, we can have an array of arrays that has numbers in each place. We can have a single flat array, or we can have a very deeply nested array. We're going to be talking about tensors nonstop from now to the very end of the course. And we're going to be making use of tensors every single time that we work with TensorFlow. All right, now, big piece of terminology, number 1. We've got 2 big pieces of terminology. This is the first one. The first piece of terminology I want you to be aware of is the word dimensions. Dimensions essentially works in the same way as dimensions around normal arrays work. So if we look at this array over here, or what we might call a tensor, this is a 2-dimensional tensor. In the middle, we have a 1-dimensional, and over here is a 3-dimensional. A very easy way to determine the number of dimensions that a tensor has is to count the number of opening square braces that you see before you see a number. So in this case, where we have an array of arrays, we see opening square brace number 1, opening square brace number 2, and then a number. And so that would be a 2-dimensional tensor. Another way of thinking about these is the number of ways in which these numbers extend into space. So with the 1-dimensional right here, we have numbers spanning from left to right, or just horizontally. So that would be a 1D tensor. Over here with the 2D, we have numbers spanning left to right and top to bottom, or vertically as well. So that would be a 2-dimensional tensor. Now when you just look at this representation of a 3D tensor, it gets a little bit more complicated. So I put together a quick little diagram to help illustrate what a 3-dimensional tensor would look like. So we have a vertical aspect, a horizontal aspect, and then an aspect which goes into the page. Now, throughout this course, we're going to be mostly working with 1D and 2D tensors. You can have any arbitrary number of dimensions that you want, but again, in practice, you and I are going to be mostly restricted to 1D and 2D tensors. So we're going to continue to see that same structure that we spoke about a ton so far throughout this course, where we have a nested array of arrays like this. All right, so that's big piece of terminology number 1. Now we're going to move on to big piece of terminology number 2. So this is the second important piece of terminology, shape. With this shape, we're essentially talking about a metric around a tensor, or a property of a tensor, that describes how many records there are, or how many elements there are in each individual dimension. Now the shape property is something that, again, we're going to talk about a tremendous amount. So we're going to go through a couple of quick examples right now, and then you'll work through a quick quiz that will walk you through a couple of different examples of shape, and you'll get a good idea of exactly what a shape is. All right, so the kind of trick here for determining the shape of a tensor is to imagine calling dot length one time on each dimension from the outside in on a tensor. Now that is kind of hard to stomach, so let's take a look at a couple of examples of this. Okay, so first example right here. So this is going to be our tensor here in the middle. The trick is to imagine calling dot length on every array one time from the outside in. And when I say every array, I mean to say one array for each dimension. So in this case, essentially I'd just say, what is dot length of that? And the answer of dot length for this would be 3. There are 3 records inside of this 1-dimensional tensor. And so it would have a shape of simply 3. Now, by convention, we usually surround this 3 with square braces of its own, so it essentially looks like an array. So for this tensor right here, we would have a shape of simply 3 inside of those square braces. Now let's try the same thing for a 2-dimensional tensor. So again, I would call dot length one time at each dimension. So I'll do a dot length and dot length. And again, we're not actually adding on the dot length or anything like that. That's just a trick for you to understand or determine what a shape is for a particular tensor. So now we would work from the outside in. So one time for this overall array, that would be 2. And then I separate it by a comma. And then I would imagine doing a dot length on this inner array right here. That has 3 elements in it, so I put a 3. And then I would wrap both those dimensions, or both those shape numbers, with a set of square braces like so. Now notice how I did not put an additional length up here. Again, it's one time for each dimension. So the shape of this 2D tensor right here would be 2, 3. Let's try it out one more time for the 3-dimensional tensor. So again, I would imagine doing a dot length, and then a, give me my text, there it is, dot length there as well. And so now in this case, I would go from the outside in. In this outer array, there's one inner array, so I would do a 1. And then in this second array inside, there's one element inside there, so it'd be another 1. And then it would be the length of this innermost array right here. And there's 3 elements inside there. So my shape is 1, 1, 3. All right, so I'm sure this shape property seems a little bit esoteric or kind of strange or irrelevant right now. So let me tell you a little bit about why this is going to be so important. So again, two-dimensional tensors is by far the most common and most important dimension that you and I are going to work with throughout this course. There's a wide variety of different mathematical operations like subtracting, dividing, and so on that we're going to be doing throughout every algorithm that we put together from here on out. And many of these different algorithms are only going to work correctly if we pay attention to, or if we have the appropriate shape for the tensor that we're trying to work with. Now, for right now, that doesn't really make a lot of sense. I don't want to give you an example right now. Suffice it to say, a lot of the work that we're going to be doing is only going to work correctly if we pay attention to and maintain the shape of our different tensors. Now, given that the 2D or two-dimensional tensor is the most important one that we're going to be working with, I want you to understand how to determine the shape of a 2D tensor very quickly and very correctly. So a very easy way to remember this is to just remember row column. Row column, row column, row column. Repeat that to yourself like 100 times right now. When you turn off this video and go to sleep tonight and you're laying there in bed or hammock or however you sleep, I want you to repeat to yourself like 10 times as you're sitting there trying to fall asleep, row column, row column, row column. Just remember row column endlessly, because we're going to be making reference to the shape of this tensor, of 2D tensors, nonstop, and it's always going to follow the same pattern right here, the number of rows and the number of columns. So if we can use that same trick of dot length and dot length, our shape would end up being 1, 2, 3. So the 3 over there. And then for one of these interior arrays, or essentially a row right here, it would be 1, 2, 3, 4. So 4 right there. Now, that's by using this dot length kind of trick or way of remembering this. A more direct way of remembering it is the number of rows, which is 1, 2, 3, and the number of columns. 1, 2, 3, 4. So the shape of this 2D tensor over here is 3, 4. Just remember for these 2D tensors, rows, columns, rows, column, row, column, row, column, over and over and over again. Now, it might sound like I'm making a huge thing about this, and you're probably tired of me saying that, but believe me, there's just so many times in the rest of this course, so many times that I'm going to say to you, remember, we need to make sure that this has, we need to check to remember the number of rows, the number of columns. I'm going to repeat that so many times and you're just going to hate me for it saying that so often. So one more time, memorize this row column. It's the shape of a two-dimensional tensor. All right, so in this section, we spoke about a couple things that probably seem totally irrelevant right now because we don't really have any way of understanding why these are relevant at all. So the first thing we spoke about was a tensor. That is a JavaScript object that wraps arrays of numbers. We then spoke about dimensions, which is talking about essentially how many directions or dimensions that a tensor extends. And then we finally spoke about the shape property. So every tensor has a shape. We can determine it by just kind of imagining this little trick right here where we call progressively dot length on each dimension as we go into the tensor. And just one quick thing to keep in mind, if you are going to use that trick, once you go in a dimension, you only do the dot length one time. So there is no like, oh, I need to do a dot length here and end up with like, 2, 3, 3. That's not a thing. It's just one time at each level of the tensor. All right, so let's take a quick pause right here. In the next section, there's going to be a short little quiz. You're going to get a couple of examples that you're going to solve on your own of determining the dimension and shape of a couple different tensors. So give that a shot. We'll come back to the next section and continue looking at a couple of different aspects of TensorFlow. In the last section, we learned some basic terminology around TensorFlow and tensors. We're now going to start to learn how we actually create tensors using TensorFlow by writing a little bit of code. And we'll very quickly go through a quick example or two to show you how you can use tensors to do some basic arithmetic operations like adding, subtracting, dividing, and so on. So let's get to it. Now I've rigged up this little code editor over here to make use of TensorFlow. As a quick reminder, you can get there by going to myname.github.io JS Playgrounds. And remember, JSP right here are case sensitive. All right, so I'm going to flip back over. I'm going to write out some code on the left-hand side. To get access to the TensorFlow library, all we have to do is write out TF. So TF is a reference to TensorFlow. And the vast majority of different methods that we're going to make use of belong to this TF object right here. To create a tensor, we call tf.tensor, and then we pass in an array of numbers that we want to be used as the data sitting inside the tensor. So for example, I might do 1, 2, 3, like so. I can then take that tensor that's been created and assign it to a variable like data. Now that I have a tensor in the data variable right here, we can call different methods on it. One property that we're going to be very interested in as we go throughout this course is the shape property. The shape property on this data object is identical to the shape property that we spoke about in the last couple of videos. So I can do a data.shape and I'll get back 3, which is the shape of that data right there. I can change the shape of this input array and we would see the output shape change as well. So for example, I can wrap this thing with a outer array. Now its shape is 1, 3 because I have 1 row of data and 3 columns. And so I see the printout over here on the right-hand side that says 1, 3. Cool. I'm going to take this back down to a one-dimensional tensor. So it's just 1, 2, 3. And now I'm going to create a second tensor as well. So I'll say const other data for lack of a better term. And that will also be a tensor with values 4, 5, and 6, like so. Now, some of the most interesting things that we can do with tensors revolve around taking 2 separate tensors and doing mathematical operations on the 2 of them together. So for example, I might call data.add other data. And I see some output over here on the right-hand side. So I took each value inside of the original data tensor, and I added each value from other data. This is what we refer to as an element-wise operation. Let's take a look at a diagram to help you understand exactly what element-wise is. Okay, so on the top here, we have the first tensor of data, and then other data with values 4, 5, and 6 right here. We then added the 2 together, which is an element-wise operation. When we do an element-wise operation, we look at identical indices in both these tensors, and then we do some operation on those 2 individual indices together. We then take the result of that and then stuff it into a new output tensor. So for example, the first index in both tensors is 0, and they have value 1 and 4. So we take values 1 and 4, we add them together, and then we put it into a new output tensor at index 0. We then do the same thing for the next index. So we have 2 plus 5 equals 7, and 3 plus 6 is 9. Notice how there was no kind of like intermingling of values. So 1 was never added to 5, 1 was never added to 6. So when we refer to element-wise operations, we're saying that identical indices in both tensors somehow get added, subtracted, divided, or whatever it is together. And then the output of that operation is stuffed into a brand new tensor. Now that last part is really important. The output of any operation that we do on 2 tensors is always going to be a new tensor. So notice how we've added data and other data together. But if we now reference data, or if we reference other data, you'll see that they still contain the original values of 1, 2, 3, and 4, 5, 6. Those were the original values of data and other data. So every single time we do any type of operation whatsoever on a tensor, the original values never change. Instead, we return a brand new tensor. And we're going to see that occur again and again and again. Okay, so let's look at another example here. So in addition to element-wise addition, we can also do element-wise subtraction. So data.sub would be something that looks like this. We do 1 minus 4 is -3, 2 minus 5 is -3, and 3 minus 6 is -3 as well. And that's the output that we see over here. Now, of course, we can do multiplication and division as well. Multiplication is done with .mul, mul being short for multiply, of course. So as you might guess, that's 1 times 4, 2 times 5, 3 times 6. And then we can do division with .div. That's 0.25, 0.4, and 0.5, the result of dividing 1 by 4, 2 by 5, and 3 by 6. I think you're probably getting the idea at this point. There are many other element-wise operators that we can use, such as less than, greater than, less than equal to, greater than equal to, both, and to do like a logical comparison element-wise, and so on. And we'll end up using a couple of these different operations over time. All right, now the next thing I want to tell you about is some kind of odds and ends around these element-wise operations. If the shapes don't match, then we cannot do these element-wise operations. So for example, we have a shape of 4 and a shape of 3 right here, and there's kind of like this 4 dangling out on the right-hand side. So when we try to do some element-wise subtraction here, well, the second tensor doesn't have a value there, and so that result is undefined. We can very easily see an example of that, where if I add on a 4 up here to the first tensor, I now see an error message down here. Now, one quick thing I want to mention. This right here, saying the shapes don't match and thus we cannot do element-wise operations, is not a hard and fast rule. There are actually some corner cases where we can still do element-wise operations even if the shapes don't match. We're going to take a look at that in the next video in just a second. But for right now, I just want to show you one more quick example. So these element-wise operations also work on multi-dimensional tensors as well. So if we have a 2-dimensional tensor and another 2-dimensional tensor, we can add the two together and get some output as well. Let's do a very quick example with this because honestly, the 2-dimensional operations are what you and I are going to be doing most frequently. So back over here, I'm going to very quickly turn my data tensor into a 2D one. So I'll do 4, 5, 6, and then I'll do the same thing for other data as well. And I'll add in a second row here of 1, 2, and 3. And now you can see that I still get some results with a division operation. I'm going to change that to an add, and I end up with 5, 7, 9, 5, 7, 9. And so that lines up with the diagram right here. So we'd do 1 plus 4 is 5, 2 plus 5, 7, 3 plus 6 is 9, and I think you get the idea. We do the same thing on the second row as well. So the 6, let's do some color coding here, would be added to the 3, and we would get an output of 9 like so. Okay, so basics of adding, subtracting, multiplying different tensors together. Now let's take a quick pause. Like I said just a moment ago, there are some cases where we can actually get these operations to work out, even if the shapes don't quite match. And that's something that we are going to rely upon quite a bit for some of the later algorithms that we're going to take a look at. So let's take a quick pause right here and continue in the next section. In the last section, I had said that you cannot do element-wise operations if tensors do not have shapes that match. But that's not actually a hard and fast rule. And sometimes we can bend the rules a little bit and get two tensors with dissimilar shapes to somehow work together. Let's take a look at a quick example of this inside of our code editor. All right, so I'm going to flip back over here. I'm going to delete everything that I have, and I'm going to recreate data and other data as two tensors with dissimilar shapes. So I'm going to say const data is tf.tensor 1, 2, and 3, and then I'll make other data as tf.tensor with a value of 4, like so. Now, even though the shapes on these things do not match up, I can still do a data.add other data, like so. And I end up with the result of 5, 6, and 7. So in diagram format, we're essentially doing something like this right here. Dissimilar shapes, but we're still allowed to do it. So when we start to do these element-wise operations with two tensors that have different shapes, that's a process referred to as broadcasting. So being able to take this shape 3 and add it with the shape of 1, we refer to that as broadcasting. Let's take a look at some of the rules around broadcasting. So we can only do this broadcasting operation when we go through this process right here. So we take the shape of both those tensors, and then we compare the shapes from right to left. And if the shapes are equal to each other, or one has a value of 1, then we are allowed to do this broadcasting operation. Now this diagram right here, super unclear. It's kind of hard to put this into words, so let's take a look at a quick example or two. Okay, so same operation we just went through. So what we do is we take the shape of both these tensors. So I'm going to represent them in a little box down here, and I'm going to stack them up on top of each other. So the shape of the first tensor was 3, and then the shape of the second tensor was 1, like so. So now starting from the right-hand side and comparing to the left, which doesn't make a lot of sense in this case because they all both have single values, we're going to compare both these values with each other. If they are identical, or one of them is equal to 1, then we are allowed to do this broadcasting operation. So in this case, the two shape values are not equal, but the second one has a value of 1, so broadcasting is allowed. Let's take a look at a couple more examples just so you can get a feel of how this works. Okay, so here's another one, a little bit more complicated. So again, I'm going to represent their shape values in these little boxes. So the first tensor over here has a shape of 2 and 3. And then the second tensor over here has a shape of 2 and 1. So now again, we're going to compare from the right-hand side to the left. We're going to say, is 3 equal to 1? No, but 1 is equal to 1, so we are allowed to do broadcasting so far. Then we move to the next index. Are these two equal to each other? Yes, they are. And so we are allowed to do broadcasting here. Now in this case, we would take this 1, 1 array and we would apply it to this first column, and then the second column, and then the third column. I think that a better term for broadcasting, personally, I don't really think of this as broadcasting. The term that I apply to it in my head is kind of like smear. I say that I'm smearing one tensor over another tensor. So you can kind of imagine if you have like, I don't know, a piece of bubble gum or something. Imagine taking that piece of bubble gum and like slapping it down right here and then forcibly just dragging your hand to smear it over some surface. It's kind of a nasty analogy, but it actually kind of works out. Okay, so in this case, we would end up with values like 0, 3, 1, 4, and 2, and 5, like so. Let's look at one or two more quick examples of broadcasting. Now this one's a little bit more complicated. You'll notice that the dimensions on these don't actually match up. And in addition to that, it's actually kind of hard to imagine how we could take this tensor and smear it in some fashion over this three-dimensional tensor on the left-hand side. But let's go through that rule process again and see if they actually are allowed to do broadcasting. Okay, so the first one has a shape of 2 because we have 2 rows, 3 because we have 3 columns, and 2 because it's of depth 2. And then for our second tensor, we have 3 rows, so 3 right there, and we have 1 column, so a 1. So notice how I took both these shapes, and even though they don't match up in dimension, I kind of smushed them over as far to the right-hand side as possible. And then going from the right hand to the left, we're going to compare the two values with each other. So we have 2 and 1. Well, one of these values is 1, so we're definitely allowed. We're going to move to the left. 3 is equal to 3, so we're allowed. We move over to the left again, and there is no shape value for the second tensor, so we quit. Even though there's no shape value for the second tensor, we are still allowed to do broadcasting here. So if there is no value on one of these different tensors, that's fine. You're still allowed to do the broadcasting as long as all the other values had either equal to each other or one of them was equal to 1. All right, so now one more example where it actually does not quite work out, even though you might think that it should. So now in this case, it kind of makes logical sense that we might take this 1, 1 right here and apply it to like, I don't know, subtract that from like 1 and 4, and then the 2 and 5, and the 3 and 6, and then maybe apply it to each in this second page or the depth dimension as well. So in this case, it kind of makes sense that you would be allowed to do that. But let's go through the same methodology and we'll see what happens. So again, I'm going to record these shapes as 2, 3, and 2. And then I'll do my shape for 2 and 1 like so. So now from the right hand to the left, 2 and 1, well, we have a 1 in there, so we're good to go. But then in the second column right here, we have 3 not equal to 2. So in this case, broadcasting actually would not be allowed, even though it kind of seems like it would make sense. All right, so that's the rules around broadcasting. Now, just so you know, you and I are very rarely going to have to like sit down and kind of like write these shapes out. After a while, you're going to get a sense of whether or not you can actually do these operations given the shapes, and I don't think you're going to have to keep writing things out again and again and again. Let's take a quick pause right here, and we'll continue in the next section, and we're going to start looking at a couple more topics around TensorFlow. At this point, we've spoken about a couple different topics around TensorFlow. There's just a couple more that we need to get through, and then we can get back over to the machine learning side of things. So let's get to it. Now, at this point in time, we've created several different tensors. every time we've been saying something like const data is tf.tensor, and we've put in a set of values, like so. We've then printed out the contents of that tensor by writing out simply data. And then on the right-hand side, you've seen this nice little array-looking representation of the data that sits inside that actual tensor. Now, I said a little bit ago when we first started looking at TensorFlow that these tensors were JavaScript objects. And so even though you're seeing this nice representation of the tensor over here on the right-hand side, that's not really what the data object is. You see, I have rigged up this code editor so that anytime you reference a tensor object here on the left-hand side, it looks into that object, finds the data inside of it, and then prints out a nice representation of it. So what I'm trying to say is that when you start using TensorFlow on your own projects, to get a nice representation like this of the data inside of your tensor is a little bit more challenging than I've made it seem here. Just a tiny bit. Like, don't let me overstate the difficulty here. This is really just a very small technicality that I want you to be aware of. So to give you a better idea of what these tensors actually look like, I'm going to open up my Chrome console, like so. So in this Chrome console, I still have access to the TensorFlow library. I can write out TF, and you're going to see, there it is, there's the library. Now let's try creating a new tensor. Then we're going to try to print it out and just see exactly what it really looks like. So I'm going to say const data is tf.tensor123. Now when I print out data by simply referencing data like so, you're not going to see that nice, pretty array. Instead, you see this ugly looking JavaScript object that has a bunch of different properties inside of it. And you'll notice that among all these different properties, you don't really see anything here that actually indicates what data is inside of it. So when you look at that object definition, you don't really very easily see that 1, 2, 3 that you see over here in this editor. So in order to nicely print out the information that is contained inside of your tensor, you're going to use a different function than you're probably used to using for logging out information. Rather than doing something like a console.log data, we're not going to do that. You can do it, but you're going to log out just that ugly looking object. So instead, you will do data.print, like so. So the print method is how we console log out a nice looking representation of the data inside of our tensor. So when you're working on your own personal projects and you want to figure out what information actually exists inside of your tensor, you're going to use data.print by itself on its own. You're not going to do something like console log data.print. We're not doing that. The print method itself is going to log out this information for you. So you don't have to do this. And I'm going to put no on here just in case you're speeding through this video. Okay, so you can run that, of course, but you're going to get double undefined, or an undefined is what's actually going to be console logged. You do see the actual printout right there, but that's because we did call data.print inside the console log. Okay, so again, just a little technicality I want you to be aware of. The tool that we're using prints out these tensors very nicely. When you're on your own project, you need to call the data.print method instead. Now, with that in mind, let's take a quick pause right here. We're going to continue in the next section, and we're going to talk a little bit more about other ways in which we can access the data that is stored inside of our tensors. So quick pause, and I'll see you in just a minute. In the last section, we spoke about how we can access data inside of our tensor and print it out so that you and I, as developers, can view that data. Now, to be really clear on that, the print method is all about logging out information inside of a tensor. So you're going to use it solely for debugging purposes. You're not going to use it to actually access some element inside of your tensor for the purposes of doing some math on it or something like that, because the print method does not return any data. Now, it does turn out that very frequently we want to access some element inside of our tensor and use it for doing some type of math. So in this section, we're going to figure out how we can programmatically access data inside of our tensor. We're going to learn two different ways. The first way is going to access one individual element. The second way is going to access many elements at a time. So let's get to it. I'm going to first begin by creating another tensor. So I'll say tf.tensor, and I'll give it values like 10, 20, and 30. So as I said many times, we will want to access an individual element inside of this tensor. To do so, I could write out data.get and then pass in the index of the element that I want to retrieve. Notice how we're using the get method here to access data inside of our tensor. Remember, these tensors are not arrays, so you cannot use the classic array-looking syntax. We can't do that. That's not going to return the actual data that we want out of the tensor itself. So instead, anytime we want to access an individual element, we're going to use this get method. Now, anytime that we have a tensor that is one-dimensional, like so, we only have to pass in this singular index. So with these 1D tensors, we have 1D accessors, which means we only have to provide a single index to get an element out. But when we start increasing the dimensionality of our tensor, the get method is going to change just a little bit. So if we have a 2D tensor, we have to pass in two separate arguments. The first argument is going to be the index of the row that we want to retrieve, and then the second argument is going to be the index of the column that we want to retrieve. So let's very quickly do an example of that as well. Back inside my code editor, I'm going to expand my tensor a little bit, and I'm going to give it a second row of data like so. And let's give it some different values as well, 40, 50, and 60. So now you'll notice that even though my tensor is correctly formed right here, I am getting an error message. And it's saying that the number of coordinates that are provided must match the rank or the dimension of the tensor itself. So now that we have a 2D tensor, I have to provide two separate arguments to the get method. So in this case, if I wanted to say get the 10 out of there, I would say give me row 0, column 0, like so. The order of numbers that you pass in to this get method follow that same thing that I told you to memorize just a little bit ago. So the order of coordinates that you provide is always going to follow the same syntax. The first element or the first argument is always going to be the index of the row. The second is the column. This is one of the very many reasons that I tell you to memorize this ordering of row, column, row, column, row, column. There are many more methods and many more places that are going to operate exactly like this, where you have to remember the first argument is the row, the second argument is the column. And you'll notice that, this is not nicely annotated for you. It's not saying something like, give me column 0, row 0. That's not how it works. So you really do have to memorize row, column, row, column, row, column. All right, let's try one or two other numbers inside of here. So let's say that we try to get 50. That's at row 1. So I'll update it to row 1. And it's at column 1. So I'll put in 1 as well. Now I got 50. And if I wanted to say get the 60, I would still be at row 1, but now I would be at column 2. And that gives me these 60. Okay, so that's it. That is how we access individual elements inside of a tensor. Now, one quick thing I want to throw in here is that given that there is a get method, you might be thinking that there is also a method called set. So you might be thinking, okay, so to update values inside of a tensor, maybe there's something called set. And we just call this set function, and maybe we pass in some index that we want to update, and then like a new number to put in there, like 50, with the intent of replacing 10 right there with the number 50. There is no set. We cannot directly set values inside of a tensor. Once you create a tensor, that's it. Tensor has been made, and you cannot modify any of the values inside there. The only way to somehow get a new tensor with a new value at some particular index is to create a new tensor, either by calling tf.tensor or using one of those other arithmetic methods that we looked at just a little bit ago, like the tensor.add, .sub, .mul, and .div, and many others as well. So there is no set, there's no way to modify a single value inside of an existing tensor. You have to create a new one to update an individual value. So just a quick thing I want to throw out there to make sure that's really clear. There is a get, there is no set. All right, so let's take a quick pause right here. When we come back to the next section, we're going to talk about one other way of accessing data inside of a tensor. So quick pause, and I'll see you in just a minute. In the last section, we spoke about how we can access individual elements inside of a tensor by using the get method. We're now going to talk about how we can access many elements at one time using a slightly different method. The slightly different method that we're going to be talking about in this section is going to be one of the ways that we solve a big issue that we had previously when we were making use of Lodash. So remember previously when we were talking about Lodash, we had said that it's kind of awkward to extract just a column of data on its own. So given this array of arrays structure right here, if I wanted to just get the values 300, 350, 416, and 722, that was hard to do with Lodash. But with TensorFlow, it's significantly easier. Now to begin this example, I'm going to add a couple more rows of data onto my tensor. And then I'll fix up some of the formatting and make sure I got commas in there. Okay, so now that I've got all these different rows, let's try to figure out how we can extract just this center column by itself. So So I want to get just the center column and forget about the other two columns that are inside of here. So to do so, I would use the data.slice method. The data.slice method gets called with two separate arguments. Understanding these two separate arguments is a little bit challenging, so let's take a quick look at a diagram to explain how we can use slice to get just this center column. All right, so I've got a diagram of numbers here. Now, I'm going to take off one column here just so that it's identical to the example we're working with over inside of our code editor. So again, we're going to say that we want to get the center column of numbers here, and I'm going to color code it just to make sure it's really clear. So with the slice method, we have to provide two separate arguments. The first argument is going to be an index of the start of the slice that we want to take, or the start of the subset of values that we want to take out of our tensor. So in our case, our starting index for this column right here is row 0, column 1. So inside of an array, I'll put in 0, 1 to indicate row 0, column 1. That is the start of the slice that we are trying to take. Now, the second argument to the slice method is very similar, but slightly different, and different enough for it to be very confusing. Whereas the first argument is an index, the second argument is going to be a size. And the reason that that is so confusing is that size values are not 0 indexed. So of course, whenever we're selecting this very first row right here, we use index of 0. And the first column over here is index of 0. So it always ends up being that our start index right here is 0 indexed. But the size is not going to be 0 indexed because it is a size value. So inside of this size argument, we're going to also provide an array. The first number inside the array is going to indicate the number of rows. So the number of rows we want to use inside of our slice. In our case, the number of rows that we want is 1, 2, 3, 4, 5, 6. So inside of here, I would put in 6. Now the reason that I say that this is confusing, because over here we've got the 0 indexed start, but over here is the size, because you might be thinking, oh, okay, I just need to look at like the index of the last row down here, and then that will be the size. That's not the case. Remember, it's not 0 indexed when we're making use of the size. Then the second value inside this array is going to be how many elements wide our slice is going to be. So in our case, we want to have a width of slice of 1. So I would put in 1, like so. You might be tempted to think that this would be like 0. It's never going to be 0. If you ever put in 0 for any of the size dimensions, you're going to get an empty slice because you are getting a slice of data with 0 elements inside of it. So at a minimum, your size over here is probably going to have a value of 1 for either the first or second dimension. Okay, so now that we've seen this in action, let's try writing out an example back inside of our editor. So back over here, again, I want to try to get that center element. So the index of that is row 0, column 1. And then as a second argument, I'm going to put in a second array, and this is going to describe the size of the slice that we want. Now in our case, we have 1, 2, 3, 4, 5, 6, 7, 8 elements. So the size of the slice is going to be 8, and it's going to be 1 element wide, like so. All right, so now I get back 20, 50, 20, blah, 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 and it goes all the way down to 50. All right, so that's how we do the slice. Now, a couple quick things I want to mention here. If I replace the 1 with the 0, you'll see that I get nothing back because, again, a slice of 0 width has 0 elements inside of it. One other thing that you're going to notice is that this row designation right here of 8 might be sometimes a little bit challenging to put together. Let me tell you why. Back when we were working with the Plinko app, we dropped a tremendous number of balls and recorded observations for each of them. So we ended up with something like 1,500 or even 3,000 different data points. So if we wanted to extract a column on that project, we would have had to add in a number here like, say, 3,000 or whatever it was. Now, it's very rare that you're going to know ahead of time the number of rows that you might have inside of a data set. And so you will very frequently not want to hard code the number of rows here. Instead, you'll want to figure out the number of rows essentially on the fly. Now, one way to approach that problem would be to do a data.slice, or shape. So you could print out the shape of your data. Then the first element inside of that would be the number of rows that you have. So one possible way of making sure that you don't have to hard code, the size of your slice, would be to do a data.shape at 0, like so. Now this is a little bit laborious right here. It's definitely some long-form syntax. I don't personally like how that line reads. So as an alternate way that we can say that we want to take a slice of all the different rows inside of our data set, rather than putting in the number that we want, we can use a shortcut where we instead put in -1, like so. The value -1 is very special. It means essentially give me all of the records that you possibly can in this particular dimension. So in other words, in the row or vertical direction, -1 means give me as many records as you possibly can. One thing that you might want to keep in mind as well is that -1 goes from your start index all the way down to the end. So if I instead use like 4 here, you'll notice that it's only going to go from index 4, like right around, see, 1, 2, 3, 4, or 0, 1, 2, 3, 4, 4 right there. So it's going to start right there and then go down to the very end of the tensor. All right. So you're going to very frequently see that we write code that looks very much like this right here. The only thing that's going to change about this is the index of the column that we want to extract. So when we start to extract columns out of a tensor, it's really just this number right here that's going to be changing. And all the others inside of here are going to be consistent. If I do 0, I can get the first column, second column, third column, like so. Okay, so that is the slice method. Again, one thing to keep in mind here is that the first argument is the start index. The second argument is the size of the slice that we want to get. Let's take a quick pause here, and we'll continue in the next section. I know that we've looked at quite a number of different little examples around TensorFlow, and I'm sure some of these examples are getting a little bit tiring since we're not getting to see really where they get applied. But believe me, as soon as we start working on the k-nearest neighbor algorithm, the TensorFlow version of it, we're going to use every last one of the methods that we've covered so far, and every method that we're going to cover in the next sections as well. So all the stuff I'm showing you right now is 100% immediately applicable to the k-nearest neighbor algorithm and every other algorithm that we're going to put together. Okay, so next thing I want to show you is how we join together two tensors. So let's imagine that we have tensor A and tensor B, and we want to essentially concatenate them together. So I want to take everything in A and everything in B and just join them together. So we end up with some result that looks like what you have over here. Well, this sure doesn't seem like it's that complicated, right? Let's write up a quick example and see if we end up in any hot water or not. So I'm going to first begin by creating tensor A. That'll be TF tensor, and I'm going to give it values 1, 2, 3, 4, 5, 6, like so. And they'll make tensor B. And I'll give this thing 7, 8, 9, 10, 11, 12, like so. Okay, so to join together or concatenate two tensors, pretty straightforward. Tensor A.concat, that's the method we use, and then we pass in tensor B like so. And all right, looks like we've got a result. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But, you know, I'm looking at this, and I'm kind of starting to notice, looking at the structure right here, it doesn't quite look like the same structure that I drew out over here. In fact, if you look at it, it looks like there are 4 separate rows. Let's try printing out the shape of this thing, and then we can really tell for sure. So I'll chain on a dot shape there, and now I see that I have a shape of 4, 3. That means that I have 4 rows and 3 columns. Remember, row, column, row, column, row, column. So rather than having my expected shape of 2 rows and 6 columns, I instead have something that looks like this. So that may or may not be a surprise. Now, who's to say which way is better of joining together or concatenating two tensors? Well, I can't really say. It's kind of tough to say. You know, who knows? Maybe for some reason I want to have two tensors concatenated together in this structure, and then maybe on another problem I want it to look like this instead. Well, it turns out that the concatenate method, or the concat method, has a second argument that you can use to specify which way your tensors will be joined together. So as the second argument to this concat function, we can pass in an integer. In this case, we can pass in either 0 or 1 because we have a 2-dimensional tensor that we are working with. The default argument for this is 0. So if I put in 0, I'm going to get the same result that I had before. But if I put in 1 instead, I'll see that I get a dramatically different result. I get 2 rows and 6 columns. which is this structure that we originally were looking at. So what's the meaning of that second argument, and why does it vary between 0 and 1? Let's take a look at a diagram or two. Okay, so the 0 and 1 refers to the axis of concatenation that you want to use. A number of 0 means axis 0 is going to be used to concatenate together these values. And a value of 1 means, hey, I want to concatenate along the second axis here. Now, even when I tell you that, that might be a little bit surprising, or at least it is for me. So this entire axis system of designating which axes you want to use for concatenation, to me personally, it doesn't make a tremendous amount of sense. The reason for that is that in my mind, when someone says, I'm going to concatenate along axis 1 right here, what I personally picture, and what you might picture as well, is that it's kind of drawing like a sticky line right there, or you're kind of putting like a piece of tape or a piece of glue. And I don't know about you, but I kind of imagine that I'm going to take my second tensor and join these things together along that like big piece of tape or that sticky glue that I put there on the bottom edge. Unfortunately, that's not how this axis system actually works. Instead, the axis system works slightly differently. And here's the picture I use in my head to keep in mind what my axis value means. So when someone says that they're going to do concatenation along axis 1, I imagine that I split up all my columns and I draw arrows along the plane of, or along the direction of axis 1. So I imagine that I kind of put these arrows in here and they're pointing at where the next tensor is going to be. That's how I personally remember this axis system. Again, you don't want to think of the axes as being the concatenation axes, as in like that's where we're joining these things two together. That's not how it works. Instead, you want to think of this as an arrow pointing along this axis to the place we're about to put on this second tensor. Okay, so that is concatenation. Again, just a little tricky thing to keep in mind. So if we put on 0, it's going to stack everything up. 1, it's going to put everything lengthwise, essentially. All right, so let's take another quick pause right here and just a couple more quick sections, getting through this as quickly as we can. So quick break, and I'll see you in just a minute. All right, my friends, one last quick example, and then we're going to go back over to the machine learning side of things and apply all this new knowledge that we have. For this last example, I want to set up a little scenario. So I want you to imagine that you are doing some data analysis for a long jump competition. In the long jump competition, athletes get a running start, they then jump, and whoever can jump the farthest is the winner. So again, I want you to imagine that you're doing a little bit of data analysis for this. In order to do your analysis, you are given two separate tensors of data. The first tensor, on the left-hand side over here, records how far a contestant jumped for each of 3 separate jumps. So this would be attempt number 1, attempt number 2, and attempt number 3. Then in the second tensor is the player or the athlete's identification number, and then their height in centimeters. So in order to do your analysis, you decide that you are going to sum up the total distance that each of these athletes jumped. So you need to take 70 plus 40 plus 73, add those 3 numbers together, and that's going to give you the sum of how far this athlete jumped. And then after you get this new tensor, you're going to concatenate that on to the other 2 columns, and you're going to end up with a 4x3 tensor. That would look like this over here. Now, who knows what you're going to do with this? All I really care about is going through the process of massaging the data a little bit and joining it together. Along the way, we're going to run into 1 or 2 little issues, and we'll have to figure out how to resolve them. So let's get to it. I'm going to flip back over to my editor, and we'll first begin by putting together a little bit of data. I'll say const data is tf.tensor. And you know what, rather than calling this data, let's call this jump data, just to be really clear. And then I'll say 70, 70, 70. We're just going to say that every one of these athletes jumped 70, whatever this is, centimeters, meters, feet, whatever it needs to be, for each of their 3 attempts. So just 70 across the board in a 4x3. Next, we'll put together the player identification numbers and their centimeter heights as well. So we'll say player data is tf tensor. And then I'll do a 1 and 60, and we'll just make everyone more or less the same, but I will update those player data identification numbers like so. Okay, so that's our starting data. So now we need to somehow take each of these 3 columns and sum them together. Now, I'm sure you might be able to think of a couple different ways of doing this. We could probably figure out a way in which we could take slices through this jump data tensor. we could take a slice of column 1, then column 2, then column 3, and then add those 3 slices together. But instead, we're going to use a nice little method that is used to make this process of summing up a tensor or values inside of a tensor a little bit more straightforward. So I'm going to use a method called jumpData.sum, like so. Now when I first call sum, you'll notice that I get a result up here of 840. By default, when you call sum with no arguments, it's going to look at every value inside of your tensor, and it's going to sum them all together, which is not quite what we want. Instead, we want to kind of sum along an axis, very similar to how we were doing concatenation along an axis a little bit ago. So rather than calling sum with no arguments, we're going to instead put an argument in here that designates which axes we want to sum these values along. Now before I tell you what it is, I want you to think back to the example that we spoke about just a couple minutes ago around doing concatenation. And I want you to take a guess as to whether we are going to enter in a axis value of axis 0 or axis 1. Now in this case, we are going to use an axis of 1 because we want to sum in this like arrow direction. So back over here, I'm going to call jumpData.sum, and I'm going to pass in the number 1. And then as a result, I get 210, 210, 210. And that is the result of 70 times 3, 70 times 3, 70 times 3. If we had put in 0 instead, we would have summed along each of these rows, and so we would have eventually taken all these rows and collapsed them up into single values. And we would have ended up with 280, 280, 280. So we definitely want axis 1 here. Okay, so next thing we need to do is concatenate this onto our player data. Well, that definitely seems like it shouldn't be too bad, so I'll call concat on the result of the sum operation, and then I'll pass in player data like so. Now when I call concat here, you'll notice that we immediately get an error message. It says that the rank of the tensors, rank in this case more or less equivalent to the term dimensions that I've been using so far, so the dimensions of these tensors must be the same as the rest. So essentially this error message is saying that our 2 tensors that we're trying to put together here are not of the same dimension or of the same rank. Well, that definitely seems like it's hard to stomach, because although we only have 2 separate columns here, and we have 3 up here, well, it definitely seems like they're both 2-dimensional. So let's take a quick pause here. We'll come back to the next section, and we're going to figure out exactly what's going on. In the last section, we attempted to summarize all of our data inside of the jump data tensor, and then concat the result onto player data. But we very quickly got an error message over here. You might recall that we had previously ran into a little bit of trouble around concat, and we eventually fixed it by designating the axes that we wanted to join our data together on. So maybe this is another case where we have to designate the axes that our concatenation is going to occur on. Let's try putting in a second argument to concat here. We can first try 0. Well, that doesn't fix it. And we can also try 1. And that doesn't fix it as well. So even though maybe this concat option is going to be relevant, maybe it's something we are going to have to do and play around with, it definitely seems like that is not the only thing that is going wrong here. So what's really going on? Well, to begin, I'm going to take this .concat right here, and I'm going to delete it, just so we can do a little bit of exploration. I'm then going to add on a .shape to the end. So when we do the .shape on there, you'll notice something kind of interesting. We get a result shape of simply 4. That means that the summarized jump data is a 1-dimensional tensor, even though the original jump data was a 2-dimensional tensor. And just to prove that to ourselves, we can very quickly do a jump data.shape like so. So essentially, when you call the sum function, it reduces the dimension of the output tensor. So we go from a 2D tensor down to a 1D. When you attempt to concat 2 tensors together, they must be of identical dimensions. So because the result right here is a 1D tensor, and the thing that we want to concat to is a 2D tensor, we are not allowed to concat them together. That's the big issue here. Now to solve this, there are 2 different things we can do. One easy way to fix it, and another way that's slightly more complicated, but is something that's going to work in many other situations where we use functions like sum, functions that kind of reduce dimensions as a side effect of what they do. So the first way that we can very easily fix this is to add in an optional second argument to the sum function. This second argument is referred to as the keep dimension argument. So if you pass in a value of true right there, then when the sum function runs, it's not going to reduce the dimensions of that input tensor. And so as you can see, our output shape over here is now 4, 1. If we then try to replace the shape with a concat, and we concat on player data, we still get an error message, but this is an error message because of that same axes thing that we just spoke about a second ago. So I can very easily put in a 1 like so to make sure that these things attempt to concat themselves along the columns as opposed to the rows. The reason that we're getting the error message there when we're not putting in the 1 is pretty straightforward. If you look at this diagram right here, here, let's actually kind of reshape this thing to what the jump sum actually is. Come on. There we go. So I want you to imagine trying to concat this column of sorts right here, even though it is a 4x1. If you try to concat this thing down onto the bottom of that second tensor, it just doesn't make sense. We have kind of a missing chunk of data here. So the only way in which we can safely concat these things together is when we use a axes of this bottom edge right here. And remember, whenever we talk about these axes things, you want to think about them joining together with these arrows. So we're essentially saying with that axis of 1 that we're going to try to sandwich this thing up like so. All right, so long story there, but the result is if we put in true to the sum function and make sure that we attempt to concat along that row axis or the 1 axis, then we definitely get the result that we wanted, which is rows of 210, 1, and 60. There's the 1 and 60 right there. And then 210 was the result of summing all these 70s together. So that's one way in which we can solve this issue, the issue of the sum function dropping that dimension kind of unintentionally. Now, like I said, that's the easy way to do things. There's another way of doing things that's slightly more complicated, but is far more robust and is going to allow us to kind of fix this issue in cases where we are not using the sum function, but some other function that still inadvertently reduces our dimensions. All right, so to get started with this alternate method, I'm going to delete that concat again, and I'm going to remove that true argument because I don't want to be bound to using the sum function and only learning that way of fixing this dimensional issue. So now as the workaround, I'm going to call expand dims, like so. The expand dimension function does kind of what it sounds like. It increases the dimension of your tensor by 1. So you'll notice our output over here, it now appears that we have a 2D tensor with a single row and 4 columns. And I can very easily verify that by doing a shape. So in fact, yes, I have 1 row and 4 columns. So that's kind of back to how you saw this diagram just a second ago, where I had it like that right there. So we now have that single row. Now that definitely seems like, we're getting to the right place here. We are getting a 2D tensor, but again, as you can see, this thing very clearly doesn't really concatenate up over to the second tensor very well. Those shapes do not match at all. So rather than expanding these dimensions and ending up with a single row, it would be really nice if we could call expand dims and get the thing to put everything into a single column instead. Now a single column, but still a 2-dimensional tensor. So to do so, as you might guess, we can pass an additional argument to expand dims right here, and we can specify the axes that we want to expand our dimensions along. So in this case, I'm going to put a 1 in, and now you'll see that my shape is 4, 1. Which means that we now have 4 rows and a single column. And if I remove the shape, you'll then see the proof of that right there. So by putting in expand dims and saying that we want to expand along the column dimension or the 1 axis, we end up with this shape right here, which is clearly going to marry up against that player data tensor very nicely. Okay, so like I said, this way of doing things, this expand dims function, is definitely more complicated. And even though I've given you a description here and shown you a diagram, you're probably still thinking, how in the world am I going to know when to use this thing? Well, don't worry, we're going to have to end up using expand dims many times throughout this course, so you're going to get a lot of practice working with it and understanding exactly how it works. So to finish up this example, now that I've put the expand dims on here and expanded the jump data sum into the appropriate shape, I can now do my concat. I'll pass in player data. And again, I do have to specify the 1 axis here to make sure that they try to join up on the horizontal direction. And I see the same result I had previously when I tried to pass true as a second argument to sum. So like I said, that's 2 ways to solve the same problem, but whenever we come across this issue, we're almost always going to be making use of the expand dims way of fixing it, just because it's a universal way of fixing issues when our dimensions don't quite line up. All right, so I know these last couple of videos, these last dozen videos or so, have been pretty intense, some pretty heavy duty stuff with TensorFlow. The good news here is that we've learned kind of like the bare minimum to be able to go back over to our k-nearest neighbor algorithm and take another shot at it with TensorFlow. So let's take a quick pause right here. We're going to come back to the next section and start working on a TensorFlow version of k-nearest neighbor. We've now got some pretty good experience under our belts with the TensorFlow library. We're now going to take that knowledge and apply it back to the world of machine learning. I put together a couple steps right here to help you understand how we're going to do that. I want to very quickly discuss these steps because the next series of operations that we're going to go through might be a little bit confusing because we're going to touch on like 2 or 3 or 4 different topics at essentially the same time. So to apply our knowledge that we just picked up around TensorFlow, we're going to first do a quick little example inside of the JS Playgrounds coding tool. We're going to use some fake data, and we're going to use our new knowledge with TensorFlow to implement a slightly different version of the k-nearest neighbor algorithm, slightly different than the one we put together before. After that, we're then going to take that modified algorithm, and we're going to move it over to our code editor for a new project, and we're going to be running this algorithm inside the Node.js environment. And then after that, we're going to do some optimization of that algorithm. So that's the plan. First, inside of JS Playgrounds, we're going to do it just here so you can very quickly see some output and have a good idea of how this data is flowing around. We're then going to move it over to our real code editor in a real project with a real source of data, and then do some optimization. So that's the plan. Well, let's first begin by talking a little bit about the modifications to this KNN algorithm that we're going to make. So before, we had a data source of that Plinko app, and we had said that some balls would be falling down, they would end up in a bucket, and we needed to predict which bucket the ball was going to fall into. So we're now going to make a little change to our data source. Rather than using Plinko, we're going to be working with housing prices. So I want you to imagine for a second that we have a list of data of some locations of properties or locations of houses. We know exactly where the houses sit on a map, and we know exactly how much those houses cost. So all the little black dots that you see in here represent the location of a house with some known monetary value. Like we know exactly how much this house costs. Now, what we want to do is we want to be able to drop a point somewhere on the map, like let's say right there, and we want to say if a new house went up for sale right here, what would that house be valued at? So if we drop the house or the marker right here, and that is a house with like 3 bedrooms, 4 bathrooms, whatever it might be, how much should that house be priced? So that's our goal. That's the change to our data source that we're going to make. Now, when we start to think about this problem, you might notice that there are some significant differences between the Plinko app and this new algorithm that we're talking about, or this new application of k-nearest neighbor. In particular, before we had been saying, which bucket will a ball go into? That was the goal of the Plinko app. That was an exercise in classification. We wanted to classify some output. Our output, the bucket, had only 10 possible values that it could be, bucket 1, 2, 3, 4, 5, and so on. But now we are trying to answer a question of what is the price of a house, given its location or some bedroom and bathroom count and associated variables. And then using that, we want to predict a price. A price is a continuous value. So we can have houses that are worth $200,000 or $200,000 and 1 penny, or $250,000, $350,000, $1 million. So this is going to be an example of a regression problem. So we're going to use essentially the same k-nearest neighbor algorithm, but at that very last step, where before we kind of counted up all these similar buckets that other balls had fallen into, that very last step, this time around, to do this regression, is going to be just a little bit different. So let me very quickly tell you how it's going to be different. All right, so here's the new version of k-nearest neighbor that we're going to put together to do this classification, or excuse me, this regression problem. So our goal is going to be to find the distances between all of our different features and some prediction point. And the prediction point here is going to be maybe like the longitude and latitude of a new house that's going to come up for sale. We're then going to sort those distances from lowest, least to greatest. We're then going to still take the top k records, but then this time around, rather than counting up the number of labels of a particular type, like the number of buckets, instead we're going to take those top k records and we're going to average out the price on each of them. So in other words, if we drop this marker right here and we say that k equals 2, we're going to find the closest two houses, like these two right here. We're going to look at their prices, we're going to average them together, and that would be our guess for the value of this new house that is coming up for sale right here. All right, so that's the general idea. Let's take a quick pause right here, and then we're going to start working on the implementation of this new version of our algorithm in the next section. In the last section, we started talking about how we're going to re-implement our k-nearest neighbor algorithm. But before, when we implemented it, we were doing a classification task. We were trying to guess which bucket a ball would fall into. This time around, we are doing a regression. We are trying to predict a continuous value. Anytime that you're working with predicting dollars and cents or like monetary values, it's almost always going to be a regression problem. So we are doing regression this time around. To change the k-nearest neighbor algorithm to work with regression, that very last step is going to change just a little bit. So rather than totaling up all the different buckets that we have or all the different discrete labels, this time around, we just take the average label value of those top k records. That's the only difference. And by doing so, it's going to give us a regression type prediction as opposed to classification. All right, so a little bit more that I want to talk about, and then we're going to start putting this example together. So we are going to have some fake data that we are working with initially inside of that JS Playground editor over here. So we're going to have fake data. Our fake data is going to have two separate features to describe the properties of every given house. We're going to have the longitude and latitude of a collection of different houses. Every row that you see here represents one single house. So for like house A, we have a longitude of 84, a latitude of 83, and the house price is $200,000. And then the same thing for the next row, and the next row, and the next row, so on. We are going to be given a prediction point. So we can imagine that this prediction point over here is like a new house coming up for sale, and we need to predict how much money that house is worth. So we have the longitude, latitude, house price, and then for the prediction, longitude and latitude. Now with all that in mind, there's one other quick thing that I want to discuss with you. You'll recall that previously, when we worked on that Plinko app, we had an approach of that array of arrays. And in every row of data, we had both our features of drop position, bounciness, and ball size, and our label of the bucket number. So in a single row, all of our data related to one single event or one single record. This time around, we're going to change things up just a little bit. So whereas before, everything was joined together in a single data set with our features and our labels, we're now going to split our features and our labels into two separate data structures. And so effectively, this is going to be tensor number 1, and then we're going to have tensor number 2 for our labels. The reason that we are doing this split here, the reason that we're not just having all of our data sit in a single row together, is that you'll recall with TensorFlow, we're doing those numeric operations like adding, subtracting, dividing, multiplying. And with TensorFlow, those operations are applied to every single element within a tensor. And we have no easy ability to somehow only multiply and divide certain columns and not multiply and divide other columns. So in other words, when we start doing math on these tensors, we don't want to be modifying the values for our labels. The labels are fixed in place. We don't want to change those things whatsoever. And so if we use these TensorFlow operations on a tensor that has all of our data in it, we're going to be accidentally modifying the value of our labels, which again, not something we want to do. In an ideal world, I personally believe that joining these things together into a single data structure makes a lot of sense. It makes a lot of other operations easy, but it's just something that is not, we just can't do very easily using TensorFlow. It's really just not a very good option. Okay, so with that in mind, essentially what we need to do is create some fake data for our features, fake data for our labels. We're then going to implement our k-nearest neighbor algorithm, take those top k records, do an average, and that's pretty much it. So with that in mind, let's take one more quick pause. Next section, we're going to actually implement this thing this time around. So I'll see you in just a minute. All right, my friends, I think we've been talking long enough. It's time to actually start writing some code. Now, we're going to write our initial implementation of this k-nearest neighbor algorithm inside of this JS Playgrounds code editor, just so we can see every step along the way. As a reminder, you can get to that editor by going to this link right here. Don't forget that J, S, and P need to be capitalized. All right, so back over here, the first thing we're going to do is put together a little bit of fake sample data. So we need to create two separate tensors. one tensor is going to store the longitude and latitude for a couple of different make-believe houses, and then the second tensor is going to store the house price for each of those separate properties. Both these tensors are going to be two-dimensional. So I'm going to flip back over, and I'm going to make a new variable here called features. This is going to be a TF tensor, and each row is going to represent the longitude and latitude for one property. So I'll put in longitude and latitude. I'll put in another one. Come on, there we go. And let's do just one more. And 46.7. Now, you'll notice I use some negative values here. Those are totally fine values for longitudes. The reason that I'm using longitudes that look a little bit specific here is that these actually map very closely to the real longitudes and latitudes that we're going to use eventually when we move our algorithm over to our code editor and start using real data. All right, so next up, we need to create another tensor that is going to be a collection of our labels, or in reality, the property values for each of these different houses. So I'll do a labels tensor. This is also going to be 2D, and I'll give it some property values like 200, 250, 215, and how about 240? That's good. Okay, so now one thing to keep in mind here is that the ordering of our labels and the ordering of our features is very important. At the first index of features and the first index of labels, those are two data points that belong to each other. So this 200 right here is the property value of this specific property. That's just something to keep in mind, and it's actually going to be a little bit important later on as we proceed through this algorithm. Now, the last thing I'm going to do here is create a prediction point. So this is the point that we are trying to calculate the property value for. It's going to be a one-dimensional tensor, and I'll give it a longitude and a latitude like so. So now our goal is to use our features and our labels to predict a property value for this prediction point. As a quick reminder of how we do this with the k-nearest neighbor algorithm, step number 1 is to find the distances between that prediction point and all of our separate feature points. Now the distance, as a quick reminder, is just going to be our Pythagorean theorem. So if we want to get the distance between, say, this point right here and this point right here, we would use this equation. So we're going to take the difference in latitudes, square it, and then add that to the squared difference in longitudes. And then we're going to take the square root of the entire thing. So again, this is pretty much the distance that we want right here. That's what we care about. Now you're going to be very surprised at how easy this is to do using TensorFlow. It's going to be almost shockingly easy. I put together a series of diagrams to walk us through each one of these steps to implement that equation over the entire data set. All right, so in this diagram right here, it's a little bit confusing. What I'm trying to communicate is that this step is going to take care of the first operation we need to do, which is to get the difference between the latitudes of all of our observation points and the latitudes of our actual prediction point. And then the same thing for our longitudes as well. So to do this first initial operation of finding the difference in our prediction point and our observations over here for both longitude and latitude, all we have to do is take our tensor of features, and we're going to subtract that prediction point tensor. Remember how the sub method works with the broadcasting feature that we spoke about quite a bit. With broadcasting, we kind of imagine taking this thing and smearing it, so to speak, for lack of a better term. Again, that's how I remember it. And we're going to smear it down, and it's going to do a subtraction difference for each element inside this first tensor by these two elements in the second tensor. So with that single sub method call, we're going to find the difference in all these data points in one single go. So let's try it out. Back over inside my editor, I'll give myself a little bit of space here, and then I'm going to call features.sub, and we're going to subtract our prediction point, like so. And I'm going to new line this because we're going to eventually add on a bunch of chained method calls. Now you'll immediately see some result over here on the right-hand side, and we can very easily do a little bit of validation just to make sure that, yeah, these values actually make sense. So you'll notice that I, in particular, I don't know if you use the same numbers as I did, but you'll notice that my prediction point is at negative 121.47. And my first observation was at negative 121.47. And so I would expect the difference between those two to be 0. And so sure enough, 0, 0 right there. Then for the second point, negative 121 and negative 121.2, Difference between those two is 0.2. Now you'll notice right there we get 0.1999. That's an artifact of floating point calculations, and it's just kind of the reality here. That number is essentially 0.2, which is what I would expect. And then you'll notice the difference between 46.5 and 47 is the negative 0.5 right there as well. Okay, so definitely the subtract right here worked exactly the way we would expect, and we've now found the difference between every single different data point. Now the next thing we need to do is take care of squaring those differences. So we have to square or raise each of those to the power of 2. We haven't actually spoken about doing powers or squaring things or anything like that using TensorFlow, but it's very straightforward. I didn't make a big deal out of it because it's very easy to do. So to take care of that squaring step for each of those, we're going to call the method pow, which is short for power, and we'll pass in 2 because we want to raise each of those to the power of 2. So the pow2 is an element-wise operation. It's going to look at every value inside of our tensor, and it's going to square each of them. And so we're going to square 0.2 to 0.04, 0.5 to 0.25, 0 to 0, and so on. So let's now add that in inside of our code editor as well. So I'll do .pow2. And now all those values have been squared successfully. Now the next thing we need to do is add all those together. So we've got all these terms, they've all been squared, we now need to add them all together. We've definitely gone through this operation before. To add all these things together and kind of condense them down to a single value, we'll use that sum function. Now, don't forget, when we use sum, if you call it without any arguments, it's going to take the sum of every single element inside the tensor and return a single number. And that's not what we want to do here. We want to attempt to sum the values in this tensor across each row. So I want to take 0 and 1, add them together and get 1. I want to take 0.04 and 0.25 and get the 0.29. Remember that if we call sum with 0, that's going to sum the values along our x-axis. So essentially all these values would be condensed down, or you see I said the x-axis, I meant to say the vertical axis. And so that would essentially condense these all down to a single pair of numbers up here at the top. And that's definitely not what we want. So we probably want to do sum with 1 to make sure that we attempt to sum across these rows. So let's give that a shot right now as well. I'll chain on a .sum. Now when I first call sum without any arguments, you see, yep, it got condensed down to a single value. If I call sum with 0, it got condensed down to just the 2 values, which is the sum of each column. Definitely not what we want, so we'll try sum 1. That's looking much better. So we now have a 1D tensor that has 4 elements in it, and that essentially represents this right here. Okay, so that looks good. Now the next thing we're going to do is the square root operation. So out of all the math we've done so far, we need to take the square root on each element. So an element-wise operation again. To do so, we're going to use the pow function again, and we're going to pass in 0.5. Just so you know, taking the square root of something is the same thing as raising it to the power of 0.5. Same thing, not much more to say than that. Okay, so back over here, we'll do .pow with 0.5, and that's taken our square root. Okay, so this is looking pretty good. Let's take a quick pause right here. When we come back to the next section, after having found the distance from our features to our prediction point, we're going to sort these things and then take the average of the top k values. So quick pause and I'll see you in just a minute. In the last section, we managed to get the distances from our features over to our prediction point. Like I said, when you start using TensorFlow, a lot of these operations start to get really, really easy to put together. If we started to write this out using for loops or Lodash or something like that, we would have ended up with a lot more code than what you see right here. Understanding what's happening definitely has a little bit of a barrier, but once you kind of get a sense of TensorFlow, things start to move rather quickly. So now that we have our distances, it's time to move forward. Remember, once we get the distances, we then need to somehow sort from the lowest distance up to the greatest. Or from greatest to lowest, it doesn't really matter, we just need to sort it in some fashion, and then take the k lowest records. I say top on here, that's just assuming that we are sorting from least to greatest. Alright, so sorting. A little bit of a problem here. So there's two big issues that we need to overcome in order to actually sort these distances. The first thing to recall is that if we sort the distances as they stand right now, then the ordering or the pairing to all of our labels is going to be off. So remember, we now have our distances and our labels as separate tensors. If we start to jumble the order of distances in here, then we won't be able to have them to line up nicely with our labels. In other words, if I start to just arbitrarily say, okay, I'm going to move, this distance down here, this one up here, this one here, and that one there, like so, well, now my ordering with my labels is off. Remember, we are relying upon the fact that the indices on both our distances and labels are lining up correctly to get that pairing between them. So if we're going to do that sorting, we need to somehow make sure that we maintain a relationship between these two records. The other issue that's also a rather large issue is the fact that tensors can't be sorted. So in the TensorFlow library, there is no method that is going to sort any numbers or any records for you whatsoever. So we're going to have to figure out some way to cleverly sort the records that are inside of here. All right, so that's the two big issues. Let's take care of the easier one first, which is to make sure that if we start to reorder our distances in any way, they'll still have matching indices to line up with our labels. So to fix that, very easy solution, we're just going to concat these two things together. So we're going to take our distances tensor, we're going to concat it to labels. And so the result is going to be a 2D tensor like so. So we have our distance, right next to it is the label. And so after we sort this thing, hopefully we can sort them like by row. And so if we start to sort it and one ends up down here and the 0.03 ends up here like so, yeah, no problem that we jumbled everything around because we still have that nice association or pairing between our distances and the actual house values, or the labels in this case. So let's try doing the concat first. After we get through the concat, we'll then start to worry about the fact that our tensors cannot be naturally sorted. Now, we spoke about concat just a little bit ago, so I'm sure it's still fresh in your head. So take note of what our data structure looks like right now. You'll notice that it is a 1D tensor, and it looks like it is a shape of 4 and 1, or excuse me, simply 4. So if I do my shape, yep, we got the 4. Now, if we go back up to our labels up here, recall that we set up our labels as a 2D tensor. So we might run into a little bit of an issue, again, like we did previously, around trying to concat two things with very dissimilar shapes. Let's just try to take this on blind faith and try to get these things to match up. So I'll do a concat, and I'm going to concat on labels. And sure enough, as you see right there, yep, these things do not match, so we cannot concat them together. All right, so like I said, we just ran into this a little bit ago. I think it was this diagram right here. So we had said that we cannot concat a 1D tensor up to a 2D tensor. And if we want to do so, we have two options. Remember, we can either pass that true as the second argument to the sum function right there. That's one option. If we pass true as the second argument, that will maintain the dimensions of our tensor and it'll stay as a 2D. The other option, the option that's a little bit more complicated to understand, but it's one that we prefer, is to use the expand dims function instead. And so that's what we're going to use in this case. I'm going to remove that concat line, and then I'll put on that expand dims. Now remember, if we just call expand dims as is, it's going to give us a single row. So this is of shape 1 and 4, because we have 1 row and 4 columns, which is not going to match up nicely with our labels. So instead, we're going to pass a 1 to expand dims to change the axes around which the tensor is going to have its dimensions expanded in. So I'll put in 1 like so, and now we've got that nice 4-1 that we're really looking for. So now we have 4 rows and a single column. And so that's going to match up very nicely with our labels, because that is also 4 rows and 1 column. All right, so we'll do our concat. Now even when we do the concat like so, oh, I've got to pass in the actual tensor, there we go. So even when we do the concat, remember another issue that we saw just a little bit ago as well as we were talking about concat. By default, it's going to join these two things on the column edge. So in other words, we're now in a situation where we basically are like that, which is definitely not what we want. So we need to specify the concatenation axes. Remember the 1 axis, if we pass in 1, that's talking about this bottom edge right here, more or less, or you can think of it as the top edge. And you can really imagine that it's those arrows that are kind of specifying the direction on which everything is going to be joined together. Remember, we just went through, let's see if I can find it. There we go, this diagram right here. So essentially, yep, we want to concat along the 1 axis to get everything to line up together along the kind of right-hand edge is how you would think about this. Okay, so to concat, as a second argument, I'll put in 1, And finally, there we go. So I now see my nice pairs here. I see the 0 to 100, the distance 250, distance 215, and distance 240. All right, so that's definitely looking good. So it looks like we've solved this issue with kind of having our distances and labels get off kilter. Now we need to address the fact that we cannot naturally sort tensors. Let's take a quick pause right here. When we come back to the next section, we'll talk about how we're going to address this. We're now maintaining a relationship between our distances and our labels, even if we end up sorting these values in some fashion. So speaking of sorting, that's what we need to tackle in this section. Our big issue here is that tensors cannot be sorted. There's no function in the TensorFlow library that is going to look at all the values inside of a tensor and somehow sort them in some fashion. So we need to think of some way of working around this issue. To work around the issue, we're going to use a function called unstack. This unstack function belongs to the TensorFlow library. Let's take a look at what the function does, and then you'll very quickly understand how we can use it to actually sort our different values. Okay, so right now we have a big 2D tensor that has two columns in it, a column of all of our distances and a column of all the house values. That is a single tensor, even though it has many rows inside of it. When we call the unstack function on that tensor, it's going to take every single row inside there and create a new tensor out of each individual row. And then out of each of these new tensors, they're all going to be stuffed into a normal JavaScript array. So we're going to get a normal array of a whole bunch of different tensors inside of it. Once all these things are inside of an array, we can then use normal JavaScript functionality that is tied to arrays to sort all the values that are inside of it. Doing the actual sorting operation is going to have its own little set of challenges, but we'll definitely figure that out. So essentially, the goal here is to take our tensor, split it into a bunch of smaller ones, and then sort all those smaller tensors. Let's first flip back over to our code editor. We're going to wire up the unstack function, and then we'll take it from there. All right, so back over here, at the very end of my method chain, I'm going to add on an unstack like so. Now when I call unstack, you'll notice that we get some really ugly output over here. The ugly output that you see right here is all of the individual tensors inside that array. You are seeing this kind of nasty input or output right here just because I did not wire up this tool to intelligently print out tensors that are nested inside of an array. If you want to prove to yourself that there are in fact a bunch of tensors inside of here, you could add on some array index notation. So that's going to pull out the first tensor inside that array. And as you'll see, it is the same value we had before, the 0 to 100. We can then try to get the second element, third and fourth, like so. So again, we now have a normal JavaScript array. Inside of it is a bunch of tensors. So now that we've got the normal JavaScript array, we need to figure out how to sort it, respective of all the different values that are stored inside the tensors inside there. Now to do this actual sorting, we're going to rely upon the built-in sort method that is attached to all JavaScript arrays. If you're not familiar with this method, I put together a quick example here. So imagine that we've got an array of letters like so. They're not currently sorted. We could very easily sort these by just calling letters.sort, like so. And that's pretty much it. It's going to order them all alphabetically. Now, unfortunately, we cannot just call sort on what we have right now and expect that everything is going to work out appropriately. Remember, we have an array of tensors, not simple letters. And so if we call sort on that, JavaScript is going to do its best to sort all those values, but essentially it has no idea what the criteria for sorting is. Let me show you a quick example of what I mean by that. Here's another quick example. I've got this distances array, and inside of it is a bunch of objects, each with a value property. Now, if I call sort on this, no error is going to be thrown. JavaScript will attempt to sort it, but you'll notice that in this case, no sorting actually occurred. No sorting occurred because JavaScript is looking at these objects and it doesn't understand that it needs to look at the value that is assigned to this value property right here. It just does not know to look at this particular number to actually do the calculation. So in order to actually get JavaScript to sort this correctly, we can pass this sort function an optional inner function. So I'm going to do that right now. This inner function gets called with 2 elements out of our array at a time. That we usually refer to these as A and B. So A is going to be some element out of our array. B is going to be another element out of our array. It's then up to us to do some type of comparison between these 2 elements and then return either a value 1 or -1. that 1 or -1 is going to tell the sorting function right here how these two values compare with each other and how they should be sorted. So we're going to do something like return a.value. If this is greater than b.value, then I want to return 1. Otherwise, I want to return -1, like so. Now, if you've never seen this right here before, it's just a normal JavaScript ternary expression. Essentially, it's a very short if statement. We're going to run this expression right here. If it returns true, then we're going to return a 1. Otherwise, we're going to return the -1. So now that I've put in this inner sorting function right here, you'll notice that we are now properly sorting all the objects inside that array. And so this right here is essentially exactly what we have to do on our array of tensors. We have to make sure that the sort function knows how to compare two tensors against each other. All right, so now that we've got a little bit of background here, let's flip back over and we'll do a quick addition of the sort function on here. So I'm going to add on sort. Now you'll notice that we still get this crazy output. Who knows if everything is actually sorted correctly or not? I have no idea. We're going to add on an inner function to this thing that's going to be called with arguments a and b. Now, the example I just gave you a second ago, notice how when we got a and b, we said a.value. The reason we said .value was just to retrieve the number inside of that particular object. This didn't have to be called value. It could have been called, color, for all we care. And I just would have had to make sure that when I did this sorting function down here, I referenced the color property instead. So a very similar token here, we need to make sure that we look into the object A, which is a tensor, and the object B, which is a tensor, and somehow pull our sorting criteria out of there. You might recall that in order to pull out a single number out of a tensor, we can use that get method. Remember, we spoke about that way long ago. So to get the first number out of both A and B, I'll do a.get0. And I'm going to check to see if that is greater than or less than b.get at 0. Now, if this returns a truthy value, then I'm going to return 1. Otherwise, I will return -1, like so. Okay, and that's it. So we've now taught the sort function right here how to look into these tensors and pull out some sorting criteria from them. So now if we do a manual array accessor on here at the end, like so, we should be able to kind of iterate through the entire array and see that all the values inside of it have been properly sorted. So here is 0, and I see 0. That definitely makes sense. Now we'll go to 1. I see the 0.316, 2, 0.538, and 3, 1.16. So those are definitely sorted from least to greatest. Okay, so that's that. We've now got our sorted array of tensors. So now the last thing we have to do is, where's our diagram right here? We need to take those top k records, the k records with the lowest distances, and then we need to somehow average them all out to get our value for our prediction point. So let's take care of those operations in the next section. We've now managed to sort all of our tensors in order of distance to our prediction point. The next thing we have to do is take our top k records and then average the label value for each of those. So let's focus first on just taking our top k records. So back over here, after my sort operation, I'm going to call .slice, like so. Now the slice method that I'm calling right here is not the same slice method that we spoke about a couple sections when we were talking about TensorFlow. Remember, when we call unstack right here, from this point on, we are no longer working directly with a tensor. Instead, we are working with a normal JavaScript array. So we are limited to using normal JavaScript array methods. Sort is a normal JavaScript array method, so is slice. So this is the vanilla array version of the slice method, not the TensorFlow version of slice. If you've never worked with slice before, or if you need a quick refresher, we can do something like distances.slice. We can pass in 0 to indicate our first argument right here, and then we'll put in a number to indicate how many records that we want to pull out of this array. So if we say put in 2 like so, it will give us everything from 0 up to index 2, not including 2. So not including this record right here, only everything before it. And so we would get color at 20 and color at 30, which is exactly what you see over here. All right, so back over here, I'm going to declare a value for k up here. I'm going to use a k of 2. Remember, we only have 4 records total, so it can never be greater than 4. And I'm going to take a slice from 0 to k. Now you'll notice over here on the right-hand side, we still have an array of tensors, but there's now only 2 tensors inside of it. And you could prove that to yourself by doing a dot length on here like so. And yep, we only have 2 tensors now. Okay, so that definitely gets us our top k records. Now the next thing we have to do is somehow pull our label value out of each of these, and then take the average of them. Now remember that in order to take the average of a value, or a collection of values, we sum all the values together, and then we divide them by the number of values that we have. Now at this point, we need to sum these numbers together, but remember, we can no longer use the sum function because we are now working with a JavaScript array. We are not working with a TensorFlow tensor anymore. So we cannot just very easily call sum on this thing. We have to instead work with a normal JavaScript array to actually do the averaging process for us. Now to do the actual averaging, we're going to use a reduce function. If you've never used reduce before, I'm going to give you a very quick example, but this is going to be very abbreviated. So if you want to get more information about reduce, you can of course ask in the Q&A, or you can go and read a couple articles online. There's a ton of content out there about reduce. Okay, so we're going to do the reduce function as a quick reminder on how it works using this sample data over here very quickly. So I'm going to do distances dot reduce. This is going to be called with an inner function that is going to be called with an argument called accumulator, which we usually abbreviate as ACC, and then it's going to be called with each element from inside of this array, one at a time. And I'll refer to that simply as OBJ, short for object. So now from the reduce function, the accumulator argument right here is going to be an initial value that we provide in as a second argument after this function. So I'm going to start off with an initial value of 0. So now the first time that this initial, or this function right here gets called, ACK is going to be equal to 0, and OBJ is going to be equal to the first element in the array. We can then do some logic inside this function, and whatever value returned from it is going to be provided to the next call of this function as the ACK argument. So let's do this really quickly. I'm going to say ACK plus obj.color, and I'm going to make sure to return that, like so. So what I'm doing here is essentially getting the sum of all the color properties across these objects. And as you can see, the sum of all those numbers is 70. I could then very easily come out here after the reduce function and divide by 4, and that would give me the average value of each of these color properties. Okay, so that's essentially what we need to do. The only difference for us is that we are working with tensors rather than these very simple objects that you see right here. So let's flip back over, and we'll try giving this a quick shot. All right, so I'm going to call reduce. I'm going to pass in an arrow function that will be called with an accumulator and my tensor. Now at this point, my tensor has 2 values inside of it. Remember, it's just the individual row by itself that has the distance and the label. And so I'm going to refer to this thing, because it has 2 values inside of it, as simply a pair, like so. So now I'm going to take my accumulator. I'm going to add on the second index from inside of that pair. Remember, real quick here we go right here. At this point in time, the second index inside of that tensor is our label value, or the actual house value in thousands of dollars. So I want to do another accessor to get into this tensor right here and get that second index out of it. So to do so, I'll do ACK plus pair.get at 1, like so. So pair.get1 is going to return the house value. Now as the second argument to the reduce function, let's not forget to put in a 0. I'm then going to close off the reduce function, and then that gives me the total of all of the, right here, all these labels, the top 2 labels. So in this case, it looks like chances are our top 2 labels was 200 and 240 right here. As a quick gut check, we could always change our k value from 2 to 4 instead. That's going to include all these labels right here. And so if you sum all these together, you would get 905. But again, we only want the top 2 records, like so. Okay, so that gave us the sum of all the labels that are closest to our prediction point. So now, after getting the sum, we have to divide by the number of points that we added together to get our average. So after all this, I'm going to add on a divided by k, like so. And that's it. That is our prediction point 220. Now, just as a quick gut check, even though we're using some fake data here, remember we have a house location of negative 121.47. So that was very close to this value right here. And the next one that was probably closest, I think, was probably this one right here, the 120.9 and 46.7. That's much closer than these other 2 points in here. And so this point right here would have had 240. And so if we take the average of 200 and 240, you do in fact get 220. So that would be our guess for the price of a house located at this longitude and latitude. All right, so that's it. That's k-nearest neighbor using TensorFlow. All we had to do was understand how TensorFlow works and then chain together a big string of function calls like so. Now this definitely looks a lot more compact than what we had before for Lodash, when you consider that with Lodash we had to have a lot of extra steps in there where we were extracting columns and kind of working with all that stuff and whatnot. So this is looking pretty good. Let's take a quick pause right here. When we come back to the next section, we're going to start to migrate this code over to our code editor, and we're going to feed in some real housing data to it. So quick pause, and I'll see you in just a minute. We've now put together our k-nearest neighbor algorithm for the purposes of regression rather than classification inside of the JS Playgrounds editor. We're now going to move this thing over to our code editor and run it with a real housing data set, and then do a little bit of optimization and whatnot. So let's get to it. I'm going to first begin by opening up my terminal and finding that Plinko directory that we had previously created by downloading that project. I'm then going to go up one level. And then inside there, so inside of the mlkits project directory, you'll see a folder called knn-tf. This stands for k-nearest neighbor TensorFlow. I'm going to change into that directory, and then I'll start up my code editor inside of here. All right, so inside this folder, you're going to see a couple of different files already inside here. There's an index.js file that is completely empty. You and I are going to end up writing a bunch of code into this file. You'll also see a CSV file. Inside the CSV file is a ton of data about housing purchases. Not only is there the price for all these housing purchases, but you'll also see the number of bedrooms, bathrooms, square footage, and then over here towards the end, the latitude and the longitude for the property as well. So this is the very real data set that we're going to use to try to make some predictions based upon some properties about a new house. If you go down to the bottom, you'll notice that there's 21,000 records in here, so quite a bit of data. Now, in addition to those two files, you'll also see a file called load.csv. This is a file that I put together for us to use that's going to load up all the data inside of that CSV file for us and parse it into a nice ingestible format. Now, just for the first time around, I'm going to give you the contents of this file, but eventually you and I are going to learn how to load up a CSV file from scratch and parse the data inside of it into something that can be very easily used by our TensorFlow algorithms. One of the most basic skills around doing a bunch of machine learning stuff is understanding how to load up data from flat files. CSV files, like the one that you see right here, is absolutely the standard for sharing data sets online. So you're going to see if you start to download new data sets of your own to do some analysis, vast majority of the time, you're going to be downloading them as CSV files. Now, the last two files inside of here are a package lock.json and a package.json file. The package.json file describes some dependencies that we're going to need to put together this project that we're working on. So we need to first begin by making sure that we install these dependencies onto our local system. Now, at this point in time, I'm going to assume that you have Node.js installed on your local machine. If you don't have Node installed, you can download it very easily by going to nodejs.org/en/download, and you can grab a version for your respective operating system. Once you've got that installed, we'll then go back to our project directory of knntf, and we're going to install our dependencies by running npm install, like so. All right, so after a little bit of time, it's going to download the TensorFlow library and install it onto your local machine. So let's take a pause right here. When we come back to the next section, we're going to start migrating our algorithm over to our code editor and wire it up to use all of that very real data. So I'll see you in just a minute. In the last section, we installed some dependencies into our new project directory. We're now going to start to wire these up inside of our index.js file back inside of our code editor. All right, so back over here, I'm going to find my index.js file. So like I said, this is where we are going to be writing the vast majority of code for our project. At the very top, we're going to immediately require the TensorFlow library into this file. I'm going to do so by first writing out require at TensorFlow/tf.js-node, and then after that, I'll say const tf equals require at TensorFlow/tf.js. Okay, so you might be curious why we have two require statements here, and why the second or the first require statement doesn't actually assign a variable or anything to a variable. So the first thing you see right here, the tf.js node, is a version of TensorFlow that instructs TensorFlow where to do calculations. TensorFlow can either use your CPU or your GPU to run calculations on your machine. The version of the library that we're pulling in right here is going to attempt to run calculations on your CPU by default. I'm going to assume that you do not have a GPU installed on your machine. If you do have a GPU installed, you can check the documentation on how to enable your GPU to be used for calculations. Essentially, all you really have to do is add on -GPU like so. And you might have to also install one other library. But again, I'll leave that up to you if you do have a GPU on your machine. The second require statement right here is what actually requires in TensorFlow as a library. So the TF variable right here is the same one that we've been using in our online editor over here. Same TF variable. All right, so the next thing we're going to do inside of here is import that load CSV file. Remember, load CSV is a file that I put together that's going to help us load up our CSV file over here and parse all the data inside of it. So I'm going to call, create a new variable, load CSV, and that's going to be require load CSV. Now, we've already had a lot of experience playing around with TensorFlow quite a bit, so rather than focusing on TensorFlow, let's pivot a little bit and figure out how we can load up a CSV file. I'm going to call load CSV, like so. When we call load CSV, there's a couple of different variables that we need to pass to it. The first is going to be the file name that we want to load up, or the CSV file that we want to load into our program. So the name of our CSV file is kchousedata.csv. Then as a second argument, we're going to pass in a couple of different options. In total, we're going to pass in 4 options. All of these are going to be pretty familiar. The first option we're going to pass in is going to instruct this load CSV module to automatically shuffle all of the CSV data that is coming out of that CSV file. Remember that one of the very core operations we have to do with k-nearest-neighbor is shuffle all the data that's coming in so that we do not accidentally take test set data or training set data from a specific area that might have some type of bias built into it. So I'm going to say shuffle true, like so. And again, all that's going to do is shuffle all the rows of data inside that data set. The next option I'm going to put in is split test. Split test is going to instruct the CSV loader to give us 2 separate sets of data. One is going to be for training purposes, and the other set is going to be for testing purposes. The value that we pass this option right here is the number of records that we want to be put into the test data set. Now for us, we're just going to use a test data set of 10 records, rather small. You'll see why in just a little bit. So now when load CSV is called, we're going to get back 10 records inside of a test set and everything else inside the CSV file. So like all the other 21,603 records in here are going to be assigned to our training set instead. Now 2 more options very quickly. The first one is data columns. This is an array, and we're going to pass in lat and long. The purpose of data columns, well, if you just look at the CSV file for that matter, I'm going to go back over here and go up to the headers at the very top. So inside of here, you'll see that there is a tremendous number of columns, just a ton of data inside this thing. We don't really care about the vast majority of data inside of here. For example, I don't care about the ID of a house. I don't care right now about its date or bedrooms or bathrooms. All I really care for this first iteration is the latitude and longitude of each of these housing properties. We're going to eventually incorporate other columns of data or other features into our k-nearest-neighbor algorithm. For this first run through, we're just going to be comparing houses based upon their physical location in the world. So all we want to extract out of this CSV file is all the latitude and longitude values. So to get just those two values, I specify them here on the data columns property. So when we call load CSV, we're only going to get back the latitude and longitude pieces of data. Now the very last option is label columns. This has the same functionality as data columns, but it instead extracts a single column or multiple columns and assigns them to our labels dataset instead. So in this case, we're trying to predict our price. So the price is our label. And so I'm going to say that for my label columns, I want to extract that price column. All right, so that's it. Now, after we called load CSV, it's going to return back to us an object with a couple of different properties in it. So I'm going to declare some new variables here. Notice how I'm using the let keyword instead of const because we're going to eventually reassign some of these variables. So we're going to destructure out a couple different properties. They are features, labels, test features, and test labels. And I bet you can probably guess what each of these do. Features is going to be the entire data set of just our latitude and longitude, and it's going to be the vast majority of our records, except for 10 that are instead going to be assigned to the test features variable. Labels is going to be price, and test labels is going to be the price for the 10 different records that got assigned to the test features instead. Okay, so now last thing I want to do here very quickly is console log out. Let's just console log test features and test labels and just verify that this data is showing up correctly. So I'm going to console log test features, and then in a separate log, I'll do test labels. So again, I'm going to expect both these to have 10 rows or 10 sets of records inside of them. And each of these features should have their labels or their monetary values assigned to the second variable down there as well. So I'm going to save this, and then I'm going to run it by changing back over to my terminal and running node index.js, like so. Oops. So it looks like I might have made a little typo there. I put TFS. I meant to put TFJS, like so. My mistake. So I can make sure that I update that TFJS like so, and I'll try running node index.js again, and that is looking pretty good. So you'll notice that we've got 10 records right here. That is from our test set. So this is going to be the set of records that we're trying to predict house prices for. And then we've got the second array down here, which is just the house values for each of those 10. Okay, so this looks good. Now, two things that I want to throw out there very quickly. You might notice right here a message that says NAPI is an experimental feature. If you see that, totally okay. No issue whatsoever. You can absolutely no issue with that. You do not have to worry about that message at all. Now, in addition, at the very top, you might also see a message up here that says something like, well, actually, you know what? Let me just show you what you're probably seeing. Okay, there we go. So you might be seeing a message that looks exactly like that right there. Something that says your CPU supports instructions that TensorFlow was not compiled to use. So what this essentially means is that when the authors of TensorFlow compile the project, they make certain assumptions about what features your CPU has. And so when we just downloaded and installed TensorFlow, we got like a very generic baseline version of the library that does not use additional features that your CPU might support. This is done just in case you download TensorFlow on a very basic bare bones machine with a basic, very old CPU that does not support these additional instructions. Now, if you want to, you could always download TensorFlow, the source code for it yourself, and compile it on your own so that this message goes away. But obviously, that's really just not something we even remotely care about right now. Now, you can keep this message from showing up by setting a little environment variable. But again, it's just a message here that really doesn't matter for us. So for the most part, I'm just going to let this message print and not worry about it. And the same for this message down here as well. We're going to just ignore both these messages. They are incredibly unimportant for us right now. Now, if you don't see these messages and you're watching this video at some point in the future, hey, that's great, totally fine. I guess they removed the messages, no problem whatsoever. All right, so it looks like we are successfully loading up some data out of our CSV. So let's take a quick pause right here. We're going to come back to the next section and move all the code from our k-nearest neighbor algorithm over to our code editor, and then start running this thing. So quick break, and I'll see you in just a minute. In the last section, we successfully loaded some data out of a CSV file. So now that we've got some data here, we can start to run our k-nearest neighbor algorithm on it, and then start doing some analysis and trying to tweak our algorithm a little bit. So to get started, I'm going to go back over to my editor over here, and I'm going to take this entire block of code, everything from features all the way down to reduce, and I'm going to copy this thing. I'll then go back over to my editor, and then right underneath our require statements, I'm going to create a new function called knn. And then I'm going to paste all of that code inside there. All right, so that looks good. Now we do have to make sure that this thing gets called with a couple of arguments, and we need to make sure that we return the result of this calculation as well. So I'm going to make sure I get a return keyword in there. And then I'm also going to assign a number of arguments to the knn function. The first argument we're going to take into this thing is going to be our feature data set. So that's going to be an argument that I'll call features. Next up, we're going to get all of our different labels. Remember, that's going to be the house prices. We'll then get our prediction point. So that's going to be the longitude and latitude that we are trying to make a calculation or an estimation for. And then finally, I'll put it in the value of k that I want to use on here at the end as well. All right, so I think that all of our variable names match up, and I would encourage you to double check and make sure that you use the same variable names as me, because if you did not, then you're going to very quickly see an error message. So I should see features, features, labels, labels, prediction point, and k up here, and k down here, and k in the slice as well. All right, so that's looking pretty good. So now that we've got this put together, I'm going to go back down to the bottom of the file, and we're going to try to call the knn method just one time and make sure that we can actually get some output from it. So I'm going to create a new variable called const result, and that's going to be the result of calling knn. And we need to pass in our features, our labels, one of our single test features, and then a value of k. Before we do so, quick reminder, features, labels, test features, and test labels right here are all plain arrays right now. They have not been inserted into a TensorFlow tensor just yet. So we need to make sure that we convert each of these arrays of data into a tensor and then pass them into the k-nearest neighbor algorithm. I made a very conscious decision not to have load_CSV right here return tensors, because load_CSV is kind of singular in purpose. It's just about loading up a CSV and then doing a tiny bit of pre-processing on that data, like shuffling it or splitting it into separate data sets. And so after you load up this data and get back these arrays of arrays right here, then we have to insert them into TensorFlow tensors. Okay, so right after that, I'll do features is tf.tensor. I'll put in my features. Labels is tf_tensor. Labels, let's get the spelling right. tf_tensor labels. Test features is tf_tensor test features. And test any labels is test labels, like so. Okay, so that looks good. So now we're going to pass in features. We're going to pass in all of our labels. And then, I just realized we don't really want to put all of our test features into a tensor, because remember, when we pass our test features off to our algorithm, we really want to pass in just one pair of data at a time. It's like a single row. So rather than taking all of our features and putting them into a tensor, and the same thing for our labels, I think that instead it would probably make a little bit more sense to just reference test features, taking the first row out of it, and then putting just that first row into a tensor. So I'll do tf.tensor like so. We're going to eventually come back and make this a little bit more robust than that and make sure that it will run over our entire test set. But for right now, we'll just stick with this kind of janky looking code. And then finally, I want to put in a k value. I'm just going to guess a k value of 10 for right now. So then the last thing to do is to console log our guess, which is going to be result. And then I also want to see what the actual value of this property is. The actual value of the property is stored inside of test labels. And so I'm going to reference test labels. I'm going to get the first row out of there with 0. Remember, I'm getting the first row here because I'm just arbitrarily using the first row of test features. And then inside of that first row, I want to get the number value out of it. So I'm going to put another 0 right there. Test labels is also an array of arrays. So again, get the row and then get the dollar value out of there. All right, so I think we're ready to give this a quick test. I'm going to save this file, and I'll flip back over to my terminal and do another node index.js. All right, so you're going to very quickly see that running the k-nearest neighbor algorithm on this very large data set actually takes a pretty good amount of time. Now, hidden in all these kind of annoying messages that we just discussed, you'll see the result of our calculation. So we guessed that a house at that first test location coordinate would be worth 1.4 million, but in reality, it was only worth $1.08 million. So I would say that we are pretty far off the mark at this point. Let's take a quick pause right here. When we come back in the next section, we're going to expand our code right here and run k-nearest neighbor over our entire test set. And after we do that, we'll start to evaluate our results and see if all these estimates are as bad as this one is right here. And then we'll start to figure out how we can tweak our analysis and get some better results than what we have. So quick pause and I'll see you in just a minute. In the last section, we ran our first iteration of the KNN algorithm. We did not get a very good result. We guessed 1.4 million, but in reality, the property was only worth 1 million. So we were about $400,000 off, which is definitely not good at all. Now, to get better at this, the first thing we need to do is figure out some way of evaluating how good or how bad any one of our guesses is. Having just the raw numbers print up here like so is not super helpful because you have to do a little bit of math in your head and say, okay, 1.4 million, and heck, I've been saying 1 million. That actually rounds closer to 1.1 million. And you got to subtract the two from each other and then somehow say whether or not you're happy with that result. So rather than doing this kind of hard guess right here, or hard estimation, we're going to instead report our error, or kind of our accuracy, using this formula. We're going to take our expected value, which is really our value of the label itself, and then we're going to subtract from it the predicted value, and then divide by the expected value. That's going to give us a percentage that we can then use to say, okay, we were like 10% off or 20% off, 30% off. It's a value that's going to be much more easy for us to understand and parse. So let's implement this very quickly inside of our code editor. So rather than doing that straight console log right there, I'm going to do a const err, that's short for error. I'm calling it error like so because in JavaScript, error like so is a protected keyword. So we're going to do just error like so as an abbreviation. Then our accuracy guess is going to be test labels at 0, 0 minus our result. I'm going to put some parentheses in here and then divide by test labels 0, 0. So then we'll report our error as error, like so. So let's now try this and see what percentage we end up with. Okay, so I'm going to run it again. It's going to take a couple seconds to get through the calculation, and then I see a value of negative 309, like so. Now I said this was a percentage. To actually turn this into a normal looking percentage, we would multiply it by 100, and that would give us our real percentage. So in this case, if we multiply this value by 100, we would end up with negative 30.9, or essentially negative 31%. That means that our guess is 31% above what the accepted value for this thing is. So we're definitely pretty far off here with a 30% accuracy rating. I'm going to very quickly multiply that value by 100 as well, so that we get a percentage value instead. So now when I rerun it again, yep, okay, there we go, a better looking percentage value. So now at least we have a percent that we can use to very fairly compare different calculations and different analyses that we run. Now, only running one analysis at a time isn't very good. It could be that, this is just one very weird property, and there might be many other properties out there that do a much better job of giving us a fair estimate. So let's try refactoring our code here. And rather than always hard coding in a single run of our KNN algorithm with the first test feature we have, we're going to instead loop over all of our test features. And once we loop over all of them, we'll then print out the result for each individual one. So we can say with definite certainty whether our guesses are way off across the board, or maybe this one test feature was just a little bit strange. So to do so, I'm going to loop over my test features array. Remember, test features is an array of arrays. It is not yet a tensor. So I'm going to do test features dot for each. And then for each of those, I'll take my test point, and I'm going to essentially just move all this logic directly in there like so. Now we got to do a little bit of refactoring here. So first off, when we call KNN, we're no longer passing in just test features at 0. Instead, we're going to pass in the current test point that we're looking at. Next up, when we do our error calculation right here, we do not want to hard code in test labels at 0. Instead, we need to look at the correct index of test labels, pull out that correct index, and then get the first number out of there, which is the actual dollar value. So in order to access the correct index, I'm going to add on an argument to my for each right here. After test point, I'm going to get my variable I. I is the counter. It reports the index of the test point that we're currently looking at. So then inside of test labels, I'll say test labels at I, and over here, test labels at I. So now we're looking at the correct row of test labels when we're trying to determine whether or not we got a reasonable guess out of our KNN algorithm. Okay, so let's now save this and rerun it again and see how we're doing across these 10 different test samples that we pulled out. All right, so I'll flip back over. I'm going to rerun this. Now this analysis is going to take just a little bit of time. Again, we've got a tremendous amount of data here that we're working through. We're going to eventually spend a lot of time working over some optimization of our algorithms, and I'm going to show you some methods that we can use to do optimization analysis and performance analysis in Node. That's going to significantly speed up some other algorithms we work on. But for this first algorithm, k-nearest neighbor, we're not going to worry about doing any fancy analysis just yet, or any fancy optimization. Okay, so after a little bit of time, we see the error for those top 10 samples we looked at, or the first 10. If you look across the board here, it looks like we are definitely a little bit above quite frequently, and there's only one case where we guessed below. So it looks like maybe using the longitude and latitude, in some cases we were like 6 to 10% off. So maybe this is not the worst method, but it definitely appears like there is more to predicting housing prices than just the longitude and latitude of a property. So let's take another quick break right here. When we come back to the next section, we're going to take a look at some of the other properties that we have access to. We're going to see if we can't somehow enhance the accuracy of our KNN algorithm. So quick pause, and I'll see you in just a minute. In the last section, we ran our analysis for a variety of test points, but we saw some pretty disappointing results. Across the board, we were off by a pretty good amount for every single guess. And so I think it's safe to say that only looking at the latitude and longitude alone for our analysis is probably not going to cut it. And we could probably get a more accurate analysis if we start to include some other features. Now, the first feature that I want to try to add in here is the square foot lot feature. Square foot lot tells us exactly how much property is associated with each of these different houses. It's reported in the size of square footage of the lot, or essentially the space that the house is sitting on. And so I would argue that if you have a large lot or a large property, you're probably going to end up paying more. And so I think that this might be a valuable signal or feature to include in our analysis. In order to add in the square foot lot to our analysis, all we have to do is find that load CSV function right here. I'm going to find data columns, and I'm going to add in square foot lot as an additional column that needs to be created by the load CSV function. And that's pretty much all we have to do. So now when we get back our features, it's also going to include this square foot lot column. We don't have to make any other changes to our code inside of here because we wrote it to work irrespective of the number of features that we throw at it. So that's pretty nice. Now before we go and pat ourselves on the back too much, I want to remind you about one little problem that we had ran into back when we were working on that Plinko application. Recall that when we were working on the Plinko application, we had the values of drop position and bounciness. And we had eventually ended up saying that the value or the range of values of the drop position far, far, far outweighed the range of values for our bounciness. We saw that given the fact that we're calculating a distance here, a change in drop position meant way, way more than a change in our bounciness. And so eventually to address this, we looked into normalization and standardization of our data set. Now, we need to think about whether or not that is something that we need to do this time around as well. Well, let's go look at a couple different values inside of that CSV file. Now, navigating this file can be a little bit challenging. I personally have a little extension installed into my code editor that allows me to take a CSV file and print it in a nice table. So if you are using Visual Studio Code, you can install this as well. I believe it is called, which one is it? Excel Viewer. That's what I'm using. So if you install that little extension, you can essentially take a CSV file and open it in this preview mode that allows you to look at the data inside of here very easily. If you're not using Visual Studio Code, you can always open up that CSV file in Microsoft Excel or OS X numbers application. All right, so inside of here, I'm going to find that square foot lot. And here it is right here. It looks like we've got values around like 10,000, 700, 1100, 954, definitely in the thousands range, without a doubt. Now, if I scroll over and look at latitude and longitude, you'll notice how the range of values here, they are around 47, and it's all like 47.6 or 0.5 or 0.7. So the range of latitude values here is like 0.2. That's like the total range of values, change in values that we're seeing here. And it's the same thing with the longitude as well. And so without a doubt, I think that we're running into the same issue that we were running into before, where we would have one metric, the lot size, that far, far, far outweighs the actual longitude and latitude of the house. So I think that this is going to be another candidate or another place where we're going to want to do some scaling of our data. Now, the question quickly becomes, do we want to do normalization or standardization? Well, let's think about this for a second. In the case of the drop position that we were working on before, we knew that we always had ball drops that were pretty well distributed between 0 and 600. This diagram right here shows 300, but you and I know that it was always falling between about 0 and 600 or so. And so in the case of normalization, when we normalized our data, we got a pretty fair distribution of values between 0 and 1. But this time around, we're talking about doing normalization on a completely different metric. In this case, it is our square foot lot. Now for the square foot lot, I'm going to sort this really quickly, and then I'm going to go up to the lowest value right here, 520, and then I'm going to go down to the greatest value at the bottom, and you'll see that is like a mind-boggling 1,000 or 1 million. Is that 1 million? Yeah, 1,651,000 square feet. Now, as I start to look at some lesser values, you'll see that if within like 20 or 30 records, it drops all the way down to 400,000. And so this is a case where we have a kind of a normal distribution of data. In other words, a lot of our values are clustered around some like average value that we could find at the very middle of our spreadsheet, like right around here. But then there are some values that are just way, way, way off the scale large. So if we started to do a min-max analysis on this, we might end up in a scenario that looks like this right here. So if we do the min-max through normalization, we could end up where the vast majority of our values are clustered around like, maybe 0.2 or something like that right here. And then because of those very, very few properties that we saw, like the property that was 1.4 million square foot, we would have some values out here that were all the way at 1, and then like this huge, huge gap. So this is a case where I feel like normalizing our data with that min-max method might not give us a very good result. Instead, we're going to try to use standardization. So remember, with standardization, our values are going to range from -1 standard deviation to 1 standard deviation, with the average value falling at around 0. The reason that we're going to use standardization here is that it accounts for some very extreme values much more nicely than normalization does. You can kind of imagine that if we have some point that we're trying to predict, and it falls like right here or so, we're going to include that incredibly large square foot lot in our analysis or in our final average value. This one lot out here might have like a ridiculous price associated with it. And so if we have, even a value that's sitting like right here, or excuse me, not that far over, but like, right there or so, it might be very close to some of these lower priced houses that are maybe like $1 million or so, but we might erroneously try to pull in this extremely large lot that is going to be something like, 1.4, 1.5, or excuse me, like 15 or 20 or 30 million or something like that. So it might end up throwing off our analysis. If we instead end up with it like, right here or however, then maybe we're still going to include that property in there, but maybe there are more values around one standard deviation that's going to kind of keep us in reality, rather than including that very, very extreme case out there. All right, so I think that we're going to use standardization to normalize our data set, or to kind of address this data imbalance that we have. Let's take a quick pause right here, and we're going to implement standardization in the next section. In the last section, we spoke about how standardization is probably going to solve our number imbalance problem a little bit better than normalization is. So in this section, we're going to start to walk through the process of doing standardization using TensorFlow. All right, so here's our formula. This is how we are going to normalize, or standardize, each of our different features. We're going to first calculate our average for a given feature. We're then going to calculate the standard deviation for a feature. And then for every value in that feature, we're going to subtract the average and divide by the standard deviation. Now, calculating the average is pretty easy and straightforward. Calculating a standard deviation is definitely a little bit more challenging, but luckily TensorFlow has a built-in function that is going to make all this stuff pretty easy and straightforward. To give you a quick example, I put together a little 2D tensor over here in my editor. So I've got numbers 1, 2, 3, 4, 5, and 6. We're going to imagine that maybe this first column right here is our longitude, and the second one maybe is our square foot lot size, or something like that. Now, when we start to apply that standard deviation, or that standardization formula right here, one thing that I want to make sure is really, really clear, very much like the min-max formula that we applied before, we are applying that standardization formula on a per column or per feature basis. So we need to calculate the mean and the standard deviation for column 1, and the mean and standard deviation for column 2. And then we're going to adjust all the numbers in each column by their respective standard deviation and standard means. All right, so first things first though, let's first figure out how we're going to calculate our mean and our standard deviation. So I'm going to reference a function called tf.moments, like so. Now, I want you to take notice here, this is one of the only times that we've seen so far where we are calling a function directly from the TensorFlow library. So the moments function is not a property of a tensor. We cannot call numbers.moments. That is not a function. You'll even see over here it says numbers.moments is not a function. So when we want to get our average and our standard deviation, we do tf.moments. And then we pass in, as the first argument, the tensor that we want to calculate this stuff for. So in my case, it's going to be numbers, like so. Now, as a result, we get two kind of nasty looking properties coming back. First, note how we get an object. The object has a property mean and a property called variance. So I'm going to destructure both those, and we'll talk about what they are. All right, so first off, the mean. The mean is just another name for the average. So that's basically the same exact number that we want to stick into this formula right here for average. But you'll notice that we got something called a variance. We did not get something called a standard deviation. Well, a variance has a very, very close relationship to a standard deviation. In fact, the relation between the two is the square root of the variance. So if you take the square root of a variance, that gives you the standard deviation. So even though we do not get directly the standard deviation, we can very easily calculate it by just taking the square root of the variance. So with that in mind, let's take a look at the value of mean and the value of variance. So first I'm going to print out mean, and then I'll print out variance, like so. And when I get these results right here, I want you to notice that something might, and hopefully something seems a little bit off. I had told you just a second ago that we need to calculate two separate means and two separate standard deviations, one each for column 1 and one for column 2. But when we just did this calculation, we got the mean and variance, and they are single numbers. So we need to somehow take like a single number and apply it to both columns? No, not quite. Well, it turns out that this tf_moments function works the same exact way as the sum function does that we looked at a little bit ago. Remember, when we call sum by default, it's going to give us the sum of a tensor using all the values inside there. And if we want to sum in a certain direction, we have to pass in an axis. So if I pass in 0 like so, I'm going to get the sum of all the rows kind of stacking up together. If I do 1, I'm going to get all the columns being smushed together. So same exact thing with this tf_moments function. We have to pass in a second argument that is going to be the axes that is going to be used for the calculation of the mean and the variance. I want to first show you 1. If I do 1, I get back 3 separate values. And so as you might guess, 1 is going to calculate the mean and the variance for each row. So we're basically going from left to right. So the average of 1 and 2 is 1.5, the average of 3 and 4, 3.5, and so on. So in this case, we probably do not want to do the moments on the 1 axis. Instead, we want to run it on the 0 axis. So now we get 2 numbers for the mean, and we get 2 numbers for the variance. So in this case, the 3 is going to be the mean or the average for column 1, and the 4 is the average for column 2, which is definitely what we want. So we now have a mean and a variance for each column inside of our tensor right here. So now the last thing I want to do is apply the mean and the variance to this numbers tensor and make sure that we can actually run this formula back over here and standardize all the values. All right, so let's give this a shot. We're going to start off by doing numbers. We're going to subtract the mean or subtract the average. So I'll do dot sub mean. And then I'm going to first take the square root of the variance and then divide everything else by that. So I'm going to divide by variance.pow 0.5. Remember, I mentioned this a little bit ago, but taking something to a power of 0.5 is the same thing as taking a square root. And as I mentioned just a second ago, the relationship between standard deviation and variance is you take the square root of the variance, and that gives you the standard deviation. Okay, so we take the square root of the variance, and then we divide all that other stuff by that standard deviation. And so now we can see our values up here. So we end up with a -122, so that would be for that index right there. Then for the 3 right here, we have a standardized value of 0, and then we have a +122 for the 5. Remember, this is going to reassign all these numbers, or kind of scale the numbers, so to speak, from, where is it? Here we go. -1 standard deviation to +1 standard deviation. So by looking at these numbers right here, that means that 122 is our standard deviation. Negative standard deviation, or excuse me, -122 is going to be the far left-hand side of the scale, and the +122 is going to be the far right-hand side. Okay, so that's pretty much it. That's how we standardize our numbers using TensorFlow. Like I said, calculating some of these things can be a little bit challenging when you look at the original formulas, but when you start to make use of TensorFlow, doing this stuff is just really straightforward. You just have to understand how to call these different functions and the confusing things like these axes. All right, so let's take a quick pause right here, and then we'll come back to the next section, and we're going to implement all of this standardization stuff. In the last section, we walked through the process of implementing standardization. So we're now going to flip back over to our code editor, and we're going to update our KNN algorithm to make use of standardization. We're going to do the standardization step directly inside of the KNN function. So up here at the top of the function, I'm going to first take the moments on our incoming features tensor. So I'm going to say const mean and variance is tf.moments on features along the 0 axis. Don't forget to get the 0 on there. Then after that, we need to first remember to do one quick thing. Remember, we get this prediction point right here. We have to apply all this scaling and standardization stuff to the prediction point as well, so that all these different values of features that we're working with are all on the same consistent scale. So I'm going to make a new variable right here called scaled prediction. And that's going to be my prediction sub the mean divided by my variance to the 0.5 power. And remember, the 0.5 power right here is a square root operation. Now that I've got the scaled prediction, I'm going to make sure that I substitute the prediction point that we had passed down here with scaled prediction. Okay, so we've taken care of scaling the prediction. Now we need to make sure that we scale our features, or standardize our features as well. So right after we reference features right here, I'm going to subtract the mean, and then I'll divide by the variance.pow 0.5 like so. So essentially, we're going to do that standardization step, and then immediately after that, we're going to go into the distance calculation right here, and then we'll start to do all those other operations as a part of the k-nearest neighbor algorithm. Okay, so that's pretty much it. That's all we have to do to implement standardization. Really not that bad. So I'm going to save this file, and then we're going to run our analysis again and see if we can get some better results than what we had before. So back at my terminal, I'm going to do a node index.js. Oops, looks like I made a little typo in there. What did I spell wrong? Prediction point, not just prediction. Prediction point. I've got notes on the code that we write here, and vast majority of the time between my notes and actually writing the stuff in the video, I very, very frequently relabel variables or rename them on the fly, and then sometimes I just forget to use the rename variable, so my mistake there. Okay, so we got that fixed up. Let's try this again. Okay, so now it's running, and remember, it takes just a little bit of time to get through this stuff. One thing I want to mention is that we're now running that mean and variance calculation on our data set for every single value that we're taking into account here. So in other words, we're running it for every single one of our test features. And so this is yet another location where we could possibly do some optimization. We're not worrying about optimization just yet. That's going to be something that we start to worry about a little bit more in the future. All right, so we're going to flip back over. And so now I'm looking at these results, and in some cases, it looks like the results are very good. Like right here, I see that we are 0.3% off. In this case, we're 3% off. But in some other cases, it looks like we are like way, way out of place. So here's just about 100% off. Now this definitely makes me think that we might have made a mistake in our calculation. Maybe we didn't, but maybe we did. I don't really know. It would be really helpful if we had some way to kind of do a little bit of introspection here and figure out whether or not we're doing everything correctly. So let's take a quick pause right here. When we come back to the next section, we're going to do a little bit of debugging and just say, yes, these are the real values, or no, we made a mistake and need to figure out how to address this. So quick pause, and we'll do that debugging in the next section. In the last section, we ran our updated analysis that takes into account the square foot lot size and then standardizes all of our different features. Now, when we ran the analysis, we really saw that we got some positive results, like 3% off, 0.3% off, 6%, 1%, but some of them were just bonkers bad, like 64% off, 99% off. So in some cases, it worked really well. In some cases, not so well. Now, it kind of seems to me like we might have some big mistake in our math at this point. And so I think that I don't really know if everything is going correctly. I don't know if everything is going wrong. But it'd be really nice if we could somehow take a look at the logic inside of our program as it is running and verify one way or the other. So to do so, we're going to be making use of a Node debugger and some Chrome debugging tools to debug our running Node.js process, inspect our code, and figure out whether or not everything is going A-OK. So let's give this a shot. To inspect our running application, so the code that we actually have inside of here, we're going to run node --inspect -brk, and then our file index.js, like so. So this is going to run our index.js file, but it's also going to start up some debugging tools at the same time. When these debugging tools start up, this brk part right here, that means that we're going to break on the very first line of code. So in other words, our program is not going to instantly run until we actually open up some debugging tools and connect to this running process. Okay, so I'm going to run that. And then I'm going to very quickly see this output right here in my terminal. So that's good. I'm just going to let that sit. At the same time, I'm going to open up my Chrome browser. So unfortunately, this step does require you to have Chrome installed. If you do not have Chrome, you can either install it or you can just skip the rest of this section. Now with Chrome open, I'll make a new tab, and then I'm going to navigate to about:inspect, like so. Now once here, I'm going to see a page that looks like this. You'll notice something that says remote target right here. This is the running process that we have, and you'll even see, we can see our folder name right there, knn-tf, the index.js. So that is our running Node.js process that at this point in time has been paused in execution. I can click on inspect right here, and then it's going to open up a classic Chrome tools debugger that I can use to walk through my code and take a look at some of the different values that are floating around. Now, at this point, I don't really know if everything's going right or wrong. I just want to take a look at some of the numbers in here and just say, yeah, that seems reasonable, and it just turns out that we got some, bad analysis, or maybe we'll look at a number and say, whoa, that's way off, something is clearly going wrong. So the first thing I want to do is progress the execution of my code all the way until we get into the KNN function. Right now, you'll notice that we've got like a dark blue line up here at the top, particularly on exports. That means that our program is currently paused in execution on this very first line of code. I can open up the debug tools over here on the right-hand side and click on the step over to start to go into my code. And you can see it's now running it line by line. Now, without a doubt, there's a lot of stuff going on here, so I just want to kind of skip ahead and get into the KNN function. So to do so, I'm going to put a blue breakpoint in here by clicking on 6 over there on the left-hand side. And then I can use the blue play button up here to skip everything and get into that KNN function. So now we can start to look at the value of these arguments by entering them into the console down here. We can take a look at the scaling process. And again, we're just trying to verify that these numbers seem like they are correct and that it seems like we are correctly scaling everything and that we're not seeing some like weird outputs here. All right, so the first thing I want to do is take a look at my features variable here. I just want to print it out and make sure that it has the appropriate number of columns in it and maybe even the correct number of rows. So I'm going to do a features.shape in my console, and that's going to print out the shape of that. So I've got 21,602 rows, and I've got 3 columns. I can also do, remember, a features.print to print out some information about the data inside there. When I do so, I see clearly what is longitude, latitude, and I can also see what definitely looks like is a square foot lot size value as well in that 3rd column. And I'm going to repeat that same process for my prediction point as well. So I'll do prediction point.print, and yep, it looks like everything came in the correct order. So I've now established that these inputs into my function definitely are of the correct structure. It definitely looks like things are more or less in the correct state right now. Now let's kind of accelerate or move forward a couple steps of execution by clicking the step over button a couple more times. 1 time and 2 time, like so. So now we can start to take a look at the scaled prediction and make sure that the scaling was done correctly. Then we'll also go through a couple steps in our calculation and again, just make sure that it doesn't seem like anything is wrong. So I'll first take a look at scaled prediction and I'll print it out like so. Now at this point, what I'm really looking for here is to see if any values are way larger than they should be. Remember, we just went through that standardization process. And in that standardization process, we should be ending up with values. Where is that darn diagram? Here we go. We should be ending up with values after standardization that are centered around 0 and go down to -1 standard deviations and up to 1 standard deviation. So they should be somewhat close to 0. If I go back over to my inspector, here we go, and look at the scaled prediction right here, they definitely look like they are very close to 0. If I saw some values in there that were like hundreds or thousands, then it might mean that I had done something incorrectly. Now I'm also going to do some execution on these steps right here. So I'm going to copy everything up to that right there, features, sub, and div. And then I'm going to run it at my terminal, or like so. And, oop, I forgot, let's put a print statement on there at the very end. So now in this case, I'm just going to print out all of my scaled features. And again, I'm just looking to see and make sure that no values inside of here are like significantly away from 0. If I saw that, again, I'd be a little bit worried. It would probably mean that I was doing something incorrectly. Okay, so I'm looking at this again, and it's looking like it's pretty reasonable. I don't see anything that's very off here. So at this point, I could continue to kind of copy paste down some code. By the way, the only reason I'm copy-pasting this stuff down is that each of these individual steps do not get assigned to intermediate variables. And so if I want to easily inspect any of the steps, I have to copy-paste them down here and then manually run a print. Okay, so once again, I'm seeing everything kind of close to 0. So at this point, it feels like everything is pretty much at least working the way that it should. I don't see anything that's sticking out here and making me feel like I did something very incorrectly. Again, if I saw numbers like in the hundreds or thousands, while others were around 0, that would be a big sign to me that I had probably done something incorrectly. So at this point, I would probably say that the output that we're seeing here, oh, I don't have the output anymore, but those percentages of like 99% off and 60% off, those are probably correct. So at this point, I feel like I've ruled out the possibility that I wrote bad code. And now I'm probably going to go back to my analysis and think about how I can possibly improve it by adding in some other different features. from our CSV dataset. Okay, so that's pretty much it. Again, no big issues, no big changes here. I just wanted to show you how I personally would go through debugging my code and doing a real gut check to say, yeah, things are more or less working the way I expect. All right, so let's take a quick pause right here. When we come back to the next section, we're going to try to enhance the accuracy of our algorithm just a little bit more. In the last section, we did a little bit of debugging and just verified that our code was more or less working the way we expect. However, we still do not have a very good accuracy rating. So some ways in which we could improve this would be to maybe do some analysis around our k-value. Right now, we've got a hard-coded k-value of 10. I just chose that value arbitrarily. We could very easily do some analysis as we did previously on our last project and alter the value of k and do some comparison to say maybe there is a optimal value of k. The other thing we can very easily do is add in more features into our data set by listing the header names or the column names here in the data columns property. At present, we're only looking at the house position and the square foot of the lot for making a prediction about the price. One other factor or feature that we could very easily include into our analysis is the square foot living property, which takes the entire square foot of the house itself into account, which is probably very closely related to the actual price of a house. So really quickly, I'm going to add that in here because I suspect it'll probably improve the accuracy of our algorithm a pretty good amount. So I'll put in square foot living, like so. And then I'll flip back over to my terminal and rerun the analysis with node index.js. Now, as this starts to run, you're going to very quickly see that we get some massive gains in accuracy compared to what we had before when we were only looking at the square footage of the lot itself. In particular, you might remember that like the third entry was like 99% off, I think. Maybe it was the second one, maybe it was the fourth one, whatever. But definitely we have way better accuracy than what we did before. So I think that we could probably take this algorithm and do some further analysis and figure out how to really tweak the number of features that we include and the k-value to get some big improvements to accuracy. Even by just adding in the the square foot living size, we're now in like under 20% error, and in almost the majority of cases, we're under 10%, which is, not bad, pretty reasonable, considering we've only worked on this for a little bit, or at least the optimization side. Okay, so at this point in the course, we have spent a tremendous amount of time looking at k-nearest neighbor, and I'm sure that at this point, you probably want to work on some other algorithms and figure out how to, really do some other interesting things with machine learning. However, at the same time, I'm also a little bit sensitive to the fact that we've now spent a bunch of time doing analysis and optimization, but we haven't really seen any application of this stuff. In other words, hey, it's great that we're able to predict house prices, but we are predicting prices of our test set of data. How do we actually wire this thing up to a front-end application and allow some users to enter their house location and their square foot values and get a prediction about their house price? Because remember, that's the end goal of all these machine learning algorithms. So with these two kind of competing things in mind, the fact that you're probably tired of k-nearest neighbor, but also the fact that you want to see some application here, I organized the course to allow you to do either one. So if you want to see how we can take this algorithm and build a front-end app with it, like the exact code that we're looking at right there, then you can go towards the end of this course and find one of the appendixes where it says KNN application or something like that. And you can go to that section right now if you want to figure out how to take all this code and allow users to interface with it in some fashion and get their own customized house estimation. Otherwise, if you want to learn about more algorithms, then just continue on to the next video, where we're going to immediately start to dive into the next algorithm and learn about an entire different way of doing analysis like the way that we've been doing so far. So totally up to you. Again, I'm 100% conscious of the fact that we've only been doing like the test sets of data, which is at the end of the day pretty boring. So if you want to see that very quick application, check out the appendix. Otherwise, I'll see you in the next section.